We will now work our way towards exploring a number of X function in the DAX formula language. So you will observe that I have cleaned up my Power BI desktop. So I have created a new PBIX file, which you can see from the top is named extension functions. There are no visualizations in here. And then in the fields menu, you can see that there are no tables in here as well. This is because we are now going to go ahead and load a few new tables from an Excel file. And this is the Excel file in question. So this is called retail. And as implied by the name, it includes a lot of information with regards to the sales transactions at a retailer. Now the Excel file is included as part of the course materials. Alternatively, you can download the original source files from this location on kaggle.com. And you'll observe that there are 3 different tables in order to represent this data. Each of these are in separate tabs of this Excel file. The first of these is customer, containing details about the customers who carried out the transactions. Then there is a transactions tab containing the transaction details themselves. And then there is prod cat info, pointing to the product categories and subcategories for each of the products which were transacted. As you will be aware, when we load this file into Power BI Desktop, these 3 worksheets will be loaded as 3 separate tables. Before we get to that, let's quickly preview the data itself. Here in the customer sheet, we have the details of a number of different customers, starting with their customer ID in column A. Then we have their date of birth, their gender, whether they are a member of the retail store, and other details with regards to where they are located in the world. And with a quick glimpse, you can see that these customers are scattered all over the world. There are customers in the United States, Germany, Senegal, as well as China. Furthermore, as we scroll along in this particular sheet, you'll observe that there are in fact a lot of customers, a little over 5,600 to be precise. So we are working with much more data than we have previously. Next, let's switch over to the transactions sheet. And in here, well, we have a total of 8 columns, starting with a transaction ID in column A, and then there is a customer ID in column B. This is the customer ID which references the customer sheet. So the transactions and customer tables which will be created when we load this information into Power BI Desktop will be related to one another by their customer IDs. So what are the details we have then for each of the transactions? Well, we have the transaction date along with the product subcategory and product categories represented by a code. Then there is the quantity of an item purchased in a transaction along with the cost per unit, and then the type of shop in which the transaction took place, whether it was over their e-shop, the teleshop, a marketing brochure, or the flagship store. Now, just in case you have gone over to kaggle.com, where the original dataset can be found, you may find that that data source has a few more columns in the transactions table. I had deliberately trimmed this file to keep things a little simpler as we apply different formulas to this data. So now we have a transactions table which includes a whole host of transactions, and scrolling along, we can see exactly how many. Just a shade over 23,000 to be precise. Now when it comes to data analysis in the real world, this is not unusual at all. In fact, you are likely to be working with much larger datasets. Furthermore, a transactions table will typically lie at the heart of all of the different tables in your analysis and should be much larger in size, at least in terms of the number of rows, than the other tables which it is related to. This follows the pattern of a star schema, where we have a central table, which is also known as the fact table, and this is surrounded by a number of dimension tables. In our example, transactions will serve as the fact table, whereas the customer table it is related to is one of the dimensions, and then the other dimension is the prod cat info table. So you will notice that in transactions, we have references to the product category and the product subcategory in the form of a code. And then when we head over to the prod cat info tab, well, we can see exactly what category and subcategory names these codes correspond to. So a product category of 1 corresponds to the clothing category, but this in turn is broken up into 3 different subcategories. 1 for women's clothes, 3 for kids' clothes, and 4 for men's clothes. The other categories include footwear, electronics, bags, and books, and each of these have their own subcategories. So all in all, we just have a total of 24 rows in here, including the header. And now that we're familiar with this new dataset, let's switch over to Power BI and import the contents of the Excel file. For that, make sure that the home menu is up and choose the option to import from an Excel workbook. Then navigate over on the file system to the retail dataset. And then when we choose open, well, from the navigator, we can select exactly which worksheets we would like to pull in to Power BI. When we take a look at customer, a quick glance at the preview shows us that there are a few null values in the postal code column. And following that, let's take a look at prodcat info. And this, of course, is a rather small table. Heading over to transactions, this is a rather large fact table. And then under suggested tables, well, we see another version of prodcat info, which in fact is quite similar to the corresponding worksheet. Now we move on and select the customer sheet to be pulled in. Then we also select transactions, and we can select prodcat info from either of these options. I'll just choose the one under suggested tables. And then to load the data with the default transformations, let's just hit the load button. And soon enough, there are 3 different tables which can be viewed under the fields menu. To view the contents, we head over to the data view. And sure enough, the customer table includes all of the different rows which we saw previously. Heading over to prodcat info, this does contain the same 23 rows of data. And finally, transactions, which is our fact table. And sure enough, it does contain over 23,000 rows in all. So within our transactions table, well, we have a quantity column which shows the quantity of a product which was purchased in a specific transaction. And then there is the rate column which gives us the price of each quantity of the product. Now we don't have a total sale amount, which will tell us the gross revenue generated per transaction. However, this is something which can be very easily computed by simply multiplying the quantity by the rate. Well, for that, we can create a new calculated column. So let's head over to the table tools menu and then choose new column, and just make sure that it is the transactions table which is currently active, since this new column will be added to that table. And then let's define exactly what this column will display. So we can call this column total underscore amount, and then its value is defined by this formula. So we multiply the quantity column in transactions by the rate column in the same table. So once again, make note of the syntax which is adopted here, with the table name followed by the column name within square brackets. So when we hit enter, well, the total amount column has been populated, and it now tells us the total value of the sale represented by each individual transaction. Furthermore, under the fields menu, you can see that total underscore amount now shows up under transactions, that this is a calculated field, and that this can also be summarized. So once we have confirmed that the total amount has been populated for every row, it's time to apply a new calculated column in a visualization. So we head over to the reports view. We will first generate a new table, and then we can decide exactly what columns will be displayed in the table. I'll just quickly expand this though to improve visibility. And then let's just say we would like to see the total sales for each store type. In this case, we will need to aggregate the total amount for each store type. So we can pull in the store type field first into values. And you can see that this has been added to the table. We will soon see exactly what the table looks like once we have loaded in the second column. And this is the total amount. So now that we have a 2-column table, to get a glimpse into its contents, I'm just going to switch over to focus mode. And this is what we have. So the first column points to the 4 distinct values of store type in the transactions table. And then when we add in the total amount column, well, by default, Power BI will aggregate the contents of total amount based on each distinct value of store type. From this data, it is clear that the eShop has recorded the most sales at about 22 million out of the total 54 million in sales. The remainder of the revenues are roughly evenly split across the flagship store, MDR, and Teleshop at about 10 million each. So we have now successfully loaded a new dataset into Power BI Desktop. However, what is significant is that we have not defined any of the relationships between the 3 tables. That is something we will get to later on. And in the next video, we will continue working with just the transactions table by exploring a number of different operations which can be performed using DAX. In the previous video, we created a new calculated column called total amount within our transactions data table. And then we used that total amount in order to calculate the aggregate sales per store type within our dataset. Now this aggregation was only possible because by default, Power BI calculates the sum of numerical values based on the categories displayed in the visualization. In our case, the categories are the different store types. However, what if we wanted to view the average amount for each transaction rather than the sum of all amounts? Well, this is an aggregation which is also possible, but for that, let's head back to the report view, and then I'm just going to expand the menu for the total amount under the values, and you'll see that by default, it is the sum which is selected as the aggregation to be performed. We have seen previously in this learning path in the video working with table visuals that it is possible for us to not summarize a value, but now we will see what happens if we were to change the aggregation to an average calculation rather than a sum. And the moment we do that, well, the values have been updated in the table, and I'm just going to hover over the average for the Teleshop in order to view its value. You will recall that the sum of all transaction amounts for the Teleshop store type was a little over 10 million, but the average transaction amount is just about 2319. So this was a quick glimpse into how the type of summarization can be changed. So I'm just going to expand the menu once again in order to switch back to a sum. And with this change done, well, we will now move on to defining another calculated column in our dataset, for which we head over to the data view and then make sure that it is the transactions table which is active. And then from under table tools, we head over to new column. Before we get to that, let me quickly explain what exactly this new column is all about. So we can see that the total amount for the transaction is available in the total amount column, but let's assume that discounts are applicable for each of these transactions, and the rate of the discount varies according to store type. Well, in this case, we will need to create a new calculated column which looks at the store type, applies one discount for eShops, and then applies another discounted rate for all of the other store types. Well, for this, we can make use of an if function. So once a new column has been created, in the formula pane, let's give this new column a name of discounted underscore amount. So I'm sticking with the naming convention adopted in the original dataset. And then to set its value, we make use of the if function. And then let me just paste in the remainder of the formula for this calculation. And then I'll just hit enter for it to take effect. And then let's see exactly how this computation is performed. So you'll remember that the first argument to the if function is a logical test to be performed. In this case, we check whether the store type column in the transactions table is equal to eShop, and if it is, the value returned is defined by the second argument to the if function. In this case, we compute a rate 0.75 times the total amount. So this effectively serves as a 25% discount for eShop transactions. Then the third argument to the if function corresponds to the value when the condition evaluates to false. So when the store type column is not equal to eShop, well, we apply a 5% discount by multiplying the total amount by 0.95. So this is how an if function can be used to perform an operation based on a condition, just like with any programming language. So now that we have the discounted amount column, we can quickly scroll along and confirm everything has been populated. And then to use it in a visualization, we head over to the report view and we can just drag and drop the discounted amount measure over to a table. So we now have three columns: store type, total amount, and discounted amount. And just as a quick reminder, by default, a sum aggregation will be performed. I'll just switch over to focus mode so that we can view the values more clearly. And there you have it. If you'd like to confirm that the discounts have been applied correctly, well, take a look at the discounted amount and total amount columns. In the case of the eShop, the total amount is about 22 million. However, the discounted amount at about 16.6 million is 75% of the total amount. Whereas for each of the other store types, well, the discounted amounts are just a shade under the total amounts, about 95% of their values to be precise. Furthermore, you will observe that the discounted amount total is about 47.422 million. Now, let's just say this is the value we are really interested in, where we'd like to calculate the sum of all discounted amounts using just the total amount column in our transactions table and ignoring our newly created discounted amount column. Is there a way to sum up all of the values based on the conditions which we specified in our if function? Well, the answer is yes. Specifically, we can make use of the SUMX function. And just as a quick reminder, the goal for us is to calculate this value of 47.4 million using just the total amount column and not discounted amount. For this, we will create a new measure using the SUMX function. First, however, let's switch out of the focus mode and then reduce the table size, because just a little later, we will add in a new card visual in order to display the result of the SUMX function. Next, let's head over to the data tab, and the goal for us is to perform a sum calculation based on this if condition here. If you have used Microsoft Excel before, you will know that it includes a basic sum function, and that function also exists in Power BI's DAX. While the function is extremely useful, it is limited in scope in that it can only perform a simple sum operation based on an entire column. What we want is a conditional sum to be calculated based on the store type. Well, for that, let's head over and create a new measure. And this new measure will make use of the SUMX function. First though, the name will be sum of discounted amounts, and then we'll make use of the SUMX function, and the little tip which pops up points to the fact that there are two arguments which SUMX takes in. The first of these is a table, and the next one is an expression. The table in question in this case is the transactions table. As for the expression, well, this will become familiar to you once I paste in the code. I'll just hit enter for this to take effect, and then let's go over what exactly the SUMX function accomplishes here. So as I had mentioned, the first argument points to the table where the operations will be performed, rather the sum operations will be performed, and this is transactions. And the second argument is an expression which will be performed on each row in the given table. And the expression here is in fact exactly the same as what we did previously when computing the discounted amount column. So we use an if function to check whether the store type is eShop. If it is, we apply a 25% discount. So we multiply total amount by 0.75. And if not, we apply a 5% discount. Since this if operation will be performed on the entire transactions table, well, what we will end up with under the hood is something similar to what we see in the discounted amount calculated column here. However, SUMX will simply sum up the values in order to return to us a single scalar quantity. Once the measure has been created, well, you should see the sum of discounted amounts pop up as a new field, and this also shows up as a calculated value. But now to see whether this has calculated the discounts correctly, let's head back over to the report view. But before we pull up a new measure, let's apply some formatting to our table. So under the visualizations menu, well, we are currently in the table settings, where we can define exactly what our visualization should portray. So of course, in our case, the store type total amount and discounted amount columns are visible. However, in order to configure the aesthetics of this table, more specifically to increase the font size so that the text is more clearly visible, we can switch over to the Format tab. In here, there are a whole host of configurations which mainly revolve around the aesthetics of our visualization. Since we're not really focused on visuals now, I'll just quickly scroll along so that you get an idea of the different categories of formatting which can be applied. So we can separately format the total row which appears at the bottom. There is also some conditional formatting which can be applied. But in order to increase the text size within the table cells, well, we just expand the values menu and then scroll down to the text size setting. Here I'll just increase it to 14 points, and now that the text is more visible, well, we can also confirm that the sum of the discounted amounts is 47.4 million. We will soon see that our new measure will return this same value. First, however, let's head over to the Fields tab for our visual, and to add a second visual to this report page, well, let's just click on a space outside of our table. And then we can head over to the visualizations pane and then click on the card visual. Once it pops up, I'll just move it over and resize it. And then in order to make use of our new measure and display it in this card, well, let's just click on the card itself so that it is the active visual, and then drag and drop our newly created measure, sum of discounted amounts, over to it. And what we see is that the sum is 47.42 million, which matches the total calculated for the discounted amount in our table. So we now have an idea of how the SUMX function can be used in order to sum up values based on an expression. Now we haven't really focused on formatting the values in either our table or card visualizations, but now that the card is active, well, let me just show you how we can display the original value for the sum of discounted amounts rather than express it in millions. We will need to head over to the Format pane and then over to Data Label. And there is a Display Units menu, which has been set to automatically be configured. But let's expand this. You can see that we can format it as thousands, billions, and more. But let's just set it to none. And now we can see the full value, which exactly matches what we have in the total row for discounted amounts in the table. So now that we know how the SUMX function can be used, in the next video, we will focus on another summarization based on an expression, namely the AVERAGEX function. In the previous video, we made use of the SUMX function in order to sum up specific values in a column of a table. Looking at the formula itself, you can see that we applied it to the transactions table, and then using an if function, we defined the expression. This allowed us to perform a sum operation with some complexity, where we summed up the discounted amounts for e-shops applying one discount rate, and then for all of the other store categories with a different discounted rate. I reiterate this because it is important to understand how exactly the X functions in DAX work. We will now focus on making use of the AVERAGEX function, which, like SUMX, performs an aggregation based on an expression, but the aggregation in that case is an average rather than a sum. You'll observe that I'm now in the data view, and this is not quite needed, as what we will be doing next is to create a new measure. And then let's go about filling in the details. So I'm going to create a new measure which only computes the average transaction amount for the e-shops. So this measure is not concerned with any of the other store categories and will just return a 0 for those. So let's see how this can be accomplished. So the name of this measure is average eShop transaction amount, and then make sure that it is the AVERAGEX function which will be used. I'll just go ahead and paste in the remainder of this formula then, and this is what we have. So the goal here is to calculate the average transaction amount for eShops based on the total amount column and not the discounted amount. So when we apply AVERAGEX, well, just like with SUMX, we first need to point to the table to which the AVERAGEX formula will be applied. This is transactions in our case. And then we define the expression which will be applied to each row of transactions before the average function sums up the values. In this case, all we really want is for the total amount for the eShop transactions to be returned as is, and then we want to ignore everything else. So you can think of this as the X or the expression portion of the AVERAGEX formula, where we just filter through the eShop transaction amounts. And then the average portion of the AVERAGEX formula will compute the average of those amounts. So we just apply the if function to filter through the eShop transactions by checking the store type column within the transactions table and then returning the total amount column as is. Now the third argument to the if function points to what is returned if the logical test fails. That is, the store type is not eShop. In this case, we will just return a 0. So keep in mind that we will use this AVERAGEX measure in a table rather than in a card, so that when computing the average, we are in fact doing it for each individual store type, and it is only the eShop which will have a non-zero value. We will get to that in just a moment. For now, however, our newly created measure has taken effect. So to put it to use, we head over to the report visual, and then let's drag and drop the average eShop transaction amount over to the table. So you can see a fourth column appear here. What is significant though is that for all of the non-eShop store types, this AVERAGEX computation returns 0. For the eShop, however, well, this is correctly computed as 2385. So in this case, the average has been correctly computed for just the eShop based on our AVERAGEX formula. However, for each of the other store types, we have a 0 returned. We will now focus on exploring a variety of DAX functions to get a sense for what exactly this formula language has to offer, and importantly, how exactly it can be applied in various visualizations. We will now focus on the blank function. Before we get to that, well, I'll draw your attention to the postal code column in the customer table of the retail sales dataset. So you will observe that for all of the rows which are currently visible, there is no value for postal code. This is quite common in many large datasets, where some information will only be available for specific instances. And whenever the details are available, it may be important for the analysis. However, in the case of our analysis, well, the postal code is not quite relevant, in which case we can just select it and then delete it. In case you're wondering why exactly we should delete this and not retain it, given that it can contain information and doesn't really get in the way of our visualizations, well, the answer has to do with performance. So this data has been loaded into Power BI in import mode, which means that it is all residing in memory. Given that, it is best to ensure that only the data which we absolutely require for our visualizations is loaded into memory. So it helps for us to trim down our dataset and remove any unnecessary columns which are not essential for analysis. So to remove postal code, we can just click on it and choose the option to delete. Once we make this selection, we will be prompted to confirm that we want to go ahead. I'll just provide that confirmation. And now we are down to a reduced dataset, and we are ready to proceed with the use of the blank function in a DAX expression. First, however, I'll point you to where exactly we will apply it. So in the gender column, you will notice that the values in view are either F or M, but in the third row, there is a value of NA. This is where the gender of the customer is not known, so it has just been listed as not applicable. But consider the case where we would like to replace it with a blank instead. Before we get to that, let's consider why this might be useful. Well, there are just a lot of functions which treat blank values differently than when there is a value. For instance, there is a count function in DAX which counts the number of cells in a particular column which contain non-blank values. If you would like to use that function to calculate how many customers there are whose genders are known, well, having a value of NA will not really work because this will serve as a non-blank value and will be treated the same as F or M. So for our purposes, let's just create a new column where NAs are replaced by blanks. Once the formula pane is up, I'll just fill in the values here. The new column will have a name of gender blank to separate it from the gender column. And then, well, we can make use of an if condition. Essentially, we'll check whether the gender column contains NA, and if so, we will replace it with a blank. So let me just complete this formula. We will need to reference the gender column, and then we check whether it is equal to the string of n.a. If it is, well, to replace it with a blank value, we can simply call the blank function. And if the value is not NA, well, we simply use the value in the gender column as is. So I'll just hit enter for this to take effect. And before we take a look at the contents of the column, let's quickly summarize the DAX expression which we used to create it. So if the value of the gender column is equal to NA, we will call the blank function, and this will return a blank value in the context of Power BI. And if it is not NA, we simply use the gender column as is. And now when we take a look at the gender blank column itself, well, the first two rows have a value of F, which match the value in the original gender column. But for row number 3, we now have a blank. With any DAX function, it is best to reference the official Power BI DAX documentation in order to understand how exactly it works. And this is where you can find the page for blank. Now we can scroll along to confirm that this has been populated correctly for each of the different rows. But with a quick glance, well, things do look fine. But for a sanity check, let's just expand the menu for this gender column, where we can see that the distinct values here are F, M, and NA, and there are no blanks here. And then when we take a look at the values in the gender blank column, well, these are either blank, F, or M. Significantly, there is no occurrence of NA here, and this is how blank values appear in this view. Alright then, let's get out of this view. And now to see how exactly the gender and gender blank columns vary in terms of behavior when used with the count function. So our goal is to figure out how many customers exist in our dataset whose gender is known. And we can try to extract these values from both gender and gender blank. We will create a new measure for this, however, and then this new measure will be called gender count, and this will make use of the count function. From the description, you can see that this counts the number of values which are present in a given column. So we make this selection, and then to fill it up, we can just point to a specific column within our data. So we'll point to the gender column in the customer table. So this is what our gender count measure looks like. And now to see what value it returns. Before we get to that, however, I'll draw your attention towards the bottom left of the window, which points to the fact that the customer table has 5647 rows. So how many of these 5647 rows have a valid value for gender? For that, we head over to the report view. From the visualizations pane, we select a card visual. And I'll just resize this so that it is of an appropriate size. And then to display the value of our gender count measure, let's just drag and drop it into the fields. And as you might expect, this returns 5647, corresponding to the entirety of the customers table. Of course, we know from the existence of at least one NA value that there was at least a single invalid value for gender. And if we are to use the count function to count the number of valid values, well, we will need to reference the gender blank column instead. So for that, let's just go ahead and select the gender count measure which we just created and then edit it so that it will point to the gender blank column. And then when we hit enter, well, our card visual has updated immediately and points to a value of 5645. So clearly, there are two instances in our dataset where originally the value of gender was NA, but in the gender blank column, it is simply a blank value. So you now have an idea of how the blank function works and also significantly how the count function works, especially with blank values. When modeling data with Power BI, it is important to keep these factors in mind so that the visuals portray the data as accurately as possible. Now for a quick side-by-side comparison of what the count function returns as applied against our two gender columns, I'm just going to edit this measure so that it points back to the original gender column. So we're back to a count of 5647 in this card visual. And we'll now go ahead and create a new measure. And this one references the gender blank column. So we'll call this gender count blank. This applies the count function on gender blank. And once this measure is in place, well, I'll quickly adjust the size of our first card visual and then click outside of it before adding in a second one. With this new visual, we just drag and drop the most recently created measure, which is gender count blank. And sure enough, this returns a value of 5645. Having successfully implemented the blank and count functions, well, if you would like to further expand your knowledge on how exactly the count function can be used, you can reference this page in the official DAX documentation. In the next video, we will move on from the basic count function over to a variety of count functions, which allow us to compute the counts of different types of values. In the previous video, we saw that the count function in the DAX formula language allows us to calculate the number of non-blank values in a column of a table in Power BI. This is a useful function when we are trying to get a profile of the data in front of us. We will now explore a variety of other count functions which allow us to count the occurrences of different types of values. Next up, we will make use of the count rows function. For this, we can navigate over to new measure and then let's start typing in this new function which makes use of count rows. So the name of this measure is simply count rows, and then we search for the count rows function, and as the description tells us, this simply counts the number of rows in a given table. So the argument here is a table itself. Let's just pass along customer, which we know has 5647 rows. And once this new measure is in place, well, we can use it in a card visualization. So I'll just click on some blank part of the report page, click on the card visual, and then drag over the new count rows measure over to the field section. Sure enough, within our customers table, there are a total of 5647 rows. So the count rows function can be useful when we want to know the overall size of the dataset. This can be useful either for us to view the values directly as we have here, or as part of a broader calculation, where perhaps we want to know what proportion of a table's contents have a specific value. To compute the profession, we will of course need to know the total number of rows in the table, and count rows will return it to us. Let's move along then from count rows over to another count function, specifically count blank, which you can think of as the inverse of the count function. So while count returns the number of non-blank values in a specified column, count blank returns the number of blank values. To see it in action, well, as you may have guessed, we create a new measure. Let's call this one count blank gender, since this will count the number of blanks for the gender. For this, we will make use of the count blank function and then apply this not to the old gender column but the gender blank column. With this selection, let's hit enter so that the new measure is created, and we can confirm the creation in the fields menu. And now to make use of it, again, let's click on a blank portion of the report, create a card visual, and to load it with the new count blank gender measure, we can either check it or drag and drop. Sure enough, this returns a value of 2. So we now have 4 different functions which we can compare, but let's focus on 3 of them. So the number 5645 points to the use of count on the gender blank column, and the value of 2 points to the use of count blank on that same column. Together, they sum up to give us a value of 5647, which is what the count rows function returned. These distinctions, though they seem tiny, are important, not just from the point of view of the DA-100 certification exam, but also when using Power BI to build your own reports. Let's move on then to another count function, and this is to count the number of distinct values in a specific column. So we create a new measure. Let's call this one distinct count, and then the function itself in this case is called distinct count. The argument here is the name of a column, so let's count the number of distinct values in the gender blank column. So once this measure has been created, well, I guess we already have some idea of what the outcome of this measure will be. So all we really need to know is whether blank counts as a distinct value, since we know that the other 2 values in the column are F and M. So to see what this returns, let's click on some portion of the report, create a new card visual, and then populate this with the new distinct count measure. And the value we get back is 3. So blank does count as a distinct value, at least in the context of the distinct count function. While we have applied the distinct count function to the gender blank column, you can easily imagine that this can be very useful when applied to many different types of values as well. If we have a product catalog and we want to know the number of distinct products on offer, well, distinct count can be applied. Now you might consider the fact that the distinct count function does suffer from the drawback that it counts a blank as a distinct value. To get the distinct counts by ignoring blanks, well, let's go ahead and create a new measure. We'll call this one distinct count no blank. And there is in fact a DAX function called distinct count no blank. So this works in much the same way as distinct count, however it ignores blanks. So let's just apply this on the gender blank column in the customer table. And then to see that it returns a value of 2, we will go through the same steps, where we click on the report, create a new card visual, and then populate it with a newly created measure, distinct count no blank. And sure enough, this does return a value of 2. Having used the count function a few times, well, let's now explore a related function called COUNTA. Heading over to the data view, we saw that the count function can be applied on both the gender and gender blank columns, and the COUNTA function can also be applied on those same columns, and the same values will be returned. In the context of DAX, the only difference between count and COUNTA is that COUNTA can also work on Boolean data types. However, we will now apply the COUNTA function on the city column. So let's just get a preview of the contents of this column by expanding the menu. And you can see here that there are a handful of blanks in this column and also a number of non-blank values. So now that we have an idea of what this column contains, we can cancel out of this view and then head over to the Reports tab, where we will create a new measure which makes use of the COUNTA function on the city column. So we create a new measure for this. The name of this measure will be COUNTA city, And then the expression in this case will be count A. And then we will apply this to the city column in the customer table. And then we hit enter for the new measure to be created. And then I'll quickly cycle through all of the steps to add a new card visual and then drag and drop count A city. And this tells us that there are a total of 5644 non-blank values in the city column. So we have now made use of a variety of different count operations from count, count A, count rows, and distinct count among others. In the next video, we will see how a lot of those count functions can be used together along with other DAX functions in order to perform some complex calculations. We will now continue working with different types of count functions in Power BI's DAX, but we will do so by using them together with other DAX functions, namely calculate table as well as filter. Towards the bottom left of this visual, we have made use of a card visual in order to display the value of a measure which made use of the count rows function. Just as a quick reminder, count rows allows us to count the number of rows in a given table. Now, what if we wanted to filter a table based on the contents of one of its columns? Well, this is something which can be done by making use of the calculate table function. To see how that works, well, let's go ahead and create another measure. And this is a measure which will be used to count the number of customers who are located in the country of Germany. So we will give this a name of count of all German customers. And we will perform this count by creating a table which only contains all of the customers where the country is equal to Germany, and then counting the number of rows in that table. Well, in that case, we will need to make use of the count rows function. So I'll just apply that. And then to create a table containing only these German customers, we make use of the calculate table function. From the description which pops up, you can see exactly what is expected when we call calculate table. So typically, we pass along at least two arguments. The first of these is the table on which the operation is going to be performed. So this is the table to which a filter can be applied. And then this is followed by an array of filters. And then the filters will be combined using an AND operation. In this case, however, we just have a single filter condition. But let's see how exactly this is used. So our goal is to filter through those customers where the country is equal to Germany. So for the first argument here, we pass along the customer table. So this is the one on which the filter will be applied. And then we define in the second argument to calculate table, the filter itself. So this is where we look for those rows where the country is equal to Germany. Now, we have made use of the calculate function before, and you may recognize that this does look quite similar to it. In fact, calculate table and calculate are quite similar, except that calculate returns a single scalar value, while calculate table returns a table. In this case, the table will contain all of those rows in the original customers table, where the customer country is equal to Germany. So let me just close out the parentheses in order to complete this DAX expression. So let's quickly take stock of what we've accomplished here. We first create a table using the calculate table function containing only those rows of customer where the country is Germany, and then we apply the count rows function on it to count the number of rows in that table. This will give us the count of all German customers. Alright then, to create this measure, let's just hit enter, and then under the fields menu, you can see in the customer table that the count of all German customers does show up. Alright then, it's now time for us to view the number of German customers. So we will repeat the steps we have gone through a few times already by creating a new card visual and then displaying the count of all German customers. And in the case of our table, well, there are a total of 278 of them. So we now have an idea of how to make use of the calculate table function And we have seen that it allows us to apply a filter on an existing table. More precisely, it allows us to apply a filter context on a table. Another DAX function which allows us to specify a filter over a table is simply called filter. And we will now use that in order to create the same table of German customers as we did just a little earlier with calculate table. However, we will use that table to perform another operation. Well, to demonstrate that, let's head over and create a new measure. And what exactly we will do with a table of German customers is to count the number of customers who have a non-null value or non-blank value for city. So we will call this measure count of German customers with non-null city. So the question is, out of the 278 German customers, how many have a valid value for city? Well, for that, we make use of the COUNTA function. COUNTA is quite similar to COUNTA, which we have already covered previously. And just as a quick reminder, the description here says that COUNTA allows us to count the number of values in a specific column in a table. However, this can only happen on a table which already exists. But in our case, we want to create a table on the fly containing only the German customers. Well, for that, COUNTA is a better option. Here, there are two arguments which can be specified. The first of which is a table, and this is a table which can be created on the fly using a DAX expression. In fact, once we have the table, you can see that for COUNTA, the second argument is an expression, so we can even transform the table which we create on the fly. In our case, however, you'll recall that our goal is to count the number of German customers where the city is non-null or non-blank. So what we require for the first argument is a table which filters the original customers table. And for this, well, we will now make use of the filter function. This is one which allows us to apply a single filter expression on an existing table. So the first argument here is the table to which the filter needs to be applied, and then the second argument is the filter expression. And what it returns is the filtered table. So you can see that this is very similar to the calculate table function which we just used. However, there is a significant difference. In the case of the calculate table function, there are multiple filter expressions which we can supply. In this case, however, there is just one. For our purposes, however, this is more than enough. And this is the entire DAX expression we will use. So let's quickly take a look at what exactly is accomplished. So for COUNTA, the first argument is a table which is created by making use of the filter function. The first argument to filter is the table on which a filter will be applied. So this is the customer table. And then we have the expression to define the filter. In our case, we check that the country is equal to Germany. So this will return the 278 customers in the customer table from the country of Germany. So this is a table of German customers created on the fly. And it is this table which makes up the first argument to COUNTA. The second argument, well, this can be some expression, but it can also point to a specific column over which the COUNTA operation will be applied. So by passing along the city column of customer, well, combined with the filter, we will effectively count the number of German customers for whom the city column is non-blank. So let's just create this measure, and to check out its value, well, I'm just going to drag and drop this count of German customers with non-null city over to our existing card visual. And from the previous value of 278, this has been dynamically updated to 277, pointing to the fact that there was a single German customer who had a blank value for city. So there you have it. We have now successfully made use of the calculate table, filter, as well as COUNTA functions. We have seen how calculate table and filter can both be used to create tables on the fly, and also how those can be used in conjunction with count functions. In the previous videos of this course, we have covered the fact that it is possible for us to call DAX functions within other DAX functions. Continuing in that mode, we will now explore how we can call an if function inside an if function. For this nested if statement, we will make use of the transactions table which we previously loaded and effectively serves as the fact table in the schema containing a customer, prodcat info and transactions tables. In the transactions table, there are a number of continuous columns, that is, columns filled with continuous values, such as the total amount, and then there are also columns containing categorical data, such as store type, where there are 4 different categories of stores. Now, in many instances, it may help for you to convert a numeric or continuous value into categorical or discrete data. As an example, let's look at the total amount column. This of course includes a whole host of values in a range, and even amongst the values which we can see in this view, you'll observe that there are some transactions where the amount was 7,300 units, and in others, it was as low as 355. Now, what if for your analysis, it's not quite important what the exact amount of each transaction is, but it is more relevant if you know if a certain transaction happens to be of a high value, a low value, or somewhere in the middle. Well, we will now make use of nested if statements or if functions to transform this data in continuous form into discrete form. For that, we will create a new column in the transactions table, and let's just call it total amount groups. Before we proceed, however, let me remind you that we have covered how to transform a continuous column into a discrete one by making use of the data groups option, which is available in the top ribbon, which allows us to define different groups in a table based on the value in a specific column. Now that is exactly what we are going to do with nested if functions, and the goal is simply to understand how nested functions in Power BI work. So let's just go ahead, and we will start off, of course, with the if function, and we're going to break this table into various categories based on the contents of the total amount column. The first test we will perform, or the first logical test, is to see whether the total amount is less than or equal to 2000 units. If it is, we will mark out the row as representing a low value transaction with the string low. And then the second argument to the if function is what exactly the value should be if the logic test is false, that is, if the value is greater than $2,000. But now we would like to split all of these transactions greater than $2,000 into 2 categories of their own. So, in order to perform the split, we make use of a nested if function. So once we make that selection, well, the logic test for this function is where we confirm that the total amount for the transaction is greater than $2,000 and that it is less than or equal to $6,000. So note the use of the double ampersand operator here in order to perform a logical AND operation. So if the transaction amount falls in the $2,000 to $6,000 range, we will mark it out as a medium value transaction. So our new column will contain the string medium. And if the logic test for this inner if function evaluates to false, well, we mark out the transaction as containing a high value. So let's just close out the parentheses so that we have a new column, which is of course a calculated column, and we can see the results. So the first 4 rows are all marked as high, and you can see that the total amounts in each case are comfortably greater than $6,000. In fact, they're all greater than $7,000. The next 3 transactions fall in the 2,000 to 6,000 range, and they have been marked as medium, and each of the others have been categorized as low value transactions. So this is how we can cast out a numeric column into categorical or discrete form. And while you could accomplish this by using the data groups option in the menu, well, nested if functions can also work if the categorization is relatively simple, as in this case. Now, let's answer the question, how exactly such groupings might be useful? Well, for that, let's just say you only want to focus on one set of transactions representing the high value ones, Well, looking at just this data table, we can apply a filter in the new total amount groups column. So let's just expand the menu, and then from all of the different values, to just view the high value transactions, we uncheck select all and check the value of high. Well then, let's just hit OK for this filter to be applied. And here we have just the high value transactions. And while at the bottom of the window, we can see that there are a total of 1050 rows, which represent high value transactions out of the 23,000 plus in the original table. You can also see this 1050 number as you scroll along. So in this way, we can perform a profiling of this total amount groups column, which will help us better understand the contents of our table. Next, we will modify this filter here just a little bit. So we will now stick with just the low value transactions. And we can see here that a total of nearly 12,000 rows out of the 23,000 fall into this category. So we already have an idea that a majority of the rows in our transactions table represent low value transactions, at least based on our own definition of low value transactions, as those where the total amount is less than or equal to $2,000. As a final sanity check, let's just bring up the filter once again and then modify it so that only the medium value transactions can be viewed. And with this in view, we can confirm that a little over 10,000 rows fall into this category. So this is how column profiling can help us understand the data, and in this case it clearly points out that just a fraction of the data points to high value transactions. Now it is possible for us to generate a visualization which displays the count of rows corresponding to each of these groupings we have just defined, so that the end users of our reports have an idea of how the total amounts of the transaction are split up. Alternatively, we as data analysts can just think of this data as helping us decide what visualizations need to be included in the report in the first place. Do we try to categorize the transactions based on this grouping we have just defined? Do we redefine the groupings? Or can this information help us decide what type of visualization, that is, what type of chart, should be presented in the report? In any case, we are now familiar with how to make use of nested if functions in DAX. Previously, we covered the use of nested if functions in DAX, and if you have used any programming language before, you will recognize that nested ifs can in fact in many cases be replaced by a switch statement. This also applies to the DAX formula language, and we will now apply a switch statement, or rather a switch function, on this transactions table. So when we performed a nested if operation, we applied it to the total amount column in order to transform this continuous column into a categorical one, giving us the new total amount groups calculated column. When applying the switch function, well, we will transform a column that is already categorical, namely the store type column, to another set of categorical values. As a quick reminder, there are 4 distinct values in the store type column within the transactions table, namely eShop, Teleshop, Flagship Store, and MBR. What if in the case of our analysis, these 4 categories are not quite what we need, and instead, we would like to map these existing categories for store type into these other categories. So we will refer to eShop transactions as online, Teleshop transactions as phone, and everything else as offline transactions. Well, you may recognize that this can be accomplished by using if functions. However, it is simpler to accomplish the same thing using a switch function instead. In any case, we will now create a new column in this transactions table. So once the table is active, let's go ahead and click new column and then put in the formula for this column. Starting of course with the name, let's just call this one store category, and the contents of this column will be determined by a switch function. So this description tells us exactly how the switch function should be defined. So we start off with an expression, and this is followed with one or more pairs of value and result. So if the expression evaluates to value 1, then the contents of this new column will be result 1. And then similarly, we will have other value and result pairs. And finally, we will have an else result for any values which we don't explicitly define. If you're unfamiliar with switch, this may all seem rather abstract to you. So let's just proceed with our example to see exactly how this works. For the expression to be evaluated for this, well, we want to check the contents of the store type column, since this will determine what the contents of the store category column will be. So this is going to be the first argument to switch, and this is the expression to be evaluated. And then we define a value which that expression might take, based on which we will define a result. In our case, if the value of the store type column is equal to eShop, well, we would like our new store category column to show online. So these are the next two arguments which we supply here. So value 1 is eShop and result 1 is online. Similarly, if the store type column in transactions evaluates to teleshop, so this is value 2, then we would like our new column to show phone. So we have now covered two pairs of value and results based on the expression to be evaluated for switch. And then for everything else, well, we would like the value offline to be rendered in store category. The effect is what we defined a little earlier. eShop transactions will map to online, teleshop ones to phone, and everything else to offline. To confirm this behavior, we can of course just hit enter. And we now have a new store category column. For each of the transactions in view, the store type is equal to eShop, which is why the store category is equal to online. Scrolling further along, well, there are more and more online transactions, but soon enough, we will get to a point where there are transactions performed at the flagship store. Since these neither correspond to eShop or teleshop transactions, these have been marked as offline in our new store category column. As you continue to scroll, you will come across some teleshop transactions which have been mapped to phone transactions in our new column, and then those purchases made using the mail-in brochures, well, these have also been marked as offline. So using a switch statement, we have successfully transformed one categorical column into another one. So when it comes to modeling data for Power BI visualizations, all of this can become important. If the contents of the raw data is not quite in the form which can be presented in visuals, well, you may need to perform this type of transformation. To understand why this might be helpful, well, let's consider the fact that an end user is more familiar with the terms online, offline, and phone, and if they'd like to view only the offline transactions, they can just pull up this filter and then select only the offline ones. Now I'm demonstrating this using a table over here, but it is also possible to implement such a filter for a visualization. So in this case, transactions performed at both the flagship store as well as using mail-in brochures are visible in this view. And you'll also see that there are a little over 9,200 rows of data corresponding to offline transactions. So with this type of grouping, we have effectively aggregated both flagship stores and mail-in brochure transactions into a single unit, and potentially for your visualization, this may make more sense. In the DA-100 certification exam, you may be presented with such a case, where you may need to combine the rows based on the value in a specific column, and keep in mind that a switch statement may be your best option. For a quick sanity check, let's just readjust the filter so that instead of offline transactions, we only view the ones which have been categorized as online using a switch function. And sure enough, the store type in each of these cases is eShop. The focus of this course was to get you familiar with the DAX formula language, and you got to apply a number of different functions which cover a breadth of operations which are very helpful for data analysis. You started off by performing aggregation operations such as sum and average, but covered how these can be made more complex by computing such values using an expression on the raw data rather than on the data directly. This involved the use of functions such as SUMX and AVERAGEX. You also got to see how blank data can be generated in DAX and how these are treated by different DAX functions, whether they are ignored or considered a distinct value. You also explored a variety of counting functions, ranging from simple counts of values to conditional counts based on filters. These included count rows, distinct count no blank, and a few others which have their own specific use cases. Finally, you made use of the if and switch functions, which cover how DAX can be treated very much like a regular programming language, though with a different syntax. You got to implement nested if calls and got to see how these work very much like nested if statements in programming languages. All of this got you familiar with the DAX syntax, the use of functions to calculate values, and how table data can be referenced within these functions. Now that you have completed this course, you are well versed with the DAX formula language, which is a crucial building block when it comes to modeling data in Power BI. This has prepared you to apply your newly acquired skills in building your own models for data analysis, or to move on to more advanced topics with regards to data modeling in Power BI. One such topic which is essential to truly mastering DAX is the filter context, and this is covered in depth in the upcoming course in this learning path, as is the topic of relationships between tables, which is also an important element of building robust and efficient models in Power BI. The dataset we have been working with in the previous few demos of this learning path contain three different tables: customer, prodcat info, and transactions. Here, transactions is the fact table, and then we have customer and prodcat info as the dimension tables, which give us more information or more context around the transactions. Intuitively, the customers table will contain more detailed information about the customers corresponding to each transaction. And from the customer table, which is up here in this data view, we can see that this includes not just their customer ID, but also their date of birth, gender, as well as details about their geographical location, such as country, state, city, and also market and region. So by combining the customer and transactions tables, we can get a lot of interesting bits of information. For example, the total value of sales recorded in each region or even each market, country, or city. However, this is something which is only possible if we were to explicitly relate the two tables to one another, and this is what we will now explore. When it comes to modeling data, relationships are often the first things which pop to mind, especially if you come from a background in relational database design, and this is also a very important consideration in Power BI, not just from the point of view of the DA-100 certification exam, but also when you use it on a day-to-day basis for your own data analysis. Now, such a relationship can only be established if there happens to be at least one common column between the two tables, and for that, I'll draw your attention to the customer ID column in this customers table. So, when we head over to the transactions table, well, this does include a transaction ID, but right next to it, there is a reference to the customer ID as well. Furthermore, you will know that there are a little over 5,000 customers in the customer table and over 23,000 transactions in this transactions table. This means that there are multiple transactions corresponding to each customer, which is why the relationship between customer and transactions is one to many. This is referred to as the cardinality of the relationship, and this is something we will explore in a little more detail just a little later. Alright then, now that we have an idea of how customers and transactions are related to one another, well, let's see why exactly a relationship is needed. So we will first create a visualization without mapping the relationship. So heading over to the report view for that, where we will create a table visualization in order to display the total sales recorded in each region. We will see what values appear before a relationship is defined and afterwards. So, of course, let's expand the transactions view here, since we will require the total amount column from this table. We will need to aggregate, more precisely, sum up the total amounts for each region. And speaking of region, that is a field which can be obtained from the customer table. Alright then, now it's time for us to create this new table visualization. I'll just expand it a little bit. And then following that, let's populate it with the data which we need. First, let's include the region as a column. And then, to view the total sales per region, let's drag along the total amount column. Now the text here is not quite visible, so to make it a little larger so that it can be rendered, I'm just going to switch over to the Format pane under Visualizations. And to increase the font size for the values rendered in the table, we will need to head over to the Values menu and then head over to Text Size, and I'll just increase it to 20 points. So now the text is more clearly visible. So what exactly does this tell us? Well, I'll draw your attention to the bottommost row pointing to the total value of the total amounts. So the sum of the total amounts for the entire table, and this comes to a little over 54.59 million. However, it is the same value of 54.59 million which appears for each individual region. This is because we have not explicitly defined the relationship between customers and transactions, which means that every transaction maps to every single customer, and correspondingly, every transaction also maps to every single region. So without explicitly defining the relationship between customers and transactions as one-to-many, effectively, a cross product has been performed between the two tables, leading to this output. So you can see that without us explicitly defining the relationship, the data itself is not really useful in terms of analysis. So of course, what we really need in this situation is for the accurate sales data for each region to be displayed. So the total amount corresponding to Africa should be the sum of the total transactions amounts of the customers based in Africa. And of course, this applies to the customers from all of the regions. And now to model the relationship between customers and transactions, we head over to the model view. Now this is the first time in this entire journey where we will actually perform operations in this model view. So let's quickly summarize what exactly this model view is about. So in short, this allows us to view the contents of each of the tables which we have imported into Power BI Desktop. We can also get a glimpse into the types of data in each table, and then we can also crucially define the relationships between these tables. So in this particular view, two of the three tables, Prodcat Info and Transactions, are visible, and in each of them, we can see the capital sigma sign next to each of the numerical columns, which can be summarized, giving us a hint as to the types corresponding to these columns. And then scrolling along, we can also see the customer table. Now in the model view, the fact that there is no line between transactions and customer points to the fact that there is no relationship between these two tables. So to establish the relationship, well, we will need to map the customer underscore ID field inside customer to cust underscore ID in transactions. Before we do this, I'll just switch over the positions of customers and transactions, and you can do this by dragging the tables along by the headers. And then, well, to show that each customer has a customer ID which maps to a cust ID in transactions, we can just click on customer underscore ID, drag it over, and then drop it on cust underscore ID in transactions. And with this done, well, the relationship between customer and transactions has been established. So there is now a line connecting these two tables, and significantly, the cardinality of the relationship is also available in this view. On the side of the customer table, this little box at the end of the line points to 1, and then there is a star or an asterisk on the side of the transactions. So this points to the fact that one customer maps to multiple transactions. So the relationship is one to many. Furthermore, in the middle of this line, you'll observe that there is a little button, which is similar to a menu button. And this is something which allows us to edit the relationship. So I'm just going to double click on this particular button. And this pops up a new dialog and allows us to edit the nature of the relationship between transactions and customer. So let's take a look at how exactly this relationship is defined. So when it comes to any relationship, you need two different tables. So the first table in this case has been marked as transactions, and it is possible for us to switch the table from the drop-down menu. However, you get a little glimpse into the transactions table right below that. And then the next table in the relationship is customer. This is also something which can be modified by selecting a different table from the drop-down. And then there is a preview of the customer table itself. Now for each of the tables in this relationship, we can scroll along and view each of the different columns. And this is important because in this view, we can select which of the columns the relationship is based on. So from each of the tables, we can select the columns which are common to the tables. So you will notice that cust_id in transactions as well as customer_id in customer are both highlighted, pointing to the fact that it is these columns which map to one another. So with the tables as well as the columns selected here, we have decided which two tables are related to one another and based on what columns. And then we can define the nature of the relationship by setting the cardinality. This has been set to many to one. So many transactions map to one customer, which is of course just a different way of saying that one customer maps to many transactions. Expanding this menu, you can see the different types of cardinalities which can be applied. So we can also set the cardinality to one, one to many, which would mean that one transaction maps to many customers. And then a many to many cardinality is also possible. Of course, the correct nature of this relationship is many to one. So let's just leave it at that. And then we move on to the cross filter direction. This is something we will explore in more depth a little later on. But at least for now, here is a quick summary. When this is set to a value of single, this means that one of the tables in the relationship can be used to filter the contents of the other table. In our case, the one side of the relationship, that is the customers table, can be used to filter the contents of the transactions table. This can be very useful when performing an aggregation. For example, calculating the sum of transactions for each region. And of course, that is precisely what we need to accomplish. So you'll observe that the two options available here are single and both. And we will check out the difference between these a little later. But for now, let's leave the configurations as is and make sure that the box marking this relationship as active is checked. So you'll notice that we haven't really changed anything in this edit relationship form, given that the default configurations are exactly what we need. However, now that we know how we can edit this, let's click out of this particular view by hitting OK. And now that we have established a one-to-many relationship between customers and transactions, Power BI knows that customers, and significantly also their regions, will need to map to specific transactions. That is, transactions will need to be filtered based on the customer, and not every customer maps to every transaction, and not every region maps to every transaction. So when we head back over to the report view, well, our table looks a lot more sensible. Having established the relationship between customers and transactions as one-to-many, each customer is only mapped to their own transactions. And since each customer has a specific region, each region also maps to a specific set of transactions. So now we can see that the total volume of transactions recorded in Africa was about 3.3 million and about 3.4 million in Central Asia. Now that we have successfully established the relationship between the customer and transactions table, we can now perform operations which combine the contents of these two tables. In fact, in the previous video, we ended things by generating this table, which is in fact a visualization based on the contents of two related tables. And now we will see that we can define DAX formulas which reference two related tables. Before we get to that, however, I'll draw our attention to the table which we already have. So we have now aggregated the total amounts in the transactions table based on the mapped regions in the customer table. However, the total amounts are not quite easy to discern given that there is no formatting which has been applied here. More precisely, there are no commas separating the numbers, so it is harder for us to figure out whether the values are in the thousands, in the hundreds of thousands, or in the millions. So we need to apply some formatting to this total amount column, which is a calculated column obtained by multiplying the quantity and the rate columns. So in this case, we can just head over to the formatting options under column tools and then click on this comma. This will apply the separators to the numbers, making things much easier to read. In fact, in the total row right below, it's now abundantly clear that this number is 54 million. Alright then, before we apply a DAX formula, which makes use of column references to multiple tables, let's just close out of this formula view and focus now on the total sales amount from the region of Canada. So this is a value which is $314,839, and let's just say this represents a value in US dollars. Now, what if we wanted this value to be expressed in Canadian dollars instead? Well, for that, we will need a way to extract this value and then multiply it by an exchange rate. Of course, we will need to reference the region column from the customer table and then sum up the corresponding total amounts from the transactions table, which is of course precisely what this table visualization has done. But now let's see how we can do this. We will create a new measure based on a DAX formula. For this, you can navigate over from the menu over to the new measure option. As for the name of this new measure, well, since this represents the total sales in terms of Canadian dollars from the region of Canada, we call this Canada sales in CAD. As for the formula to be applied for this, well, what we really need is this value of 314,839 so that we can multiply it by the exchange rate. For that, however, we can filter the contents of the transaction table based on the regions they map to in the customer table. So we need to filter transactions based on region and then sum up the Canadian transactions. And in DAX, when you hear the terms filter and an operation like sum, you must think of the calculate function, which of course allows us to perform calculations within a filter context. Now, I have mentioned before in this learning path that calculate is important from the point of view of the DA-100 certification, especially when it comes to performing operations on filtered data. So let's see how this works for our requirements. So once we select the calculate function, you know that this involves the evaluation of an expression based on one or more filters. The expression in our case will be to sum up the total amount column in transactions. So we apply that in here, but this will give us the value in US dollars. To convert it to Canadian dollars, we simply multiply this by the prevailing exchange rate, which at the time of this recording is about $1.25. So with this argument supplied, we have defined what calculation we would like to be performed, but without a filter context, this will apply to the entire transactions table. So it will be the total amount of a little over 54 million, which will be multiplied by the exchange rate. But to make sure that this only applies to the Canada transactions, well, we can apply this filter, where we only filter through those transactions which map to the customer region of Canada. So while we have used the calculate function before, let's quickly consider what is new in this case. So when it comes to defining the filters, we are referencing the customer table and more precisely the region column in that table. However, as far as the operation to be performed, we are summing up numbers from the transactions table. So we are effectively applying the filter on one table and then performing an operation on another. And the reason this will return to us the correct value is because we have related the two tables to one another. Now I'm just going to hit enter so that this new measure is created. And to see where exactly this is available, well, I'll just scroll along in the fields menu over to the customer table. And this is where the Canada sales in CAD measure shows up. Before we proceed, however, I'd like to draw your attention to our use of filters in the calculate function. Now in a lot of sources online with regards to Power BI and DAX, you may come across the use of the calculate function in this form, where the second argument, or in fact any of the filter arguments to calculate, are defined using a filter function, just as I have highlighted in green here. Now keep in mind that this will work in terms of giving you the same result. However, it is highly recommended to use a Boolean expression as the filter argument, much as we have over here with the Boolean expression customer region is equal to Canada. The rationale behind this is explained in depth within this page in the Power BI documentation. However, to summarize it in just a few words, well, using Boolean expressions as we have improves performance, with the added benefit that it makes the formula a little easier to read given that there are fewer characters. Alright then, now that we have this DAX measure, in order to calculate the total Canadian sales in terms of Canadian dollars, in order to view what this number is, let's go through the usual steps of clicking on the report, adding in a new card visualization, and then dragging along over to it the Canadian sales in Canadian dollars. And this is the number we end up with. And this is a number which is correct. We can just use a calculator that the number in this card visualization is exactly 1.25 times the number represented in the table corresponding to Canadian sales. So we have now successfully created a DAX measure using the calculate function, which references the data from two different tables. With that said, let's take a look at our new DAX measure once again. So when we have used the calculate function here, we have just defined a single filter. So this is where only those customers where the region is equal to Canada will be included. However, it is possible for us to use multiple filters here. And the filters themselves can span any of the tables which are related to one another. So for this calculation, we are summing up all of the sales from the region of Canada. But let's just say, rather than summing up all of the Canadian sales, what if we only wanted to see the sum of amounts for all of the high-value Canadian transactions in our dataset? Well, for that, we will require a little change in this measure. First of all, let's go ahead and edit the name and call this high-value Canadian transactions in CAD. So we already have a filter in place for the Canadian transactions part, but we will next include a second filter to only include the high-value transactions. Given that this is going to make this formula a little more complex, we can just add a new line in here. So I'm just going to place the filter definition on a new line by placing the cursor right before it and then hitting Shift Enter on the keyboard. This will move this filter definition over to the next line, and I'll just use the space bar a few times to point to the fact that this filter belongs to the calculate function. Again, note that all of this is merely formatting. It does not really affect the function itself in terms of what it returns, but makes things much easier to read. Alright then, let's now add in the second filter definition to point to high value transactions. This time, let's just say what represents high value is where the total amount of a transaction is greater than 5,000 US dollars. The US dollar amount is available in the total amount column of the transactions table. So we have now applied two different filters. And of course, the way the calculate function works is that by default, the filters will be applied using the AND operation. So the way the calculate function works is it will first apply the filters which we have defined. So it will filter through those customers from the region of Canada, then the transactions where the total amount is greater than 5,000, and then combine the two so that we're left with high value transactions from Canadian customers, and only then will the sum operation be performed and then the multiplication by the exchange rate. Alright then, let's now view the sum of the high value transactions from Canada by hitting enter, and the number in the visualization automatically gets updated. So to view it in full, I'll just close out of the formula view, and we can see that this number is a little over 100,000 in terms of Canadian dollars. So we have now seen that when we are able to define a relationship between two different tables, our DAX formulas can get a lot more complex, and we are also able to perform more complex calculations. And tying all of this to our big picture of analyzing the data correctly and gaining useful insights, well, you can just imagine that the scope here is nearly limitless. Previously in this learning path, in the video Creating Filtered Tables, we have covered the use of the calculate table function. Now this is quite similar to the calculate function which you can see on the screen in front of you, in that there are filters which you can define. However, while calculate returns a single scalar value, in the case of calculate table, what is returned is a table. Now to understand both calculate table as well as the calculate function in a little more depth, let's look at the filters which have been applied in this calculate function. So there are two different conditions here. The first of these points to the customer table and its region column, and we only filter through those customers where the region is Canada. And then we also only filter through those transactions where the total amount is greater than $5,000. Under the hood, what really goes on is that something like a table is created containing only those transactions corresponding to these filters applied. Then the total amount in those transactions are summed up and then multiplied by 1.25 in order to return a single value. Now, however, let's create a new table using these two filter conditions and see what it looks like. Well, for that, let's first head over to the data view and then choose the option to create a new table. Based on our filtering conditions, of course, the table will only contain high-value Canadian transactions, so we can give this table a name conveying exactly that. And then to create the table, well, we make use of the calculate table function. So the arguments which we need to supply need to start with the table from which the rows will be sourced and then filters applied. So if we want a table containing just the transactions, well, let's start off with the full transactions table. And then we can define the filters. Again, don't make use of the filter function, but just make use of Boolean expressions which represent filtering conditions. So the first filter condition, of course, needs to point to the fact that the region of the mapped customer should be Canada. So once we make that selection, well, given that there is now a relationship between customer and transaction, only those transactions representing Canadian customers will be selected. And then for the next argument, we can supply a second filter condition. This is also a Boolean expression, and here we just point to the total amount column being greater than 5,000. The total amount, of course, is part of the transactions table. Then when we hit enter, well, this represents the high value Canadian transactions. So you can see that there are just a handful of rows in here, 14 to be precise. And these are the rows from the transactions table, which were used in order to compute the total sales amount in Canadian dollars in the measure which we created in the previous video. So this gives you an idea of how filtering conditions can be applied to a table and how the calculate table function works with such filters. And now you also have an idea of how the calculate function under the hood works with such a filtered table by performing some kind of aggregation and then returning a single value. Furthermore, you will notice from the discounted amount, total amount groups, as well as store category columns that when using the calculate table function, even the calculated columns from the original table will be retained. Also, for a sanity check, you can sum up these total amounts and multiply by 1.25, and this will give you just a little over 100,000 in transaction revenue. One difference between creating such a table under the hood in a calculate function and explicitly generating a table in this manner is the fact that this table is now available within Power BI Desktop for us to work with. Furthermore, you will notice that this icon right next to our calculated table is a little different from each of the other tables. So it does include a little calculator symbol pointing to the fact that this is a calculated table. Furthermore, by hovering over this, we can also clearly see that the storage mode corresponding to this table is import. So it is entirely based in memory. This corresponds to the storage mode of the table from which each of these rows have been sourced, namely the transactions table. Previously in this learning path, we have covered the fact that when we define a relationship between two tables within Power BI Desktop, it is possible for us to create visualizations which allow us to perform aggregations on the data in one of the tables based on related data in another table. In our table visualization on the left, we saw that it is possible for us to aggregate the total amounts from the transactions table based on the regions in the related customer table. And then we also calculated this value of just over 100,000 using the calculate function, which spanned both the transactions and the customer tables. An important factor in this is the use of the filter context, which allows us to define filters on the original data and then perform operations on the filtered data. Such filters, however, are not just applied in DAX formulas, they can be applied within visualizations themselves. And this is what we will now explore before moving on to see how some of those filters can be ignored. Well, for that, let's first delete this card visualization. So I'll choose remove from this menu option. So once this is gone, let's clean out the remainder of this report and get rid of this table visualization as well. Again, we expand the menu and then choose the option to remove. So now that we have a clean slate to work with, I'll first go ahead and expand the transactions table. And then from the visualizations pane, we'll choose the option of a table visualization. I'll just expand it first and then move along the store type field over to this visual. So this makes up one column of the table. And then to view the total sales amount corresponding to each store type, let's drag that field over as well. So now we have a two-column table. And of course, by default, the text is a little too small, at least on my screen. So to increase the font size, we'll head over to the Format pane, over to the Values menu, and then from text size, we'll choose to increase from the default 10 points to 20. And now things are a lot clearer. So to summarize, a total of about 22 million in sales were recorded at the eShop and almost 11 million from the flagship store and the mail-in brochures and about 10 million from the teleshop. Now, let's assume that each of the total amounts which we see here are the revenues generated from each of these sources. However, what if we wanted to view the profits from them instead? Well, for that, we will assume that there is a standard profit margin for each of the different store types. And then we can visualize what the profit is from each of these store types and also the aggregate profit. Well, for that, let's define a measure which will calculate the profit for us. So of course, we will head over to new measure. And then we will simply call this measure profits. So that's simple enough. And then the profits can be computed using a formula. So in order to apply a profit margin on the gross transaction amount, we will need to apply an expression on the total amount and then a sum operation, for which SUMX is the function which we need. And I'll explain how this works once the entire function has been filled in. This requires a source table as the first argument. So we will sum up the data from the transactions table. And then for the expression, well, we'll just make use of this if statement, or if function to be precise. So I'll just first explain what exactly we need before going into the details of this if function. So let's assume that the profit margin for all eShop transactions is 15% and 10% for each of the other store types. So we need to perform one calculation for eShop transactions and another one for all other store types. So we first check whether the store type is equal to eShop, and then if it is, we multiply the total amount by 0.15. So this is the 15% profit margin. And then if the logic test fails, that is the store type is not eShop, well, we apply a 10% profit margin by multiplying total amount by 0.1. So just to reiterate how the SUMX function works, so this if operation will be applied to each individual row in the transactions table, and then the returned values will all be summed up. And SUMX will return to us a single scalar value, which will point to the profits over all of the transactions. So to view this, let's hit enter so that the profits measure is created. And following that, to view what it returns, we create a card visual and then drag over the profits measure over to it. And this is what has been calculated. From the 54 million in sales, the total profits generated is 6.57 million. This, of course, is based on our entirely made up profit margin. Now, I did mention that the SUMX function will return a single value and calculate the profits over the entire transactions table. However, this is just part of the story. It will in fact calculate the sum of the profits in the current filter context. It is just that there was no filter context which we supplied in the DAX formula for this measure. However, a filter can be applied using visualizations themselves. To demonstrate that, well, let's just say we only wanted to take a look at the data related to the flagship store. So in this case, we would like to focus on the total revenues from the flagship store as displayed in the table visualization, and then also view the profits in the profit card visualization. And these profits should only point to the profits generated from the flagship store. Well, for that, we can just click on the row corresponding to the flagship store in our table. And you will see that that is the one row which gets highlighted, and each of the others have been faded into the background a little bit. But significantly, you'll observe that the profit number has also changed. At 1.09 million, it is clear that this is 10% of the revenues from the flagship store, exactly as our formula defined it. Then when we click on MBR, well, it is that row which is highlighted in the table, and the profits have been adjusted to 1.1 million. So there is some rounding off which goes on here. For the teleshop transactions, we can see the revenues here of 10.4 million, and the 10% profit margin yields 1.04 million in profits. So what exactly is going on here? Well, when we click on, say, teleshop within our visualization table, under the hood, a filter has been applied, and it is only the teleshop transactions which will be considered. And this also affects the other visualizations in the same report page. So our card visualization performs a SUMX calculation. However, it only operates in the filter context set by the report. And this, of course, has been set to just teleshop transactions. In which case, the profits can only be calculated for teleshop transactions and gives us back a value of 1.04 million. Well, let's click back on the flagship store. And this, of course, means that our filter context only points to those transactions. However, if you hold down the control key and then select one of the other rows in this table, for instance, MBR store type transactions, well, our filter has been expanded a little bit. So both the flagship store and MBR transactions are now included in our filter context, and these profits of 2.19 million have been computed over this filter context. Holding down the control key and selecting Teleshop will expand the context a little further to about 32.4 million in sales, which translates to 3.24 million in profits. And then without the control key, if we just click on eShop, the profit number shows us the 15% profit margin. So this is an important demonstration of how the filter context works in Power BI. And we also saw some of the dynamic behavior to the visualizations, where an interaction with one visualization can cause the others in the same report page to change. Now, there will be instances where you don't want the filter context to be applied in certain situations, and there are a few DAX functions which allow us to do precisely that. And starting in the next video, we will explore some of them. Previously in this learning path, we have seen how a filter context can be defined when using the calculate function, and also how one can be applied using visualizations. Next, we will work our way towards defining calculate functions where some operations can be performed by ignoring the filter context. Well, for that, let's start off with a clean slate by first removing this card visualization and then follow it up by removing this table as well. Once that is gone, well, we can create a new table visualization where we will display the aggregate of total sales based on two different factors. So for that, well, let's head over to the customer table and then include the market column. So this is going to be one of the fields or one of the columns in our table visualization. And in this data set, each market or each market segment is broken up into a number of different regions. So let's drag and drop the region into our visual as well. And then for us to view the total revenues, that is, the total value of transactions recorded across each market segment and region, we drag total amount over to this particular visual. So we now have a table with three different columns. And then to improve visibility, well, I'll just go over the steps to increase the text size. So we'll head over to the format pane and then repeat the steps which we have already performed a few times already before. So this is what our table looks like. The headers for each of the columns, however, are still rather tiny. So to increase its size, we can head over to the column header section of the format pane and then adjust the text size property for that as well. So before we proceed, let's try to understand the data in front of us. So in the market column, you can see that there are a handful of different markets, and for each market, there are a few regions. To understand these, let's focus on the EU market. So there are three different occurrences of EU in this table corresponding to the three different regions within that market: Central, North, and South. Similarly, there are four different regions in each of the markets of APAC or Asia Pac, Latin America represented by LATAM, and the United States. Furthermore, you will notice that there are three different markets: EU, LATAM, and the US, each of which have their own central region. In fact, all three of these also have a south region, while EU and LATAM have a north region as well. This is why, for this particular data set, only performing aggregations based on region will not be very helpful. And in fact, even the aggregations we performed previously on the regions combine the sales from the central regions of EU, LATAM, as well as the United States into a single value. However, from here, it is clear to us that each of these regions needs to be treated separately and in the context of the market. Alright then, so we now have a better understanding of the data in front of us. But now, let's move on and make use of the calculate function in order to compute the total quantity of sales in the European region. So for that, let's select the transactions table and then choose the option to create a new measure. And we will call this measure sales in EU. for which we will make use of calculate. As for the expression, well, we will sum up the contents of the total amount column in the transactions table. And to only work with EU data, well, we reference the market column in customer and make sure that it is EU. So, to get an idea of what exactly this number should be, we can take a look at the 3 rows in our table corresponding to the EU market. So, adding the 7.88 million and then the two values of 2.698 million, this sales in EU measure should return us a value of a little over 13 million. So once we hit enter and confirm that sales in EU has been created, let's go through the steps of clicking on the report, adding a new card visual, and then placing sales in EU to it. And sure enough, the value here is 13 million. So far, so good then. Now, consider the case where we would like to view not the raw sales number for the European Union, but its proportion in the total sales. That would be 13 million divided by the shade over 54 million of the total revenues. So this should give us a value a little under a quarter of the total sales. So it should be a little less than 0.25. Now, let's see what kind of DAX formula can be used for this. And here, rather than creating a new measure, let's just modify the sales in EU one and call this proportion of sales in EU. And then consider what our next step should be. So we already have 13 million, which is returned by this calculate function. And then we can divide it by the sum of the transaction total amounts. However, what if we wanted the calculate function itself to return the proportion of EU sales? We will need some way of getting this 54 million number within the calculate function. Clearly, when we apply the sum function on the transactions total amount, it only works within the filter context of the customer's market being equal to EU. What we really need is to use a sum operation which can ignore this filter which we have defined. So within Power BI's DAX, there are a handful of functions which can be used within a filter context in order to ignore the filter context. And one of these is the all function. So let's now divide this sum calculation on the total amount, and keep in mind that this sum function works within the filter context. So this will become the dividend of our operation, and the divisor, well, for this we make use of the SUMX function. We will use this in order to compute the sum over all of the rows in the transactions table, regardless of the filter context. And for that, well, the first argument which we pass to the SUMX function will be a table which disregards the filter context, for which we make use of the all function. Let's just select this first, and the argument here is the name of a table or a column, and if we supply a table name, this can be followed with the names of columns within that table. So I'll just supply the name of a table which is transactions, and then for the second argument will point to the total amount column in that same table. And we'll then round out this SUMX by closing the parentheses, and then make sure that there is a comma before the filters are applied. And this is the new measure. Just to quickly summarize, we have already seen that the filter context in the calculate function will ensure that only EU transactions will be considered when applying the sum operation on the total amount for transactions. This will of course give us back the value of 13 million, which we have already seen before. However, we now make use of this SUMX function in order to calculate the total transaction amounts across all the rows in the transactions table, regardless of filter context. In essence, this SUMX operation should return the value of 54.59 million, which we can see in the total row of the table visualization. So 13 million divided by 54.59 million should give us something less than 0.25. However, this will not quite work with the data in the current form, and we can demonstrate this by hitting enter. And our card visualization is automatically updated and the value which it projects is 0. So why exactly is this the case? Well, when it comes to the total amount column, you will recollect that this is in fact a calculated column. We had created it in the video defining a calculated column in the first course of this learning path. When it comes to the all function, well, it does not quite work as expected when working on calculated columns, so we will need to make a few modifications and in fact load a different data set. I have just demonstrated this here for you to know that working with calculated columns can pose some hurdles when it comes to the all function and other functions where filters are ignored. But now to properly demonstrate the all function, well, let's clean things up in this particular view. Firstly, by heading to this measure, expanding the options, and then choosing to delete it. I'll just confirm the removal. And following that, let's go ahead and get rid of this visual as well. And before we move on, let's make one more change, and this will be to our table. So let's just select it and remove the total amount, which of course is based on a calculated column. And now we're ready to load new transaction data where there is already a total amount column containing the total value of the transactions. And then we will redefine the formula to compute the proportion of sales in the European Union. In the previous video, we saw that when using a filter function such as the all function, we run into problems when it comes to working with calculated columns in our tables. However, to demonstrate the power of the all function, well, let's reload a new transactions table from a different dataset, one where the total amount has already been computed. And for this, well, let's head over to the Excel workbook shortcut in order to load the dataset from an Excel file. And then we'll navigate over on the file system to this retail_data dataset. So this is also included as part of your course materials. And as a quick reminder, this is where you can download the data from kaggle.com. In fact, what we were using before was the modified dataset, and now we will be using the original data. Once we choose to open, well, you can see that there are 3 different tables in here corresponding to the 3 different worksheets. However, it is transaction_details which we will now use. Scrolling along to the right, you can see that beyond the quantity and rate columns which are present in the original table which we loaded into Power BI Desktop, this one contains 2 additional columns, tax and total_amount. So the tax has been computed on each of the transactions, and the total amount in this case is calculated using a slightly different formula than what we had before. So it is now quantity times rate plus tax. So keep in mind that when we perform any summarizations of the total_amount column, it is going to be a little different from the total amounts we have been working with so far, given that the tax is now considered. Alright then, let's load this data into our Power BI desktop, and to do so using the default options, let's just hit load directly. And in a few moments, transaction_details now appears alongside transactions within fields. Expanding it, we can see that each of the transaction columns, including tax and total_amount, now show up here. Now, of course, this new transaction_details table has not been related to the customer table. However, it does contain the cust_id column, just as the previous transaction table we have been working with. So this is one which can be combined with customer, but we will define that relationship just a little later. First, however, let's drag and drop total_amount into our table visual. And in a few moments, well, we see that the total transaction amount now is a little over $60 million. This is of course higher due to the tax calculation which now features. Furthermore, without any relationship defined between transaction_details and customer, each of the total amounts for every market and region combination shows up as $60 million. To get the right values, well, we will need to map each transaction in transaction underscore details to their corresponding customers. And sure enough, for that, we head over to the model view. Scrolling along, I'll just move things over a little bit. And now we have transactions, customer and transaction details. And to map customer underscore ID from customer to cust underscore ID in transaction details, we'll repeat what we did before by dragging customer underscore ID and then dropping it on cust underscore ID. And with that done, well, soon enough, a one-to-many relationship has been created between customer and transaction underscore details. Of course, this is similar to the relationship between customer and transactions. And of course, if you were working with real data, having duplicate transaction details is not quite good practice. And it is best to remove one of the transaction tables altogether from the view. However, for now, to demonstrate the use of the all function, let's stick with both of these transactions and see if it has any effect on the output generated. When we head over to the report view now, well, we can confirm that the total underscore amounts do seem a lot more sensible now, which means that we can go back to focusing on the sales in the Europe market. Now, when you sum up the sales from the three different regions, we should get a value of about $14.6 million, assuming, of course, the total amount is expressed in US dollars. Now, let's create a new measure to convey the sales in the European Union. So we head over to the new measure option, and the name of this measure is sales in EU. And for this, we will use the same formula which we did previously. So we use calculate, apply the sum function on the total amount column in the transaction underscore details table and not transactions. So this is how the formula is a little different from what we used previously. As for the filter, well, we will focus on the customers in the EU market. So we set market is equal to EU. So we now have this sales in EU measure once again. And to view its value, we'll of course create a new card visualization and then drop sales in EU. Sure enough, the aggregate sales in this market is 14.67 million. And when we look at it as a proportion of the total sales of just over 60 million, well, we can roughly compute that the proportion should be about a quarter, just a shade under that, in fact. And now it's time to see whether we can perform this calculation using the same formula we used previously. So I'll just rename this measure proportion of sales in EU, and then retaining pretty much all of the existing code, we'll just make sure that when applying the calculation, the syntax is correct. So after the sum calculation, we'll just add in a divide sign, and then the divisor in this case will make use of the SUMX function, and the argument which we pass along will be a table which contains all of the rows in the transaction underscore details table and not just the one within the filter context. So we use all, and then I've just filled in the remainder of this formula. So let's now once again focus on the SUMX portion of this formula. The first argument here refers to all of the transactions in transaction underscore details, ignoring the filter context which we have applied in the calculate function. So market is equal to EU will not apply to the SUMX thanks to the use of the all function, and then we sum up the total amounts. So the divisor in this operation should give us the value of 60.327 million, which we see in the total row of the table. And now when we hit enter, well, the proportion of sales in the EU has been calculated correctly. So now we get to see the power of the all function. It effectively allows us to ignore the filter context which has been applied in the calculate function. And this can be truly powerful if you want to perform complex calculations within a calculate function. To confirm that this calculation does ignore the use of the filter context, let's modify our filter itself a little bit. So we can add in a second filter to calculate by adding in a region filter. So with these filters, it is only the Central European customers which will be considered when summing up the total amounts when using the sum function, but this will still be divided by the value of 60.327 million thanks to the use of the ALL function. And we can also see that our card visualization has been updated with this new filter. So the proportion of sales in Central Europe is 0.14 or 14% of the total sales. We can also do a quick sanity check here. And if you were to divide the 8.7 million in sales, which you can see in the table, by 60.327 million, we will get back the same value of 0.14. So from the point of view of the DA-100 certification, the use of functions such as all, which allow us to ignore the filter context, is important to understand from a conceptual standpoint, since there may be case studies where you need to perform calculations which involve the use of such functions. Before we move on to the other functions which disregard filters, well, we no longer require the new transaction_details table and can go back to working with the calculated column of total_amount in the original transactions table. So first, let's perform some cleanup by removing this card visualization and then removing any reference to the transaction_details by eliminating total_amount from our table. We follow this up by reverting to the previous total_amount column from the transactions table. So heading over to transactions, let's just drag and drop the calculated column of total_amount, and now we're back to all of the total amounts without any taxes. So in the next video, we will focus on the ALLSELECTED function, which allow us to disregard filters which have been applied at the visualization levels. Previously, we have seen that the ALL function can be used in order to ignore any filter context which has been applied and is especially useful when used inside a calculate function. We have also seen that filters can be applied by visualizations, and we will now explore the use of the ALLSELECTED function in order to ignore filters at the visualization level. For that, consider the table which we have in front of us. So there are three different columns here: market, region, and total amount. Now, before we make use of the ALLSELECTED function, let's dig a little deeper into the context for the total amounts in this table. And for that, we will consider the second row in the table, which points to the sales in the market of Asia Pacific or APAC and the region within that of Central Asia. So the total amount here of 3.4 million points to the sales within the region of Central Asia inside the market of APAC. So it is just the transactions within that context of Central Asia and APAC whose total amounts have been summed up. You can in fact think of this number of 3.4 million as the sum of total sales within the context of Central Asia within Asia Pac. Similarly, as we go further down in this table, looking at the sales in the central region of the market EU, the number 7.88 million refers to the sum of sales within the central region within the context of the EU market. And this central region is different from, say, the central region in LATAM or the US. All in all, each of the values in the total_amount column correspond to the sum of sales within a specific query context. And this query context is determined by the market and region fields. This is important to understand because it is possible for us to ignore this query context using the ALLSELECTED function. Well, to demonstrate that, let's pull in a new type of visualization, which is not so much a visualization as a tool for us to interact with one, and this is a slicer. You should see an icon such as this one with a funnel on it. And rather than explain how it works at first, I urge you to follow along with me and then create this particular utility. So once the slicer is in place, let's populate it with one of the fields. And for this, we head over to the customer table and then select market and drag it into the field section. And with that, all of the distinct values for market should appear within the slicer. Now the text, of course, is rather small, so I'll quickly go adjust the sizes here. Heading over to the Format pane, first we can head over to the slicer headers and then adjust the size here to 20. So we can clearly see that the slicer will be applied on the market field. Next, let's head over from the slicer header over to the items in the slicer and also expand the size. And there you have it. The 7 distinct values of market are now visible in the slicer. You can see that there is a checkbox next to each of them, and this should give you an idea of what exactly slicers are capable of, just in case you haven't used these already. Slicers effectively slice the overall dataset in order to display just specific information. So for example, if you were to select the Africa option here for market, instantly you notice that the table visualization has changed and only shows the data corresponding to the market of Africa. Similarly, if you were to uncheck Africa and then choose the US, well, we have the 4 rows corresponding to the US market. Now, let's consider the case where alongside the sales represented in the total amount column, which point to the revenues from a specific region within a specific market, we also wanted to view the overall sales in the market without regards to the region. That is, we want to sum up the sales across the entire market. In other words, we would like the total amount for the sales represented in the last row of 9 million to appear alongside the total amount for each individual region and market. Effectively, any calculation which gives us that value will need to ignore the region filter which has been applied for the total amount in each row, while retaining the market filter. Well, this is what the ALLSELECTED function allows us to do. And to demonstrate how, well, we will of course create a new measure. So I'll just select transactions first, head over to new measure, and then let's call this measure sales without region filter. And then to calculate this, we use the calculate function. And as you may imagine, the operation we will perform is a sum operation. This will be on the total underscore amount column of the transactions table. And then when specifying the filters for this, well, we will in fact be telling it to ignore filters in the visualization. That is, ignore any query filters. For this, let's make use of ALLSELECTED. And then, since we want any filters applied on the region column to be ignored, this is what we specify as the argument to ALLSELECTED. So let's quickly summarize what exactly this measure computes. In summary, it effectively sums up all of the total amounts by ignoring any filters that have been applied at the query level on the region column. Keep in mind that any filters defined within the calculate function will not be ignored by this. Now to view the effects of this particular measure, and specifically the use of ALLSELECTED, well, let's first select the table itself, and we will now add in a new column which makes use of this newly created measure. And we can do this by simply dragging over sales without region filter over to the value section, and there you have it. There is now a 4th column in the table. However, it does look a little messy. So to clean things up a little bit, we can apply some formatting by first selecting the measure. And then from the menu which pops up for the format, let's click on the comma so that the separators for thousands, millions, and so on show up. And then I'll just expand the view a little bit. And there you have it. We can now see the contents of the sales without region filter in its raw form. Importantly, I'll draw your attention to the last 4 rows of data in here corresponding to the US market. And here we can confirm that in the 4th column, the value which appears for the US and for all 4 regions in the US are exactly the same at about 9 million. And this is precisely what we saw as the aggregate of sales in the US market. Just in case this is not clear, let's select one of the markets here from the slicer. So we have the LATAM market rows displayed, and now we can contrast the third and fourth columns within this table. So each value in the total amount column has been applied within a specific filter as defined by the market and region. And given this is in a visualization, this is a query filter. This filter has been applied based on the fact that the table contains market and region columns. However, in the sales without region filter column, it is only the market query filter which has been applied, and the region filter has been ignored, which is why the total market sales of 9.2 million now appear for each of the rows for the LATAM market. And in the slicer, if we head over to the US market, sure enough, we can see something similar replicated here. At this point, let's experiment a little bit and keep the US market selected in the slicer, and then using the control key, select the LATAM market as well. And the output does give us some interesting information of how the ALLSELECTED function works. So the contents of the sales without region filter column are exactly the same as in the full table and still represent the sales in the market corresponding to the row. This confirms that the selection from the slicer does not really influence this particular column, since the slicer works with the market field, while this fourth column is only set to ignore any filters applied to region. So, clicking on the sales without region filter measure, we now know that ALLSELECTED allows us to ignore any filters applied to a selected field at the query level. In the next video, we will explore the use of the ALLEXCEPT function in order to ignore filters on every field except the given ones. In the previous video, we saw exactly how the ALLSELECTED function works in DAX. This effectively allows us to ignore any query filters which have been applied to the specified field. In our case, we were able to ignore any filters applied to the region column in the customer table when summing up the total transaction amounts. This can all be very useful, of course, but consider the case where you have a very large table with many columns, and rather than simply ignore filters applied to a single column, you would like to ignore all filters except those applied to a single column, effectively the converse of ALLSELECTED. Well, this is the ALLEXCEPT function available in DAX, and we will now explore its use. In fact, we will define such a filter so that it is any filter on the market column which will be retained and all other filters will be ignored. Given that the table we have been working with contains market and region as the two columns which determine the filters which are applied to the total amount calculations, the output should be similar to this particular measure which we have used, where the region filter is ignored. If this all seems a little abstract, just follow along with me and modify this sales without region filter by renaming it to sales with market filter. Remember, we only want any filters applied to the market column to be applied and everything else to be ignored. For the calculate function, we retain the expression where the sum operation is used. As for the filter, let's clear that out, and rather than ALLSELECTED, we replace it with the use of ALLEXCEPT. You'll observe that this is a DAX function which takes in at least two arguments. Here we start off with a table name, so this will apply to a single table within our datasets, and then we can specify multiple columns on which any filters should be ignored. So let's point this to the customer table, which of course contains the market column, and then we point to the market column itself in the second argument. And then, in order for this modification of the measure to take effect, let's just hit enter. I'll just close out of this formula view, and you'll observe that the visualizations are exactly the same as before. And in fact, this is entirely expected. Whereas previously, The fourth column ignored any filters applied to the region column. On this occasion, the exact same behavior is displayed. The filter on region is ignored. It is just how we define this behavior which has changed. Whereas previously, we said that filters on region should be ignored. Now we say that only filters on market should be applied. Of course, these two behaviors are identical only in this particular context. If you were to add other columns over to the table, they will behave differently. So now selecting a newly created, or to be precise, a newly modified measure, well, from the formula which pops up, we are now familiar with how exactly the ALLEXCEPT function works. But now, let us consider the case where we want to ignore filters not on specific columns or apply filters just on specific columns, but we want to ignore all filters altogether. Well, there is a function for that. To put it to use, let's first rename this measure to something a little more descriptive. So this is called sales with no filters. And of course, we will need to get rid of this ALLEXCEPT function, and the function we will now use is simply called REMOVEFILTERS. This is one which takes in no arguments at all because we don't really need to point it to any specific column or columns in plural, since it will simply remove all possible filters, at least at the query level. And here is the result. Clicking out of the formula view, without any query filters, we can see that the fourth column now simply displays the entirety of sales across the entire transactions table without regards to any filters, whether on market or region, or any other combination of columns which could be added here. So when it comes to using Power BI, in order to create meaningful visualizations, well, you may need to perform a lot of filtering and in some cases ignore filters using some of the different functions which we have covered. This course gave you hands-on experience working with the filter context in Power BI, a topic which you need to master to truly become a Power BI expert. This is also a significant factor distinguishing the DAX language from regular programming languages, which clearly marks it as a tool for data analysis. You kick things off with an introduction to the relationships between tables in Power BI. You saw how this is essential when it comes to performing accurate aggregations when data is split across multiple tables. You got a glimpse into how relationships can be defined, and this will set you up for more advanced topics with regards to relationships in Power BI. You then moved on to the use of the calculate function in the DAX language. This is a highly versatile function which serves as a great tool when it comes to operating in a filter context. You saw how a filter context can be defined so that it only points to a subset of the overall data, and that it is possible to perform operations within this filter context. You cover the use of one or more expressions when it comes to creating filters with calculate, and also how a query context is created by visualizations by filtering the data which is displayed. And then you cover a breadth of options when it comes to ignoring the filter context for specific use cases. This included the use of DAX functions such as ALLSELECTED, ALLEXCEPT, and REMOVEFILTERS, and you got to see how each of these enable you to bypass filters, whether they are defined by you within a DAX function or whether they are set by a visualization. Having come to the end of this course, you have the skills required to make the best use of the DAX language when it comes to working in a filter context, and crucially, to ignore this context when the situation requires it. This has prepared you to applying the DAX language in the DA-100 certification exam, and also to defining meaningful and optimized measures which can then be used to build insightful visualizations. However, there is still more to learn when it comes to modeling data in Power BI, and the next course in this path covers another crucial topic in this domain, namely working with time intelligence tools. We will now explore the use of various time-related features available in Power BI. And in this demo, we will focus on creating a date table. Before we proceed, however, you will observe that I have cleaned up the report section on my Power BI desktop and have also done some level of cleanup with regards to the tables. Looking at the Fields menu, you'll observe that the transaction details table, which we had used previously when exploring the use of the all function, is no longer part of our data. I have removed this to avoid any confusion or maybe even conflict with the transactions table we have been working with for most of this learning path. With that out of the way, let's now head over to the data view and see where exactly a date table can be helpful, for which we can focus on the one column in the transactions table which contains a date, specifically the tran_date column. Now keep in mind that before we create a date table, make sure that this column is formatted as a date. In case that was not automatically done when you loaded the dataset, you can change the type of this column either from the data view or by pulling up Power Query. Now to understand why exactly a date table can be useful, well, let's take a closer look at the values in tran_date. You will notice that the first two dates in here are from the year 2013. Row number 3 is from 2012, and then there is a transaction from 2014. Furthermore, we can see the different months where the transactions were recorded, the different dates within the month, and significantly, also the day of the week. All of this is very important information because when analyzing sales data, if the information spans multiple years, we will very likely want a breakdown of transactions over each year. Similarly, we may wish to analyze the total sales recorded in each month, each quarter, or maybe even on specific days of the week. For example, from the transactions on view, there are quite a few which have been recorded on a Sunday, and we may want our analysis to point to whether sales on a Sunday are significantly more than sales on other days of the week. While I have given a rather long explanation here, at the heart of it all is the fact that a date has multiple dimensions, and a date table allows us to represent those dimensions. To see exactly how, let's go ahead and create a new table, and we will need to define this with a formula, and I'll just paste it here. So you can see that this is a formula which spans 9 different lines, and in fact, this will create a new table containing 9 different columns. These will include different dimensions for a date along with different representations of a specific dimension. Of course, I recognize that this all seems rather abstract right now, so let's dive into the details. First of all, the name of this table is date table, and this table is created by defining a number of calculated columns. To do this, we make use of the add columns DAX function, and this will allow us to specify what each of the calculated columns are. The first column is defined on line number 1 of this formula, and for this we make use of the DAX calendar function. This will generate a sequence of contiguous dates based on the given range. So the arguments point to the lower bound of the date range as well as the upper bound. So for the lower bound, we make use of the DAX minx function in order to get the minimum value for the transaction date. When using this function, the first argument is the table over which the minimum needs to be calculated, and then the column in that table from which the minimum value will be extracted. Of course, in our case, we need to point to the tran_date column in transactions. And then for the upper bound of our range of dates, we make use of the maxx function. As you may expect, the workings here are similar to minx, except it returns the maximum value from the specified column, which is of course tran_date in transactions. So note that the calendar function here returns a single column containing the range of dates and will automatically assign a name to this column which is simply called date. In fact, I'm just going to hit enter over here so that you can view the date table which is created, and this will also make it easier for me to explain each of the other columns which we define. So you can see that the first column now contains a date value and has the header of date. So the lowest value of the transaction date is the 1st of July 2012. And note that on my machine, the region has been set to the United States, hence this date format. The next date is the 2nd of July 2012, then the 3rd of July, and so on. So you'll see that the dates here are contiguous. In fact, the calendar function does not really consider whether the corresponding date exists in the transactions table. It will simply generate the sequence of dates based on the minimum and maximum values supplied. Alright then, this concludes column number 1. Let's move on then to column number 2. And this is defined on row number 2 of our date table DAX formula. So you'll notice that there are in fact two arguments here. The first of these is the name of the column or the column header, and we set this here to date as integer. You can also see the effect of this column header setting in the table itself. As for the value in this column, well, this is not exactly an integer as suggested by the header, but in fact a representation using just numerical digits. For this, we make use of the format function where we can format a date value. The first argument here can be the date itself which we want formatted, and then the second argument is the format string. So in this case, in order to have 4 digits representing the year and then 2 each for the month and date, this is the string which we can use. And you can see the results in the table itself. The 1st of July 2012 is represented as 2012-07-01. This of course can be a very useful date representation, especially if you'd like to sort the contents based on the year, month, and date in that order. Let's move along then to column number 3. This has a header of year, and this simply displays the year corresponding to the date. And to get this, we can simply make use of the year DAX function. The argument here is the date itself, and you can see that this simply returns the year of the date. Similarly, in column number 4, we display the month corresponding to the date by using the month function, and the column header is set to month. And in each of the rows in our date table, which are visible right now, we can see that it is the numeric form of the month of July, which is rendered. And then come two different representations of month using strings. So you'll know that months can be represented as a 3-character string or one involving multiple characters. On line number 5 of this formula, we define a column called month text short, which renders the month as a 3-character string. For this, we once again make use of the format function where we pass along the date, and then the formatting string is simply 3 lowercase m's. And you can see the effect of that formatting in the data table itself. July is simply represented as JUL. Next comes a column with the header month text long, and this will represent the full string itself corresponding to a month. So in this case, when we call the format function, we pass along a formatting string of 4 lowercase m's. However, this does not mean that the month will be represented using just 4 characters, and we will soon confirm that by scrolling further along in the date table. Next, we move on to column number 7, which represents the day of the month as a number, and for this we simply invoke the day function on the date, and the numbers themselves are visible in the table. Then for the day of the week, well, to represent this in the form of a number, we can make use of the weekday function. So in this case, the number 1 corresponds to a Sunday, as the 1st of July 2012 does, and then the number 7 maps to a Saturday. And then we can view which quarter of the year the specific date falls under. For that, we make use of the quarter function. This is again applied to the date column, and it returns a numeric value, but to render the quarter value as a string starting with an uppercase Q and then followed by the quarter number, we concatenate two values. Here the string uppercase Q is concatenated using the ampersand symbol, which is the concatenate operator in DAX, and this is followed by the number corresponding to the quarter returned by the quarter function. And in the date table itself, we can see that each of these July dates have been categorized as Q3. When we expand the date table here, you will notice that each of the numeric fields now have the uppercase sigma sign next to them, such as day of month, month, and year. And beyond that, the date field within the date table can also be expanded. We will get to that a little later when we cover date hierarchies. For now, however, let's minimize the formula pane and then take a look at the table itself. Scrolling along, we can confirm from the month text long column that the text February is represented in full for the corresponding month. So specifying a format string of 4 lowercase m's in the format function does render the full month. And importantly, each February date is marked as belonging to Q1. Next, let's focus on how exactly the date values in the date column are rendered. By default, you can see the formatting which has been applied, so it includes a date and timestamp. However, given that this only points to a date and all of the times have been marked as midnight automatically, let's make use of a more concise and more easy to read representation. So expanding this menu, I'll just head over and make use of this format. And we now have a modified date table and a date column. So now that we have successfully created a date table, in the next video, we will focus on working with this. It's now time for us to work with the date table which we created in the previous video. And while doing so, we will explore the topic of date hierarchies. Well, for the hierarchies, consider the fact that the date column in this newly created date table can be split up into various dimensions as we have done so already within this table. For example, each date includes a year, month, day, and can also be cast into one of the 4 quarters in a year. And Power BI is well aware that we may need to break up a date into such categories, which is why when you take a look at the date column of the date table under the Fields menu, not only does it have a calendar icon next to it, pointing out that this is a date, but it does have this sign conveying that it is a menu which can be expanded. And when we do that, well, you can see that there is a date hierarchy which is present here. This is what Power BI does automatically with many date fields, assuming that we may want to break it up into various dimensions. And to see how exactly a date can be broken down, let's just expand the hierarchy itself. And there you have it. For each date, we have a numeric year, a quarter, a numeric month, and a day. So you'll see that while it is possible for us to explicitly break up a date into a number of different dimensions as we have in the date table, Power BI also does a lot of this work automatically. Keep in mind that this may not always happen for every table which you consider a date, and you may need to explicitly set the type for the column. So now that we know a date hierarchy has been created for the date column, well, the question is, how exactly can we put it to use? Well, of course, the main table which we have loaded into Power BI so far is the transactions table, which is our fact table, and everything around it is simply a dimension table. Customer represents each customer in multiple dimensions. Prodcat info conveys details about the categories and subcategories of the different products which have been transacted. And in fact, even the date table contains various dimensions for the transaction dates. Also, when we scroll along and check out the fields within the transactions table, there is tran_date, which has been marked as a date as implied by the calendar icon next to it, and this can also be expanded. You can go ahead and confirm that this is also something which can be represented as a date hierarchy. In any case, let's pull up the transactions table, and the values which we have been summing up so far in this learning path from the transactions table has been the total amount column, which of course is a calculated column. However, it is possible for us to use a measure in order to achieve the same results as aggregating total amounts. And for that, let's just go ahead and create a new measure. Once the name has to be set, let's just call this total amount measure, and its value can be computed by multiplying the quantity and rate columns just as we have done in the calculated column. But we do this now with the SUMX function. So we point to the transactions table and then multiply quantity and rate for each row in the transactions table. Now when we create such a measure, you may think that it operates in much the same way as total underscore amount, since it will give us the aggregate sales based on the current filter context, as we have already seen with a few visualizations. However, there is a subtle difference between how calculated columns and measures work. First of all, calculated columns will be loaded into memory, while measures will be computed on the fly. This does mean that measures can be quickly recalculated when the context changes. However, this does come at a cost of performance. In any case, for now, let's just go ahead and create this total amount measure by hitting enter. And once this is in place within the transactions table, and you can confirm this from the fields menu, we can also scroll along and confirm that there is no separate column for the measure, which of course makes sense because our measure is meant to return a single aggregated value. Alright then, it's now time for us to use our date table in a visualization, for which we head over to the report view, and then let's add in a new table visualization. I'll quickly resize the table so that it makes better use of the available space. And then let's expand the date table and then drag in the date column itself. This of course includes a date hierarchy, which is why once we drag it into values, the entire hierarchy is visible to us. Furthermore, each of the dates now are visible in the table in the visualization, and the date has been broken up into 4 different columns for year, quarter, month, and day. While this is not quite visible on the screen, I will expand it so that the text is a little more clearly visible. Alright then, so now that we have the different date dimensions represented in the table, let's head over to transactions and include the total amount measure which we just created so that we can aggregate the total sales amounts for each date. So this has now been added over to our table visualization. But before increasing the text size, let's just select our newly created measure and then apply some formatting to it so that the thousands and millions separators show up. And following that, well, let's head over to the format pane and then adjust the text size for each of the values. But we start off by heading over to the column headers so that those are more clearly visible, and then quickly adjust the text size, and then repeat the trick for the data by heading into values. So now that the text size has been adjusted, we can clearly see that for each date, the total amount has been calculated as the sum of all total amounts, so about 54.59 million. And this is because the relationship between our newly created date table and the transaction table has not been set. Each date in the date table now maps to every single transaction in transactions, since we have not defined the relationship between transaction date within transactions and the date table. That is what we will focus on next, in which case each of these values in this table should get updated to reflect the value of the transactions on the corresponding date. And while we could head over to the model view in order to set up this relationship, I'll show you a different way by heading over to the data view, and then let's head over to the date table itself and then expand its menu options. Out of the different choices available here, there is one for manage relationships, and when we pull that up, we see the relationships not merely with the date table, but all of the relationships which we have defined with our data so far. So you can see that there is currently a single active relationship between transactions and customer. And this is based on the cust ID and customer ID columns of each of these tables respectively. Then at the bottom, you will observe the available choices at this point. We will now create a new relationship, but there are also choices available to auto-detect relationships based on the current tables imported into Power BI Desktop. We can also edit existing relationships or delete any of the existing ones. Let's proceed to create a new relationship. And then there is this create relationship form which pops up, which is completely empty. The first thing we will do is to pick the first table in the relationship, and the drop-down menu presents us with each of the tables which we have loaded into our PBIX file. So once the date table has been selected, we get a quick preview of the data itself. Next, let's head over and select table number 2. And of course, we want to relate date and transactions. And now that the tables have been picked, it's time for us to choose which of the columns will be used to establish the relationship. And note that the columns selected from each side must be of the same type. In fact, Power BI may automatically pick the columns which it thinks are the related ones. So it has chosen the date column from date table, which is the first column in that table. However, it has also automatically selected transaction ID from transactions. The second choice, of course, is incorrect. So let's just select the tran_date column, which is, of course, what we really want. Furthermore, the cardinality has been set as 1 to many, and this does not need to be changed, since each date in the date table will correspond to multiple transactions in transactions. And we also leave the cross-filter direction as single, so that each date in the date table can be used to filter transactions within the transactions table. Also ensure that the checkbox next to make this relationship active has been checked. And then when we hit OK, well, the Manage Relationships list now shows 2 relationships and they're both active. So at this point, we can close out of this view, and then to check whether this has any effect on our visuals, we head over to the report view, and now the numbers in the 5th column of our table seem a little more accurate. So we can just scroll along and confirm that the numbers here are mostly in the tens of thousands, and in some cases also in the single-digit thousands, reflecting the total sales in a given day. In the previous video, we made use of a date hierarchy and then used it in order to compute the total sales over every single day in our dataset. Looking at the table on view, I'll first draw your attention towards the bottom, where the last dates recorded are February 27th and 28th of 2014. However, you will notice that there are 2 days which are missing in the sequence. There are no sales recorded for the 25th and 26th of February in this dataset. This is something which will come into play a little later, but for now, let's focus on the top row, which points to the 7th of February 2014. We can see that the total amount of sales on that particular day was a little over $64,000. Now consider the case where you would like to compare the total sales on any given day with the total sales 2 days into the future on the same row, or perhaps 7 days later so that you can compare sales on the same day of the week in the following week. Well, one easy way to accomplish this is to make use of the date add function, and to demonstrate that, well, let's pull up the date table, and then within this, let's create a new measure. Now we already have a measure which gives us the total value of sales recorded within a filter context. And now we will create this new measure with the name of date add, and we will set this to compute the total value of sales 2 days forward from the date used by the total amount measure. I recognize that this may seem rather abstract, so let's just go ahead and complete this formula. We will make use of the calculate function here, and the expression in this case will simply be our total amount measure, which you will recall sums up the total value of the transactions, and what is implicit in Power BI is that it'll sum up the values within a filter context. Looking at the table which we have in our report, well, the filter context is determined by the date, which is why the last column returns the total amount for that particular date. With this new date add measure, however, we would like the total amount measure to work in a slightly different filter context than what is set by the visualization. And this is what we will define next. Specifically, we want this filter to point to 2 days forward from the date pointed to by the date table. So in our table visualization, for the row pointing to February 1st, we would like this measure to compute the total value of sales recorded on February 3rd. In this case, the filter can be set using date add, and the first argument which we supply will point to a date column. And to point to a date 2 days forward from here, well, for the number of intervals argument, we can set a value of 2, and then for the interval itself, we can point this to day. And this is our new measure. So it redefines the filter context to point to 2 days forward from the currently referenced date in the date table, and then sums up the total value of the transactions for that particular date using the total amount measure. To see this in action, let's just hit enter, and within the date table, we can confirm that date add is now one of the fields. And now when we drag and drop it over into our table, well, the results are visible. While the date add field is still active though, let me just format it. And then we can examine the output, where I'll draw your attention once again to the row for the sales on February 1st. So on that day itself, the recorded value of transactions was a little over 59,000, but the last column tells us that the sales 2 days forward was just over 27,000. And in fact, we can confirm this number when we take a look at the sales recorded on 3rd February. In fact, for every single row, we can confirm that the last column points to the sales 2 days into the future. And this is how the date add function can move the current context over by a specified interval of dates. To view the results of this, I'll just close out this formula bar first and then scroll along, and it looks like the last column is available for pretty much every single row until we hit the bottom rows. Here you will recall that there were no transactions recorded for the 25th and 26th of February, which is why the total amount measure column is empty on these rows. And correspondingly, the last column for 23rd and 24th February is also empty. Furthermore, the date add column for the last 2 rows is also blank, and this is understandable given that there is no data for 2 days into the future right here. And then, as we scroll all the way to the top, you can see that the total sales recorded for 25th and 26th January never appear in the last column, since these dates don't correspond to 2 days into the future for any of the dates within our table. And in fact, this explains the difference in value for the totals in each of the last 2 columns, since the sales for the 25th and 26th of January are not under consideration when performing the date add calculation. Alright then, let's now head back over to our new date add measure and make a little modification. Let's just change this to point to 1 day into the future, and when we hit enter, well, our table visualization has been updated. I'll just cancel out of the formula view, and we can confirm from the contents of the last 2 columns that date add now does indeed point to the next day. And for a quick sanity check, we can once again scroll all the way down to the bottom, and it's now just the last row which is confirmed to have a blank value due to the modification of our formula. Alright then, let's perform the next operation using date add, for which we head over to that measure. And now, let's just change the number of intervals to 3 days. And then when we hit enter, well, we can confirm, let's say by focusing on 1st Feb once again, that the sales recorded in the last column point to 3 days into the future, specifically to the 4th of Feb. So using DATE-ADD, we now know that we can set the context to some days into the future. However, we can also set the context to a point in the past by specifying a negative value for the interval. So in order to point to the previous day, we set the number of intervals to -1 and leave the interval type as day. And then when we hit enter, again, I'll draw your attention to the 1st of February, where the last column now points to the sales recorded on the 31st of January. And closing out of the formula, well, as you might expect, it is now the DATE-ADD column for the first row, which is currently blank, since there is no value to be computed for the previous day. And then, scrolling all the way down, we can see that DATE-ADD now does have a value for the last row. Next, for a sanity check, let's just pull up DATE-ADD once again. And for the number of intervals, I'm going to set it to -3 so that we point to 3 days into the past. And sure enough, our table has been modified and the first 3 rows are now empty for the DATE-ADD column. And significantly, focusing on January 28th, we can see that the DATE-ADD column now points to the total sales recorded on the 25th of that same month. Alright then, scrolling along, we can now confirm how exactly the DATE-ADD function works when we set an offset based on the number of days. However, note that this is a generic DATE-ADD function and not a day-add function, which means that we can also point to a date which happens to be a specific number of months in the past or the future. So let's pull up our measure once again and then set the interval to 2. However, for the type of interval, we can now select between day, month, quarter, and year. To compare the sales recorded 2 months into the future, we select month as the date unit. And then when we hit enter, well, the table has been modified. So, to check whether this does indeed point to the sales recorded 2 months into the future in the DATE-ADD column, again, let's look at the row pointing to February 1st. So, in the DATE-ADD column, the value which we see is 62,811, and we should expect that the sales recorded on April 1st is exactly the same. To confirm, let's scroll along to the row pointing to the 1st of April 2011, and sure enough, in the total amount measure column, the total sales are 62,811. So we can confirm this by examining any of the other rows within this particular table, and there are a few interesting quirks which we need to be aware of. For that, let's head over and take a look at one of the rows corresponding to the end of December. You'll observe that for the 28th through the 31st of December, the DATE-ADD column has the same value, $42,336. The reason for this is that 2 months on from December, we hit February, which only has 28 days in total, and the DATE-ADD column now points to the sales recorded specifically on the 28th of February. So, if we just scroll along to the 28th of February 2013, we can confirm from the total amount measure column that the recorded sales are in fact 42,336. So when DATE-ADD is used to point to a certain number of months into the past or the future, keep in mind how exactly it computes what a month is. Furthermore, as you might expect as you scroll further towards the bottom of this particular table, the DATE-ADD column for the last 2 months of data are all empty, given that there is no information 2 months into the future for those dates. In the previous video, we made extensive use of the DATE-ADD function in order to modify the context which applies when calculating a measure, specifically the total amount measure which we have also created previously. This allowed us to perform some interesting operations such as view the total sales recorded, certain days or certain months into the past or future with respect to the current context. However, when it comes to analyzing any kind of financial data, as we're looking at sales data in this particular table visualization, a very common time frame over which to aggregate sales numbers is the year to date. This is where we aggregate numbers such as the total value of transactions from the start of the current year until the current date. And as you may have expected, DAX has a function for this. So as things stand in the table, you will notice that I have made a few changes since the end of the previous video. Now the date add measure, which is pointed to by the last column, points to 1 month into the future. And furthermore, the table is also sorted by the date add column in descending order. Next, we will add in a new column to this table, which points to the total sales recorded in the current year to the current date. So let's select the date table first, and then within this we will create our new year-to-date measure. We will give it a name of year-to-date sales, and the calculation which needs to be performed will of course make use of the calculate function. It will sum up the total amount measure which we have created previously, and the filter context in which this will operate will make use of the dates YTD function. In order to calculate the total sales recorded in the year to date, we will need a range of dates within our filter. So this needs to start with the 1st of January for the current year and go all the way to the current date. So there is at least one argument which we need to supply to the dates YTD function, and this is a column where a date range can be obtained. So for this, I will just reference the date column from our date table, and this means that within our filter context, we have all of the dates starting from 1st January of the current year up to the current date. And since the calculate function will operate within this filter context, the total amount measure which is computed will be over those dates. In other words, this will return to us the total sales recorded up to the current date in the current year. So when we hit enter, well, in the fields menu, we can see the YTD sales measure has now been created. And now to put it to use, let's just drag and drop it over into our table. Now, of course, to view the new column, I'll just need to apply some resizing, and then following that, we'll also format this measure. And once that is done, well, the data in this table is not quite in sequential order. However, this does allow us to get an idea of how exactly the YTD calculations have been done. For instance, let's focus on the 4th row which is currently in view, pointing to the 1st of January in 2013. So in the total amount measure column, we can see the total sales recorded on that day is 39,346, and in the YTD sales column, we see the exact same number. Furthermore, when looking at the next smallest value for YTD sales in this particular view, it is a little over $611,000, and this corresponds to the 13th of January 2012. So as you might imagine, the year-to-date sales number are less for January, and then focusing on the higher numbers here, well, the biggest number in YTD sales is a little over 17 million, and this is for the 30th of December 2012. Once again, this is not at all surprising, given that at this point, pretty much the sales of the entire year will be taken into consideration. And scrolling along, we continue seeing this pattern where the low values for YTD sales correspond to January, and then the higher values are towards the end of the year, in either December or November. Alright then, now to focus a little more on the year-to-date sales numbers, let's make a little modification to our table visualization. First, we head over and get rid of the date add measure from this table. And now that we have one column less, let's further simplify this table by expanding the menu for the date hierarchy. And you'll observe that it is possible for us to either configure this as a hierarchy, and in fact, that is the option which is selected now, but alternatively, we can also represent it as a normal date. If we make this selection from multiple dimensions, we have a single date dimension pointing to a specific date. So now our table visualization is a lot less complex. There are just 3 columns in all, one pointing to the date, another pointing to the total volume of sales recorded for a particular date, and then the year-to-date sales number. And this is where we can confirm the behavior of the year-to-date sales. So for the first date in this particular table, well, the year-to-date sales matches the sales for the particular day at 44,305, and then the YTD sales for the next day is the sum of the sales for the 25th and 26th of January. So adding up the 44,000 odd and 56,000 odd for the two dates gives us a total of 100,000. And then for the next day, when we add in the $29,000 of sales for the 27th, we end up with $129,000 worth of sales over the 3 days. And furthermore, we can see that the YTD sales increases for each row. So now that we understand how the year-to-date sales work, we can move on to another measure which calculates the sales in the month to date. So there is a separate DAX function for that. And to show how this works, let's head over to the date table, and within this we can create a new measure. This one we will simply call MTD, and much like our YTD sales measure, this will make use of the calculate function. The expression will once again be our total amount measure. However, the filter context in this case will make use of the dates MTD function. As for the argument to this, well, we simply pass along the current date in the context, which means that the context for this particular calculation will be all of the dates in the current month up to the date in the query context. So if the query context points to the 4th of February 2011, the filter context in this case will start from the 1st of Feb 2011 up to the 4th of February. So when we hit enter, well, our new MTD measure is in place, and now to put it to use. Given that our table visualization has now been simplified, all we need to do is to drag and drop our MTD measure over to the values for it, and I'll just quickly apply some formatting to MTD, and there we have it. Sure enough, for the first row in this table, corresponding to the 25th of Jan 2011, the values in each of the three numeric columns are exactly the same. And then for the 26th of January, well, the year-to-date and month-to-date sales values are identical, of course, and this pretty much goes on for all of the January dates in view. However, it is in February where the month-to-date sales have a reset. This is where it matches the total amount measure column, but not the year-to-date sales. Then we can confirm that the month-to-date sales for the 2nd of February are in fact a sum of the total sales recorded for the 1st and 2nd of Feb. So the sum of almost 60,000 for 1st Feb plus 43,000 in sales for 2nd Feb gives us this number of 103,000 odd. So as we scroll along in this particular table, we can confirm the year-to-date as well as month-to-date sales, and we will see that the month-to-date does reset each time there is a new month, as is the case for the sales recorded on the 1st of December. And then as we scroll further along, specifically to the start of a new year, on the 1st of January, the YTD and MTD values have both been reset. So, in the DA-100 certification exam, there may be a number of different questions with regards to scenarios where potentially you will need to configure a report for some manager who would like to see the total value of sales recorded until the current date in the current year or in the month to date, in which case the dates MTD and dates Y2D functions should be at the top of your mind. In the previous video, we made use of the dates MTD function as well as the dates YTD function in order to set the filter context when performing a calculation. This filter context effectively allowed us to override a query context which pointed to a specific date and then aggregate values for the month to date or year to date. However, as we can see from this MTD measure formula, we make use of the calculate function, which allows us to specify multiple filters which together determine the filter context. In this case, there is just a single filter defined by datesMTD, in which case we may be better off using another function rather than calculate. More specifically, we can make use of the total YTD or total MTD functions. To demonstrate that, let's select the date table, and then within that we create another new measure. And now we'll first explore how the total YTD or total year-to-date sales can be calculated using the total YTD function. Here, you'll observe that we can specify the expression which needs to be evaluated along with the dates and then optionally a filter. As far as the expression is concerned, what we really want is the sum as calculated by the total amount measure. So we can just include that as the first argument. And then for the range of dates, well, we only need to specify our date column from the date table. And Power BI will automatically include all of the dates starting from the 1st of January of that year until the current date. And the current date being the one determined by the query context. So for now, we won't specify any additional filters and then just see how this total YTD function operates with regards to our YTD calculation using the calculate function. So let's just hit enter in order to create this new measure. Next, in order to more easily compare the year-to-date sales values based on our old and new measures, I'll switch the positioning of the MTD and YTD sales columns in the table. So we have YTD sales at the end now. And now we can drag and drop the total YTD measure. I'll just resize the table so that all of the columns are in view and then apply some formatting to this newly added column. And what we see here is that the last two columns are identical. Of course, the last column is calculated using the total YTD function, whereas YTD sales makes use of the calculate function along with the dates YTD function. So if the year-to-date calculation is rather simple, well, you can simply stick with the total YTD function. However, if you need to apply some complex filters, then the calculate function might be a little better. However, this does not mean that no filters can be applied when using total YTD, and we will soon apply such a filter. But first, let's quickly scroll along and confirm that the last two columns are in fact identical for the entire table. So now that we have an idea of the total YTD function, you could also make use of the similar total MTD function in order to aggregate values for the month to date. And there is also a total QTD function to aggregate values for the quarter to date. To get more detailed information on those and other time intelligence functions available in the DAX language, you can head over to this page in the DAX documentation. This course delved into a crucial dimension when it comes to analyzing data, namely time. You got to apply a number of techniques when it comes to modeling data so that time-based analysis is simplified. You started off with a very useful technique when it comes to working with time, namely the creation of a date table. This allowed time to be represented in multiple dimensions such as year, month, quarter, and day, and also allows each dimension to be expressed in different formats. You then explore the use of DAX time intelligence functions to extract all of these values from a date. You also got a glimpse into how dates can be defined as a hierarchy, which can then be applied in visualizations. Next, you used functions such as dateAdd, which allow you to operate on a range of dates which are shifted from the range in the current context by a specified interval. You use this in a calculate function and saw how this enables operations in a different window than the current query context. Finally, you got to use functions which allow you to perform year-to-date and month-to-date computations from the date in the current context. While the current context gives you a snapshot of the data at that point in time, the month-to-date and year-to-date functions allow you to visualize the cumulative effect of data such as sales and profits. Having come to the end of this course, you have hands-on experience working with date and time in Power BI. This is possibly the most essential dimension on which data needs to be analyzed, and you have the skills required to model data with regards to date and time for your own analysis, and also to use time intelligence correctly in the DA-100 certification exam. There is still more you can learn when it comes to data modeling in Power BI though. Coming up next in this path are a variety of advanced topics such as defining complex relationships between tables, setting the right cross-filter direction, defining data hierarchies, and implementing row-level security. While we have successfully defined relationships between tables in Power BI previously in this learning path, that has not really been the primary focus, so we have only worked with basic one-to-many relationships. Now, we will delve into relationships in more details by working with a much more complex set of tables. So you'll observe that my Power BI desktop is up, and I have in fact created a new PBIX file, and from the top you can see that this has been named Create and Model Relationships. Furthermore, this particular report is completely empty. In fact, no data has been loaded, and we will now be working with a new dataset containing many more tables than what we have seen before. To get a glimpse of that data, let me just switch over to the Excel file which contains the data itself. Much like the previous dataset we have been working with, you will notice that this dataset also focuses on sales which have been recorded. So there are 3 different worksheets in this Excel file corresponding to sales recorded in the years 2015, 2016, and 2017. These can serve as the fact tables in our schema, and then all of the other tables will be the dimensions corresponding to those facts. In fact, rather than working with multiple fact tables, we will just be working with the 2017 sales, but more on that later. For now, we'll focus on getting an overall understanding of the data by looking at not just the fact tables, but also the different dimensions. Now, this Excel file has been created by combining the contents of CSV files, which you can download from this location on kaggle.com. However, it may be easier to work with the Excel file, which is part of your course materials. Back to the data then. So the first dimension related to the sales is the territory in which the sale has been recorded. And for that, we have this territory sheet. So you can see that each territory is represented by a continent, country, as well as region. And an important point to note with regards to these 3 different columns is that they follow a hierarchy. The top level in this hierarchy is continent. And in this dataset, there are 3 distinct continents: North America, Europe, and Pacific. Each continent may have 1 or more countries within them. So in the North America continent, we have the United States and Canada. And then within Europe, we have France, Germany, and the United Kingdom. And then the Pacific continent just has a single country, namely Australia. And then within the countries, we can have separate regions. In our dataset, this only applies to the United States, which is broken up into 5 different regions, including Northwest, Northeast, and Central. Now each combination of continent, country, and region corresponds to a territory. And there are a total of 10 territories represented here. Now the reason I'm focusing on the nature of this relationship and the hierarchical relationship between continent, country, and region is because this will play an important role when we model this data as a hierarchy. Alright then, from one of the dimension tables, it's time for us to move along to a fact table. And this is the Sales 2017 worksheet, which will get loaded into Power BI Desktop as a table. So you'll observe in here that all this particular table will contain are dates and numbers. While each order has an order number, you will observe that there are multiple occurrences of a single order number. So this is not the primary key of this table. For instance, the top 3 rows here have the same order number of SO61285. However, the product key corresponding to each of these rows is a little different. Further along, in column G, you will notice that there is an order line item, which points to the fact that each order is broken up into multiple line items. Now, let's quickly glimpse into the possible relationships between the sales fact table and dimension tables around it. So the territories table we have already seen. And this maps to the sales table by means of the territory key column. Each order also maps to a products table by means of a product key, and then to a customers table by means of a customer key. For each order then, we have an order date along with a stock date, though we really won't be using the stock date column, and significantly, there is an order quantity for each product. The price of each product is available in the products table. So in order to compute the value of each transaction, we will need to combine the sales table along with the products table. Alright then, so we now have an idea of what our fact table looks like. We can move along then and take a look at the whole of this fact table, and we see that this contains over 28,000 rows in all. So clearly a lot of data to work with. Next, when we head over to sales 2016, we see that this has much the same format as the 2017 sales, and this is also the case with the 2015 sales. But as I did mention earlier on, we will solely be focused on the 2017 sales for the demos in this learning path. Next, let's take a quick look at the returns table, and for each return, there is a date of the return along with the territory, product, and the quantity of items returned. Now, this will also not be very important from our data analysis standpoint, so let's move on to the products table. As you can imagine, there are several different columns here, including the product key at the very left, which uniquely identifies each product, and we have other details. Significantly, there is a product cost column giving us the cost price of the product, and then a product price, which represents its sale price. So we know that the products table can be directly related to the sales table. However, as we move along to the next table, which is a subcategory table, well, this is something which is related to a product but not to the sales table. So this subcategory table called subcateg will have a one-to-many relationship with products, and products in turn will have a one-to-many relationship with sales. Now, if you look closely at this particular table, specifically the third column, you will notice that each product subcategory maps to a broader product category. In fact, there is also a worksheet for product category, and there are just 4 in total. So, product category has a one-to-many relationship with subcategory. Heading over to the calendar sheet, you can see that this is effectively a date table since all it contains is a sequence of dates. And finally, we have a customers table. So, there are many details corresponding to each customer. Each customer is identified by a customer key. But then we have details about their first and last name, and also their income and education levels. Alright then, let's head back over to the start of the dataset because we're done with the preliminary examination. It's now time for us to head over to Power BI Desktop and then load all of that data from the Excel workbook into the form of Power BI tables. So let's navigate on our file systems over to this particular dataset, and then once we choose Open, well, we have the option to select which of the tables we would like loaded into Power BI Desktop. As you will very well know by now, it is also possible for us to get a preview into the data. So calendar, of course, is a date table. Customers includes all of the customer data, and then we can go on and preview all of the data to make sure that it all looks fine. Here we can preview, for example, that for each product, there is a product SKU along with the name as well as model name. Just as a quick sanity check, I'll just glance over each of the different worksheets over here, including the sales tables, and soon enough, we'll be ready to load the selected tables into Power BI Desktop. So for that, let's apply check marks next to each of the tables which we need, starting with customers and then product category. And in fact, I'm going to check each and every table over here except the sales tables which we don't need. So it is just sales 2017 which we'll be working with. The subcategories as well as the territories tables will be required. You will notice that aside from the 2015 and 2016 sales, we also ignore the calendar table for now. So let's just go on and choose to load the data. When we make this selection rather than choosing transform data, you will know, of course, that we are letting Power BI handle the transformations of the data on its own, and it will also automatically assign any types based on what it finds in each of the columns. Beyond that, however, it will also auto-detect relationships, and that is something we will dig a little deeper into just a little later. So let's just go ahead and load, and I'll fast forward to the point where each of the tables, to be precise, each of the 7 tables which we selected have been successfully loaded into Power BI Desktop, and they can be viewed in this Fields menu. In the previous video, we successfully loaded sales data with regards to a number of different products sold across territories to various customers. So there are 7 different tables which we have loaded in here, and let's now quickly glance into each of them to see how these could be related to one another. Within the customers table, you'll observe that there is a customer key. This is a field which uniquely identifies each customer, and we will soon see that there is a reference to this customer key in the sales table. Next, when we take a look at product category, again there is a product category key and a name for it. Let's move on and take a look at the products table, and this is one more very important table within our data. So you'll observe that the identifier in this case is the product key. Again, make note of the Pascal case adopted here, since there is a reference to the product key within the sales table. Next, let's take a quick look at the returns table, which also has a product key reference. So clearly, the products and returns table can be related to one another via this product key. And then comes the sales table. Of course, there are a lot of important columns here. However, note that the customer key has the exact same name in the sales table as it did in the customers table. The reason I bring this up is because Power BI is smart enough to pick up on this and can automatically configure the relationship between customers and sales using this customer key. The same also applies to the product key column, which is present in sales. So this is the same name as the product key in the products table. So once again, the relationship is one which can be automatically detected by Power BI. And in fact, we will soon see that this relationship has in fact been set already. Furthermore, you'll observe that both the order date and stock date fields now appear as dates, and each of these can be expanded into date hierarchies. Lastly, I draw your attention to the territory key, and this is how the sales table can be linked to a territory. However, note that the name of this column here is territory key, and it is a little different in the territories table, due to which the relationship is not automatically detected and applied. Moving along then to the subcategory, we have already seen that this is related to the product category table. And next, when we head over to territories, we see that the name of the key column here is sales territory key, as opposed to territory key in the sales table. Beyond that, we know that continent, country, and region have a hierarchical relationship with one another. Alright then, I have mentioned that the relationships between the tables have been automatically detected, and to confirm this, let's head over to the model view. And once we head there, well, we can see some of the different tables, but I'm just going to zoom out so that we have a broader view. And once we zoom out just a little bit, you can see that the territories table seems to be on a little bit of an island all on its own and is not related to any of the other tables. Now this is purely because of the mismatch in names between sales territory key in the territories table and territory key in the sales table. Zooming out just a little bit more, we can see that the products table does seem to be at the heart of a lot of relationships. So there are 3 lines extending from products, and you will also notice a one-to-many relationship between products and returns. This is because Power BI has automatically detected the fact that there is a common product key column between these 2 tables. So they not only share the same name, but also the same type, and it has used this fact in order to set up this relationship. Zooming out just a little bit further, you can see that each of the tables is related to at least one other table, except for territories, and this of course we know is because of the slight mismatch in the territory key name. A little later in this course, we will explore the fact that each of these relationships have in fact been defined correctly, and that a lot of operations are now possible because Power BI has automatically detected the relationships. Furthermore, I'd like to point out that it is not quite a star schema which has been followed here, because the sales table, which is our fact table, is not quite at the heart of everything, and dimension tables such as products seem to have further dimensions of their own. So rather than a star schema, this can better be described as a snowflake schema, where data is split across multiple tables, and to use database terminology, each of the tables are normalized. Now all of this is just to highlight the fact that Power BI is capable enough of detecting and then applying relationships between the loaded data automatically. However, there may be many instances where you would like to explicitly set the relationships on your own. Well, if that is the case, you will need to turn off the feature which automatically detects and applies relationships. And for that, we head over to the File menu, over to Options and Settings, and then from there, we expand upon the Power BI options. And here, as you can imagine, there are a number of different settings which can be configured. From the menu on the left, you will observe that the settings themselves can be categorized into global and current file settings. So global, of course, applies to all of Power BI desktop, whereas current file will only apply to the current PBIX file. Within the global settings, you'll observe that it is possible for us to configure details for the Power Query editor, as well as overall security settings and so on. Within the data load settings, however, at the very top, take note of the type detection setting. By default, this has been set to auto-detect the column types and also the headers for the data. This is something you can disable entirely or alternatively enable through file-specific settings. What we are interested in at the moment is the data load settings within the current file so that we don't change any of the global settings, and this is where we will modify whether relationships are detected automatically. And from this view, under the relationship settings, you'll observe that the third option points to auto-detecting new relationships after the data has been loaded. This has been checked by default, and this explains why all of the tables which you have loaded, barring territories of course, has been related to at least one other table. Another setting under relationships is the importing of relationships directly from the data sources. This is something which applies to loading data from relational database tables which are already related to one another at the database level. And further settings over here include time intelligence settings, where the auto detection of date and time values can be turned on or off. If this is enabled, it means that date columns can automatically be detected and date hierarchies can be built out of them. For now, however, let's simply uncheck each of the settings with regards to relationships so that the relationships are not automatically detected. And before we set this by hitting OK, consider that we may want to explicitly define relationships if, for example, the source data has not defined the relationships correctly or not quite in a form which we require for analysis. Alright then, it's time for the disabling of these settings to take effect. So we just hit OK here. And of course, this has not affected the relationships which have already been set. However, if you were to reload each of the tables, they will appear as independent islands. Now, to get to that point where we have a bunch of unrelated tables, let's go ahead and manually delete each of the relationships because this will just be a little quicker. For that, we can just head over to one of these lines relating to tables, right-click and choose the option to delete. And when prompted for a confirmation whether the delete should go ahead, I'll just say yes. I'll just go ahead and delete some of the other relationships as well, and each time will provide a confirmation. I'll now just fast forward until each and every relationship has been removed, and in the end, we're just left with a collection of independent tables. The reason for undoing each of these relationships is because in the next video, we will focus on computing the transaction value for each line item in the sales table by looking up the corresponding price of a product in the products table, and we will do this without using a relationship. I'm now in the data view of my Power BI desktop, and the 7 tables which we have loaded here are all visible under the Fields menu. It is the Sales 2017 table which I have now activated, and this gives us a lot of details around various orders. So for each line item here, we have the product key which points to the product which was sold in a specific order, along with an order quantity column which points to the number of items of that product which was ordered. We have already seen that the order number column here cannot really serve as a primary key because there are multiple occurrences of the same order. Now, however, let's focus on the fact that one very important piece of information is missing from this particular table, specifically the total revenue generated from each line item in this sales table. The revenue is something which can be computed by multiplying the order quantity by the price of the product, but to get the price itself, well, we will need to look into the products table. So how exactly can we do this in the absence of a relationship between sales and products? Well, we can make use of a DAX function called lookup value, which will allow us to look up the product price within products using the product key, which is common to both the sales and products table. So to demonstrate how this works, let's go ahead and create a new calculated column, and we will call this column sale amount. As mentioned, the total sale amount for each line or each row in this table can be obtained by multiplying the order quantity by the price. So let's pull up the order quantity first, and then we multiply by looking up the product price using the lookup value function. Now, if you have ever used the VLOOKUP function in Excel, it should be easy enough for you to understand how exactly lookup value works. But let me just go ahead and make this selection and then explain the inner workings of lookup value. So our goal here is to make use of the product key present in the sales table and then use it to look up the corresponding product price in the products table. So the first argument which we need to supply is a result column name, and this is the column which contains the data which we're looking for. This of course is the product price present in the products table. So once we make that selection, well, next we define exactly where in the products table we will be searching for a product key. So we have the product key here in the products table, and we need to look up the corresponding product key in the product key column of the products table. So this is where we will be conducting the search. Once that selection is made, we can specify exactly what value we will be searching for within the search column. That value, of course, is the product key from the sales table. And once that selection has been made, well, let's just consider exactly what this lookup value function is about to do. Since now I will explain things in the reverse order of the arguments. So for each row within sales table, we will make use of the product key column within sales and then search for the same product key in the product key column of products. Once a matching product key is found, well, on that same row in the products table, we will head over to the product price column and retrieve that product price. So at this point, we will have the price corresponding to a particular product. And let's get back to our calculated column here, because that price will then be used to be multiplied with the order quantity and then compute the total sale amount. So now when we hit enter, well, the calculated column has been filled in. So for each of the rows in the sales table which are visible in this view, we can see that the order quantity is 1. So it is fair to say that the sales amount which we see are exactly the same as the price of each product. And then scrolling further along in this particular table, well, we can see the sales amount which have been computed for each of the rows, including ones where the order quantity is greater than 1. Alright then, once we've taken a look at all of the 29,000 plus rows in this table, well, we are satisfied that the calculations have been performed correctly. And you can do a quick sanity check by simply heading over to products table and confirming the prices of some of the products here. So now that we have the sale amounts, well, we are in a position to perform some aggregations based on them. So that, of course, let's switch over from this data view over to the report view. And now we will create the first visual of this demo by pulling up a new table visualization. So once the table is in place, well, let's consider what exactly we can display in here. To start with, let's just say we would like to see the total sales recorded for different models of products. Well, for that, let's expand the products table and then drag and drop the model name field. So this is now a part of our table visual. And next, we head over to sales and then place the sale amount column, which is of course our calculated column, as column number 2 in our table visual. Alright then, we now have two different columns. However, the text is rather small, so I'm just going to head over to the format pane and then adjust the text size. We'll do this first for the column headers, and this will be set to 16 points, and then we'll head over to the values themselves, and then this is also set to 16 points. And now we get an idea of the different models here, and you can see that most of these apply to bikes. To be precise, to bicycles rather than motorized bikes. As to the sale amounts, however, well, these are clearly all wrong. And in fact, every single sale has been mapped to every single model here due to the lack of a relationship between products and sales. We can confirm that the same number appears for every single row in this table. So now we can decide that it is time to head over to the model view and then set up a relationship. More specifically, we'll set up a relationship between products and sales. So I'll just move the products table over, and the common column between these two is product key. To manually set up the relationship, well, we will need to click on product key in the products table and then drag and drop it over to product key in the sales table. Of course, we have already done something like this before, and at this point, the relationship between these two has been set up. Furthermore, we observe that this has been created as a one-to-many relationship. But to confirm this, and if you would like to edit the relationship at all, we can just click on this particular button between the lines and then choose Properties. And here we can see the nature of the relationship. So we have Sales 2017 on one side, Products on the other side, and it is the product key column, which is common to both, which has also been highlighted. So this is the one which is used to set up the relationship. Given that sales is the first table in this relationship, the cardinality is many to one, means that there are many rows in sales corresponding to each individual product. And then the cross filter direction is set to single. In a one-to-many or many-to-one relationship, it means that the one side of the relationship, in this case products, can be used to filter the contents of the other side, that is sales in this case. In other words, it is possible for us to aggregate the sales corresponding to each product. Keep this in mind as this will become important a little later on in this learning path. So of course, we can take a look at each of the different columns in this table and edit the relationship if we so choose. And we can also set the cardinality. However, everything here seems to be okay. So let's just make sure that this relationship is marked as active and then hit OK. And now when we head back over to the report view, well, the sale amounts do seem to be at least a little more accurate, or at least they don't all have the same value. We can see from a quick glance that it is the Mountain 200, which seem to have very high sales, and this is a mountain bike. So we have now seen how we can make use of the lookup value function in order to look up a value in another table, even without a relationship. But we have seen that in the end, if you wish to perform some aggregations in a visualization, it is best to establish relationships between tables. In the next video, we will once again make use of the auto-detect relationships feature in order to re-establish the relationships between the different tables we have loaded. In the previous video, we saw that in order to get the correct sale amounts corresponding to each model of product, we needed to set up a relationship between the product and sales tables. So now that we have these correct numbers, well, let's head back over to the model, and we can see that we now have a number of different tables which are isolated from one another. This, of course, is because we went ahead and deleted the relationships which were auto-detected and applied by Power BI, and then we only explicitly set up a relationship between sales and products. Next, however, let's go on and reinstate those auto-detected relationships and see whether those are correct and whether any editing is required. For that, let's go ahead and delete this relationship between sales and products, and then we will have this auto-detected later, and then we will need to confirm the delete, of course. And following that, in order to auto-detect the relationships, we simply head to the Manage Relationships option. And this brings up a dialog where we can set up various relationships and also view any existing relationships. Of course, there are no existing relationships at the moment, which is why this is empty. And at the bottom, you'll observe that there are two options here to either create a new relationships or auto detect based on the existing data. Of course, this is the option we will now choose. And in a few moments, you should see that 5 new relationships have been identified. Let's just hit close and then take a look at what each of these 5 relationships are. Right at the very top is one between products and subcategory, which represents subcategories. Then one between returns and products, between sales and customers, also between sales and products. Of course, this is the one which we set up explicitly just moments ago. And finally, between subcategory and category. And then when we close out of this view, we get more information about the nature of these relationships. Once again, I'll draw your attention to the sales 2017 table here, which is our fact table, but it is just related to 2 other tables directly, products and customers. Indirectly, however, it is related to all of the other tables, except for territories where that relationship has not been auto-detected. However, if you leave that out, you can clearly see that this is not quite a classic star schema with the sales table in the middle and related directly to a collection of dimension tables, but instead, this more resembles a snowflake schema, where some of the dimensions have further dimensions of their own. For example, products has further dimensions of subcategories, which in turn has further dimensions of categories. Beyond that, the cardinalities of each of these relationships are also clear from this view. For example, each product category has multiple subcategories, and each subcategory in turn maps to several products. And we have seen that by default, when one-to-many relationships are established, the cross-filter direction is auto-set to single in most cases. Now to see what repercussions that might have, let's now take a look at the relationship between customers and sales. For that, let's click on the little button between the line establishing the relationship and then choose properties. And here, well, we can confirm that the relationship between these two is on the customer key field, which is available in both tables, and that the cardinality is many to one. Significantly, however, the cross-filter direction here is set to single. This means that customers can be used in order to filter for corresponding sales. So we can, for example, aggregate all of the sales records for a given customer. However, the filtering cannot be applied in the other direction. So for example, we cannot search for customers corresponding to specific sales records. In most cases, this is perfectly fine. It is very rare that you will need to look up customers or perform aggregations of customers using sales records, at least when it comes to data analysis. While the reverse, where you look up sales corresponding to customers, is quite likely. However, let's just hit OK to exit this view and see where exactly this relationship falls short. Back in the model view then, let's consider the case where we would like to see how many different customers have made purchases for a specific category or subcategory of products. So in effect, we will need to aggregate customers based on subcategory or category. To keep things simple, let's just focus on subcategories. So how exactly can we aggregate customers by subcategory? Well, for that, let's take a look at how subcategories and customers are related. So subcategory is related to products. Products is related to sales 2017, which in turn is related to customers. While this all seems a little complex, it is important to understand how these relationships are established from both the point of view of the DA-100 certification exam and also if you do wish to use Power BI for complex data analysis. Alright then, now that we know how subcategory and customers are related, let's see how the aggregation can be performed. given that subcategory is related to products by a one-to-many relationship, and we can assume that the cross-filter direction is set to single, it means that products corresponding to subcategories can be identified. This is because it is possible for us to filter products based on subcategories. Similarly, it is possible for us to filter sales based on products, given that this is a one-to-many relationship between products and sales. And at this point, it is possible for us to get all of the sales corresponding to a specific subcategory. However, it is at the next relationship where we run into an obstacle. If you'd like to aggregate customers based on sales, this is not really possible due to the single direction of the cross-filtering. So we can aggregate sales based on customers, but not customers based on sales. If this all seems a little abstract right now, let's see what happens if we do try to aggregate customers for subcategories, for which we head over to the report view. Now we no longer require this table visualization. So from the menu, let's choose to remove it entirely and instead create a new table. Once this has been resized, let me just go ahead to the subcategory table and then drag and drop the subcategory name. So all of the different subcategories now appear within the table. But now to aggregate customers for each subcategory, let's just go ahead to the customers table and then drop along the customer key. In this case, when we expand the menu for customer key, we can take a look at the aggregation which is performed. By default, it is set to not summarize. However, we would like to count the number of customers corresponding to each subcategory. So we opt for count as the aggregation. And when that is done, well, the text is rather small. So I'll just head over to the format pane and then resize both the column header as well as the values in this table visualization. And once that is complete, well, we can see that the count of customer key column has a single value of 18148 for each and every subcategory. So clearly, this is not the correct count of customer keys, and the reason for this is the unidirectional nature of the cross-filtering in the relationship between sales and customers. Before fixing that relationship, however, let's focus on one detail of this visualization, specifically the total row which appears at the bottom. If this is not so helpful, we can always head over in the format pane over to the totals menu, where we can simply adjust this bar in order to turn off the totals. So you can see that the total row no longer appears within our table visualization. Before we move on, I'd like to point out that currently in the subcategory name column, each and every subcategory present within the subcategory table is represented. And this is regardless of any purchases made for that subcategory. The reason I bring this up is later on when we aggregate the customers for each subcategory, not each and every one of these will appear. So keep an eye out, for example, on the pedals subcategory here. Alright then, it's now time for us to fix the same value of 18148 appearing for the count of customers. So we head over back to the model view and then let's click on the relationship between sales and customer and then choose to edit its properties. When we do that, well, everything here can remain exactly as it is, except for the cross-filter direction. Let's just move on and then set this to both. Once this is done, well, let's just hit OK for these changes to take effect. And you will observe that the little button in the line connecting the sales and customers table now points in both directions. So it is now clear that this little arrowhead on this button indicates the direction of cross-filtering. And now we know that cross-filtering can be applied in both directions here. This of course means that it is now possible for us to aggregate customers based on sales, which means that it should be possible for us to aggregate customers for each subcategory as well. So to confirm, let's head back over to the report view, and the numbers in the count of customer key column does seem to make more sense. You will also notice that the number of subcategories visible are less than what we had previously, and this is because we now only include those subcategories here which have corresponding sales and customers. You will recall that earlier on, there was a subcategory with the name of pedals, and this no longer shows up in this table. Now we can also sort this table based on the count of customer key, and this tells us that tires and tubes seem to have the highest number of customers. Though of course this does not mean that they recorded the greatest volume in sales. In the previous video, we successfully applied bidirectional cross-filtering between the sales and customer tables in our datasets. This allowed us to see how many customers there were for each category of products within our catalog. We also saw that when it comes to single directional cross-filtering, while it does work in most cases, there will be instances where it does not help us. So the question you might pose at this point is, why don't we simply set all relationships to have bidirectional cross-filtering? Well, to explain, let me just head over to the model view once again, where we can see the nature of the relationships between each of our different tables. And for now, let's consider the relationship between products and sales. Of course, if you would like to aggregate the sales corresponding to each product in order to learn, for example, which product has sold the most, we only need the ability to filter sales based on products. So single directional cross-filtering is more than enough. But we saw that when we want to aggregate the count of customers for each subcategory, we need to go via the sales table. So it helps if we are able to filter customers based on sales. Even though intuitively, it will seem that the more common use case is for us to be able to aggregate sales based on customers. So we of course fixed our problem by setting the cross-filtering direction to both, as indicated by this arrowhead pointing in both directions. However, this does come at the cost of performance. A best practice is to limit the use of bidirectional cross-filtering only when absolutely needed. Otherwise, it might just end up slowing down a lot of your visualizations and degrading the user experience overall. Given that this is a rather complex topic, I can understand if you'd like to learn a little more, in which case you can navigate to this link in the Power BI official documentation. This also includes a link to a very nice white paper which points out, among other things, that this bidirectional cross-filtering is a relatively new feature in Power BI. So for the DA-100 certification exam, keep in mind that bidirectional cross-filtering may adversely impact the performance of your visuals. Alright then, let's take a look at one more feature of modeling relationships in Power BI, for which we will explore the relationship between product category and subcategory. So we can just click on the little button in the middle and then choose properties, and we'll focus on the cardinality of the relationship. So this is currently set to many to one, which means that for each product category, there are multiple subcategories. And based on what we saw of each of these tables earlier on, this does make sense. However, Power BI did detect the fact that the nature of this relationship is many on the subcategory side and one on the product category side. And to see how, let's just try to change the cardinality to many. And the moment we do this, well, a warning shows up at the bottom. This clearly points out the fact that such a many-to-many relationship can only be set if we know that the product category key column is not going to be unique on either end. So Power BI has clearly picked up on the fact that product category key is unique on the side of product category and not so on the subcategory side. To further confirm this, let's try to modify the cardinality once again to 1 to 1. And the moment we do this, we are told that this cardinality is simply not valid. And in fact, the OK button at this point is not even active. This is because a 1-to-1 relationship can only be established if there happens to be a common unique key on both sides of the relationship. And given that the subcategory column has multiple occurrences of the same product category key, well, a 1-to-1 relationship cannot be set up. So this is just an indication of how Power BI does perform a few checks when it auto-detects and applies relationships between tables. So let's just cancel out of this view, and then we can say that, at least from the point of view of the little analysis which we have performed, these relationships have been defined exactly as they need to be. Previously in this learning path, we loaded data about bike and bike accessory sales from a fictitious retailer, and what we have in here include a fact table called Sales 2017 and a number of dimension tables surrounding it. These include products and customers which are directly related to sales, but then we also have returns, subcategory and product category which are indirectly related to it via the products table. However, there is one table which we have mostly ignored so far, and this is the territories table. So you can see that this effectively is on an island on its own and is not really linked to any of the other tables. However, we also saw that this was only because its relationship to the sales 2017 table could not be auto-detected due to a slight mismatch in the name of the common column. That is something we will address a little later on. But for now, let's focus on one of the features of this territories table, and this is the fact that the continent, country, and region columns which it contains are in fact related to one another in a hierarchical form. To be precise, each continent contains a number of different countries, and each country can be subdivided into one or more regions. We have already seen previously in this learning path that there are date hierarchies which can be set within Power BI, and in fact, we can also configure hierarchies for geographical data, and this will allow us to analyze data in a manner where we can drill down the different hierarchies. For that to happen, however, we will need to explicitly set a hierarchy, since this is one which will not be auto-detected by Power BI. And for that, well, let's just open up the menu corresponding to one of these columns which need to be part of the hierarchy. I'm just going to pick region here and then choose the option to create a new hierarchy. The moment we do that, well, you will notice that there is now a new field which has been created within the territories table for a region hierarchy. When we expand this, we see that at the moment it only contains a single field, and this is the region, but this is something which can be configured. In fact, the little properties pane which appears to the left of the fields pane is where this configuration is possible, starting with the name of this hierarchy. So it currently says region hierarchy, but I'll just be a little more descriptive here and say that this is a regions hierarchy, since of course regions is at the bottom of the hierarchy here. You'll also observe that it is possible for us to enter a description for a hierarchy which we create and also place in some synonyms. Synonyms are not quite relevant in this learning path. However, this is something which can come into play when designing Q&A visuals in Power BI. Scrolling further along in the properties, we can see some of the other configurations which can be set here, including hiding this particular field from view in the reports view. This can be done by setting the isHidden attribute to yes. And then we have the hierarchy settings. So this is where we are going to be working for now. And you can see that the region field has already been added to this region hierarchy. But now to add another column, well, we can select from this drop down, and we'll start off by picking the top level of the hierarchy, which is the continent. Once that is done, we now have continent plus region in the hierarchy. Then the missing ingredient here can be picked from the drop down once again, and this of course is the country. So with that, we have the three different fields which we need for our regions hierarchy. So these are region, continent, and country. But just in case you made a mistake in adding a particular column, well, it is easy enough to just hit the X button in order to remove it. Now I'll just reinstate the country from the drop-down menu. And now we're back to the three different fields which we need. However, these fields are not in the order in which the hierarchy needs to be applied. So the placement of each of these fields is important, because as things stand, it says that region is at the top of the hierarchy, followed by continent and then country. But to fix this, we can simply drag and drop each of these fields to their correct positions. And now things are as they should be. Continent at the top, country just below that, and each country, of course, can have multiple regions. At this point, we can simply hit apply level changes for our configuration changes here to take effect. And once that is done, when we expand the regions hierarchy, we see continent, country, and region in that order. We are not quite done with our regions hierarchy configuration, however. Our next step is to mark out each of these fields as conveying geographical data. Well, for that, we'll need to configure each of the fields individually. So we can begin by selecting the continent, and then from the properties pane which pops up, you'll observe that we can rename the field over here and also set descriptions or synonyms. However, what we are interested in is right below, where we can expand the advanced settings. And here we see that it is possible for us to configure sorting for this particular field, and then we can also supply the data category. It is this category which we will now alter by expanding the drop-down, and we can see the different values which can be set here. We can mark this field as conveying an address, or that it represents the name of a city, or even the latitude or longitude of a location. This categorization is something which will come into play when plotting this data on a map visualization. A map visual is something which will be covered in depth in the next learning path in this journey. But as far as modeling data is concerned, it is important for you to know that if you feel that a particular field can be used in a map visual, you should mark it as the type of geographical entity it represents. You can see that it is also possible to categorize a particular field as a URL or a barcode. In our case, of course, the continent field represents a continent, so we will mark it as such. And with that done, you'll notice that a little globe icon now shows up next to the continent field. Now you'll notice from the properties pane that the data type or the format has not really changed at all. This still says text. However, Power BI now knows that this column can be used in order to mark continents in a map. Similarly, we can also categorize a country. So let's just select that field first, and then the same type of properties can be configured over here. And scrolling right down over to the data category, from the drop-down menu, we will now make the selection of country or region. With that done, well, the globe icon also pops up next to country. And at this point, if you're wondering, how exactly does setting this particular field up as a country or continent help when it comes to maps? Well, think of it this way. If you search on any kind of mapping software for a particular place, let's just say a country, it is able to identify the country even if you use different variations of the country's name. Most of Power BI's map visualizations are built on Bing Maps, and categorizing fields as either continent, countries, or cities will allow Bing Maps to locate such places on the map and potentially mark them in a visual. Alright then, let's move along to the region field, and then in the data category, set this as once again a country or region. And with that done, well, all of the three different fields in our regions hierarchy have been explicitly marked as geographical entities. Each time we generate a geographical hierarchy, it is important to categorize the data as such, because typically when we do have such data, at some point a map visualization may need to be created out of it. So with that, well, we have now configured the regions hierarchy, and it is now possible for us to use them in visualizations. However, you will notice that we have yet to establish a relationship between the territories table and the sales table. So this means that if we were to combine the data from both of these tables, we will run into issues. Next, however, we will try to use a regions hierarchy in a table visualization. And for that, let's head over to the reports tab, and we will generate the table in the next video. In the previous video, we generated a regions hierarchy which is now available within the territories table. And of course, this hierarchy consists of continent at the top level, country just below that, and region at the bottom. Now, to make use of this regions hierarchy in a table visualization, well, we can simply repurpose the table which we already have within the reports view. And for that, however, we will need to clear out the current contents. So from the values pane here, I'll just remove count of customer key, followed by the subcategory. And then this table will need to be populated with new data, starting with our regions hierarchy. And automatically, you'll observe that the three different levels of our regions hierarchy now show up in the table. Before we load any new values in here, let's quickly summarize what exactly the data in the territories table contains. So it points out that there are three different continents within our dataset. So these are Europe, North America, and Pacific, which is a continent only from the point of view of this retailer. The European continent has three different countries, France, Germany, and the United Kingdom, and each of these have just a single region which match the names of the countries. North America has two countries, Canada and the United States, and it's just the United States which is broken up into 5 separate regions. And the Pacific continent has just a single country and region, namely Australia. And now it's time for us to see what value of sales were recorded in each of these regions. So for that, we can just include the sale amount calculated column in this table visualization. And the moment we do that, well, a new column has popped up in the table. However, the fact that the same value appears in each row means that something is missing. This, of course, is because the relationship between the territories and sales tables has not been defined. We will get to that in just a little bit. But first, heading over to the format pane for the visualization, I'm just going to include the totals here. So from the total menu, we'll turn on the totals. And we now have the total summarized in the bottom row. So we will need to set up the relationship between territories and sales, for which we head over to the model view. Alright then, let's set up this relationship by dragging the sales territory key column inside territories over to the territory key column in sales. And now we can see a line connecting territories and sales 2017. So territories is no longer an island. Now to ensure that this relationship has been configured correctly, let's just take a look at the properties here. And here we can see that these two tables are related to one another based on the territory key in sales and sales territory key in territories. Also, the cardinality of this relationship has been set to many to one. So many sales records map to a single territory. So this all seems fine right now, as does the cross filter direction, where it is possible for us to filter sales based on territory, given the unidirectional cross filtering. And of course, this relationship has been marked as active. So everything looks good over here, which means that we can simply exit out of this view by hitting the OK button without making any changes. And then when we head back over to the reports, well, the sale amount column does seem to contain the correct numbers. So here we get to see the sales recorded in each individual region. So the region with the highest revenues here is Australia, and this is followed closely by the southwestern United States. Sales in the central United States have barely registered at just about $300. So we have now successfully used a region hierarchy in a table visualization. However, what is the benefit of us having a region hierarchy in this case? Well, it is easy for us to simply disregard one of the levels of the hierarchy. So by eliminating the region, which is the lowest level, we can see the sales for each of the countries. So much like with a date hierarchy, when we have a hierarchy of geographical regions, well, it is still up to us what levels of the hierarchy are represented within our visualizations. In fact, in the visualizations learning path, which follows this one on modeling data for Power BI, we will cover charts where it is possible for us to drill down various levels of a hierarchy in order to get more and more detailed information. In any case, now that we have eliminated region from this table, we can see that the most significant country in terms of revenues here is the United States. Next, let's just go ahead and eliminate the country column from our table visualization so that we're only left with the sales for each of the continents. And here we have it. Now it is also easier for us to confirm that the 3 million in Europe plus the 3.7 million in North America plus 2.4 in the Pacific continents sum up to the total of 9.1 million. So having covered the use of a geographical hierarchy within our table visualization, in the next video, we will focus on configuring the sale amount calculated column within the sales table. In the previous video, we generated this table visualization, which gives us the aggregate sales amounts for each of the continents. Now, when I use the term aggregate here, I mean it in the colloquial sense. However, it does have a very specific meaning in the context of Power BI, since aggregations can come in various forms. The aggregation which is applied here is, of course, the sum of the sale amounts. We have already seen that this is the default aggregation which is used for numeric data in Power BI. However, this is something which can be changed by a setting. Furthermore, we can also change this particular field so that the decimal values are no longer displayed, since when we're dealing with numbers totaling in the millions, that is not particularly significant. To demonstrate, let's switch over from the report view over to the model view. And since it is the sale amount calculated column in sales 2017 which we wish to modify, we expand the table and then navigate over to sale amount. And then when we click on this, well, first of all, you will notice that in the model view, in the sales 2017 table, sale amount has now been highlighted so that we can see exactly where in this design view our field fits in. And then in the properties pane, we can now configure this particular field. We're not quite interested in changing the name or description now, but instead, let's head over to the formatting section, where we can see that the sale amount has automatically been assigned the type of decimal number. This, of course, has been chosen by Power BI, and there is enough precision in the data available for us to make full use of this type. However, we have already seen that when it comes to the sales data, in our analysis, we often work with numbers in the scale of thousands, if not millions, in which case this decimal precision is really not needed. However, to retain the decimal value but only present whole numbers in a visualization, we can retain the decimal number data type but change the format from general to whole number. So with this selection, we have now the correct data type as well as format for our visualizations. And you'll notice that it is also possible for us to set a percentage format if this value represents a percentage. Since it does not, we can leave it as no, and then we can also configure whether 1,000 separator should appear by default. I'm just going to set this to yes, since once again, the scale of the numbers we are dealing with here is usually in the thousands or millions. And while all of these seem like rather low-level settings, these are absolutely essential when it comes to generating visualizations which are rich and informative, and from which insights can be extracted easily. The formatting as a whole number plus the use of 1,000 separator will make the sale amounts much easier to read and interpret. As for the decimal places setting, we can leave this as 0 since we only wish to work with whole numbers. And then under the advanced settings, well, we have already applied a data category change in our territories table. However, the main setting we are interested in at the moment is the summarized by property. So this is where we can see that by default, it is a sum which will be used when summarizing the sale amounts, which of course makes sense. However, there may be instances where an average or some other kind of summarization will be more appropriate. For instance, if you're working with the price of products in a dataset, it will be much more appropriate to summarize the price by calculating the average rather than simply counting the prices of all items. For instance, it makes much more sense for us to compute the average price of products in a particular category rather than the sum of the prices, given that the sum depends on the number of items available. For now, however, let's just change the summarization for our sale amount to average. And with this selection, well, to view its effects, let's just head back over to our report view. And we can see that at least within our table visualization, it still calculates the sum. This is because this visualization has already been generated using the sum of sales as the aggregation. However, if we were to create a new visualization, we will soon see that it is the average of sales which will be computed. And for that, well, let's just click on the report at some point outside the table visualization where we can place in a new visual, and we can now click on a card visualization so that it gets added to the report. And following that, well, let's expand the sales table and see what value is displayed if we were to add in the sale amount to this card. Just as a quick reminder, if the aggregation which is performed is a sum, the value we should see is about 9.185 million as in the total row of the table visual. However, when we include sale amount now in the card, what we see is 312. So this is the average value of a sale line item. To confirm that this is in fact the average, we can just head over to the field section of this visual, and from the menu for sale amount, we can confirm that it is in fact the average sale amount which has been computed. Of course, the setting which we have changed is only for the default summarization, and we can simply switch over to any of the other summaries here. For example, we could opt for a count or even a minimum or maximum. However, as mentioned earlier, when it comes to the sale amount, a sum is much more appropriate as the default aggregation. So let's just head back over to the model view, and then from the properties menu, we change the summarize by setting back to sum. With that done, let's head over to reports, and now to make sure that the default summarization does in fact perform a sum, let's first eliminate this average of sale amount from this card visual and then re-add the sale amount. And now the value which is on display matches the total in the table visualization, and this is 9 million. The value, of course, has been rounded. And now to confirm that it is in fact a sum which has been calculated, when we take a look at the menu, the sum has been checked. So we now know not only how to change the default aggregation which is performed for numeric data, but also when it is most appropriate to use average or sum. And now that we have covered various aspects of modeling data in Power BI Desktop, in the next video, we will focus on categorizing all of the key columns in our tables into a single unit. We will now continue modeling the data we have been working with, and this time we will group similar fields together into a single folder. This grouping will allow us to treat all of the fields in it as a single unit and make certain setting changes to all of them in a single go. We will now perform such grouping for each of the key elements or the key columns within our tables. We are now currently in the model view, and each of our tables are related to at least one other table. Now with so many different tables, and with each of these tables having multiple fields on their own, if you were to try and build visuals out of these, well, we have way too many choices. Just looking at the customers table, well, the details here include the customer key along with some personal details including their date of birth, their first and last names, email address, and so on. While all of this can be helpful if you're trying to get details about individual customers, when it comes to performing data analysis, do we really need all of this information? For instance, do we really need the customer's email address and first name in order to analyze their data? Surely, details such as their annual income, their age, which can be computed from the date of birth, education level, and so on, will be more useful when analyzing sales data for different types of customers. So, we could make the argument that details such as email address and first name should never belong to any visualizations. And at this point, let's assume that you are an administrator of Power BI projects and you have other teammates who are tasked with building visualizations from this data. Well, a good practice then is to obscure unnecessary fields from the visualizations team so that they don't inadvertently make use of them in a visualization or even consider including them. And this brings us to the concept of grouping certain fields together into a folder, following which we will see that it is possible for us to hide them from view in the reports pane of Power BI Desktop. And for now, we will focus on obscuring each of the key fields so that those are not really included in the visuals. And of course, you can imagine that details such as the customer key in the customers table does not really belong in any kind of chart, as it does not convey any meaningful information about customers, though of course is very useful in the back end, where we can use it to join related tables and also in order to count customers when we use measures for aggregations. In fact, let's go over each of the tables over here to get an idea of what keys are present. In product category, we have the product category key, again, which is not particularly useful in a visualization, but of course the category name can be used to perform some helpful aggregations. For instance, to view the sales for each category. Then as we move along, there is the products table, and in here we have the product key itself along with a product subcategory key. So these cannot directly be used in visualizations to extract any meaningful information. In returns, we have a product key as well as a territory key. Heading into sales, this is related to customers via the customer key and to products via the product key. Now I'm not really listing every single key, but we can see that even the subcategory is made up of two key columns. One of these serves as the primary key for this table, which is the product subcategory key, and then the product category key can be used to relate this to the product category table. And then finally, we have the sales territory key inside territories. So once again, the goal is to hide each of these key columns or fields from the visualizations pane in Power BI, so that anyone who develops visualizations will not inadvertently use them or be even tempted to use them in the first place. Now it is possible for us to hide each of these fields one at a time. However, it is much easier if you were to treat them as a unit. And we will now group them together into such a unit. The first step towards that is to select all of these fields together. So let's just select sales territory key from territories, and then make sure that the control key is pressed on your keyboard before heading over to the subcategory table and selecting the subcategory key and also the category key. So to use relational database terminology, it's not just the primary keys of each table which we're looking to group together here, but also the foreign keys, the fields which connect one table to another. So now that we have collected three different keys, let's move on and include the territory key from the sales 2017 table and also the product key from it. Then there is the customer key. As these selections are made, you can take a look at the diagram displaying the relationships and the tables, where each of the selected keys have been highlighted in the tables themselves. Moving along then with the key selection, make sure again that the control key is still pressed and choose territory key followed by product key from returns, and you get the idea now. I'll just go ahead and select the different key columns from the products table here. So one key is selected, and then scrolling along, we will also go ahead and choose the product key, and then to wrap things up, we'll select the key column from product category, and finally we'll move on to the customers table where the customer key will be chosen. Alright then, there are a whole host of keys which we have now selected. So how exactly can we group them together and then hide them from view in the visuals pane? Well, for that, we can make use of this property menu which appears over here. And you can see that it is now possible for us to make various settings changes to all of these different fields as a group. The setting we are interested in right now is the isHidden property, which has been set to no by default. And this means that these fields are not hidden and will be available in the visuals pane, but we can simply switch this over to yes. When this is done, well, take a look at the fields menu, and then next to each of the selected keys, we have a little eye icon with a line across it, conveying that these fields are not meant to be seen in the reports view. Alright, so now that we have obscured each of these fields, the next thing we can do is to cast them into a display folder. So by calling this keys group, we have explicitly marked these out as belonging to a specific group of fields. Once this little change has taken effect, well, I'll draw your attention once again to the fields pane, where each of these key columns now shows up inside a folder called keys group. So you can see the customer key is inside this folder here, and then within the product category table, this is also the case with the product category key. Moving over to the products table, well, the product key and product subcategory key now show up together inside the keys group. And as we move along, we can see all of our key selections, including the 3 keys in sales, are now cast together. So now that we have successfully created a group of fields within Power BI, I'll just zoom in a little bit in this relationship diagram, and we can see those little hidden icons next to each of these hidden fields. Now the big question, of course, is whether these fields are in fact hidden from view, for which we head over to the report pane, where we have our confirmation. Looking at the sales and territories columns which are up, we can clearly see that none of the 3 key fields are available inside sales, and neither is the territory key from within territories. Previously in this course, and more specifically in the videos titled Creating a Geographical Hierarchy and Using Geographical Hierarchies, we were able to define a hierarchy of geographical entities within the territories table, which you can see in the fields pane. This, of course, being the regions hierarchy. This was a hierarchy which we needed to explicitly define. However, we also know that Power BI supports date hierarchies, and these can be created automatically when loading data containing dates into Power BI Desktop. Glancing at the Sales 2017 table, we can see that order date and stop date over here have automatically been assigned date types, and these also are date hierarchies. We will now explore this auto date hierarchy detection feature in Power BI. For that, however, let's go ahead and remove this card visualization since we no longer require this. However, we will retain the table because we will use that in order to view information in the context of dates. First, we can make sure that we click this table so it becomes active, and then under the values pane, we see that this includes the continent field from the regions hierarchy along with the sales amount. But now, let's just go in and add the order date from Sales 2017 as well. This will allow us to view the orders for each date from each continent. Significantly, each date is represented using the year, quarter, month, as well as the day itself. So in effect, it is the entire hierarchy of order dates which is in use. Now, you may not be interested in breaking down the order date into each of these different dimensions, and all you may really need is the day itself. In which case, this order date hierarchy can be collapsed, for which we expand the menu, and then rather than render this as a date hierarchy, we simply choose to render this as a regular order date. Before this selection is made, I'll draw your attention to the table visualization where the last 4 columns represent the 4 different levels of the order date hierarchy. But once we choose to cast this as a regular date rather than a hierarchy, well, the table visual has changed and there is just a single order date column. You will note, however, that the number of rows in the table has not really been affected by this modification, since each row here still corresponds to a specific date for a specific continent, except that the date itself is not represented as a hierarchy of 4 different fields, but as a single value. Now, this may be more than enough for your own visualizations, in which case, you may not really want the date hierarchy to be applied. Moreover, you may not want a date hierarchy for every single date field loaded into Power BI Desktop. And we will soon see how this can be accomplished by turning off the auto date time feature. For now, however, let's stick with configuring the order date. So from the table, it is clear that the representation of the date is rather long. Looking at the date in the top row, this says Sunday, January 1st, 2017. Now this may be exactly what you need. However, in many cases, you may want a shorter representation. Well, of course, for that, we just need to change the format for this order date field. And to do this, well, there are different places within Power BI Desktop where this can be accomplished. For one, we can do it from the model view, but now we will head over to the data view, and then we will pull up the Sales 2017 table, which contains the order date. From here, let's go ahead and select the order date column. And once that is done, under column tools in the top, we can just head over to format and then choose the format which we prefer. I'll just choose this one where the date appears first. And with that, well, the order date is a little more concise. There is also a stop date field. let's just select that and then apply the same format to this field as well. And now that the fields have changed, when we switch back over to the report view, well, the representation of the order date in the table visual has also been modified. Alright then, now that we can see the sales per continent per date, well, let's just reorder the sale amount and order date columns within this table by dragging the order date and then placing it before sale amount. And it is much clearer now what the categories are and then what the aggregated value is. That of course being sale amount, which is the last column. Alright then, before we turn off date hierarchies, let's just reinstate the date hierarchy for the order date by bringing up its menu and then picking date hierarchy. And sure enough, the single order date column has been now expanded to 4 columns in our table. Now before we get rid of the hierarchies for the date, I'll just play around with it a little bit. So by removing some of the fields and then reinstating them, and now that we know what is possible with date hierarchies, well, let's go and turn it off. But before that, let's quickly take a look at the table itself, where we have 4 columns corresponding to the different levels of the date hierarchy. And then we have the date hierarchy itself, which we can see in the fields pane. Now, to turn it off, let's head over to File and then navigate to Options and Settings and then pull up the options. We have, of course, been here before, and while previously we focused on turning off auto detection of relationships, we are now concerned with the date time settings. So within the global data load options, towards the bottom of the screen, you can see under Time Intelligence that the auto date time for new files has been selected. This means that dates will automatically be detected from the loaded data and date hierarchies will also be created. However, rather than modify the setting at a global level, and this setting only affects new files, when we head over to the data load under current file, well, there is now the option to turn off auto date time configurations. So I have unchecked this box, but we need to hit OK for these changes to take effect. But before that, I'll again draw our attention to what you can see in the background, where the table visual has 4 columns for the order date, and then we have those same 4 columns in the date hierarchy seen within fields. But now when we hit OK, well, all of those have disappeared. There is just a single order date column within our table visual, and this represents the order date as a regular date. In fact, under the Fields menu, you will notice that order date no longer appears as a date, but as a regular text field. In fact, if you were to head over to the menu for the order date, well, there is no longer an option to cast this as a date hierarchy. Alright then, let's now reinstate the auto date time detection. So we head back over to File, and then over to the Options and Settings, and then to the Options. I'm just going to repeat each of the steps by heading over to the data load under current file, and then checking the box for auto date time. And now when we hit OK, well, there are a few changes in this report view. Specifically, order date now appears as a hierarchy, and this hierarchy itself does include the year, quarter, month, and day. And as a final sanity check, when we pull up the menu for the order date from the visual, well, there is the option to set this as a date hierarchy. So with that, we now know the power of the auto date time feature in Power BI. We will now build our way towards implementing row-level security in Power BI. Before we get to that, let's quickly take stock of where we are now. So we have loaded 7 different tables into Power BI Desktop, corresponding to the sales of various bikes and bike accessories for a fictitious retailer. So the entities we're working with include customers, product categories, and so on. You will also see from this relationship diagram that each of these entities are related to at least one other entity. And based on some of the operations we have already done earlier on in this learning path, you know, for example, that we can aggregate the total sales based on different groupings. For example, we can calculate the total sales for each territory, subcategory, and so on. However, in each of the examples we have covered so far, it has been possible for us to view the sales data for every single sale. Now it is entirely expected that Power BI will be used by top-level management in your organization who will need access to all of the data available. However, there may also be mid-level managers whose access may need to be restricted. For instance, there may be sales department for each product category, and members of those departments should only be able to view their own sales and not that of other departments. This is what row-level security allows us to accomplish. Now, to see how exactly this can be done, we will need to add in a new table, for which let's head over to the Transform Data option. And as you may well be aware, this will pull up the Power Query Editor. This is where we can apply transformations to each of our different tables. But now let's just head over to the product category and take a look at the 4 different categories present here. So these are bikes, components, clothing, and accessories. And for the sake of our example, let's assume that each of these represents a separate sales department in an organization, and that each of these sales department has their own manager. We will soon create a separate table containing the details of those managers, and they will be linked to this product category table via the product category key. With that said, keep in mind that there are a total of just 4 keys represented by the numbers 1 through 4. Alright then, let's just move along and quickly glance into the other tables over here. And once we're satisfied that there are no further transformations required, well, it's time for us to create a brand new table. This one will contain the data for the fictitious sales managers corresponding to each product category. This will be a table which is small enough where we can manually enter the data. So we choose the Enter Data option, and this will pop up an interface where we can create a new table. So we can add rows and columns to this. The new table will contain a total of 5 columns. So you can just go ahead and add them by hitting the little plus button here. And then once you have those columns in place, you can set the column headers as I have done here. So the columns are employee ID, name, title, UPN, and category key. And then the data itself can just be pasted, and the data is available as part of the course materials. So you can just copy and paste in this information from there. Or you could just simply type in any fictitious details as long as the category key does match at least some of the product category keys we saw in the product category table. So let's quickly summarize what this table contains. So each row represents a manager of a specific sales department, which maps to specific product categories. The title of each employee here is manager, and they are identified by a name and also a UPN, which in the context of Microsoft's Active Directory is short for user principal name. Expanding this particular column, we can see that this represents what looks like an email address, and while it could in fact translate to a real email address, in Active Directory, this is simply a username in the format of an email address. I bring this up because this is how a user who logs into the Power BI service can be identified. And when implementing row-level security, we will configure the visibility of data based on this UPN. Now, each of these department managers is mapped to a specific product category by means of the category key column. And speaking of the product categories, well, I'll draw your attention to the fact that there are 5 different categories represented here, while we only had 4 in the product category table. Specifically, the last row here points to an employee with the name Gareth Vargas, whose department is not really mapped to an existing product category. So let's just assume that this is a new department which has been created, for which sales have not quite been recorded yet. And when we implement row-level security so that these managers can only view their own sales data, Gareth Vargas should not be able to view any data. Alright then, this is all of the data we're working with. At the bottom, we can also go on and set the name for this newly created table, and we'll just call this product category managers, and then we can just hit OK. In a few moments, we now have an 8th table which has been created in our Power BI desktop file. Once we confirm that all of the data looks fine, well, let's just go on and choose to apply the changes of the addition of this table, and we'll be taken back over to the model view. To make sure that this table is available, let's just scroll along. And yes, product category manager does show up, but of course it is not related to any of the existing tables. We will need to explicitly define the relationship between product category managers and product category. So for that, I'll just move around some of these tables here so that the view is a little more compact. And once that is complete, it's time to establish the relationship between the product category manager and the product category. This can be done using the category key column in the new table. So we can just map it by dragging and dropping it over product category key in the product category table. Once this is done, you may notice that a one-to-one relationship has been applied between these two. And to confirm, let's just pull up the properties of this relationship. And there you have it. We know that category key and product category key have been used to establish this relationship. Power BI has automatically set the cardinality of this relationship to 1-to-1. And this has been done because Power BI has figured out that the category key columns in both of these tables do contain unique values. And you'll notice that the cross-filter direction in this case has been set to both by default. Given that this is a one-to-one relationship, it does make sense for each of these tables to be used to filter the contents of the other. Of course, you can reset the cardinality if you believe that each product category may have multiple managers, or on the other hand, some managers may be put in charge of multiple product categories. This is entirely a design choice, and this one-to-one cardinality has only been set based on the current data, which of course may be subject to change in the future. In any case, let's say we are satisfied with how this relationship has been set, so we can just hit OK, and in the next video, we will focus on implementing row-level security. In the previous video, we added a product category managers table containing the data for managers of individual departments which map to specific product categories. It's now time for us to implement row-level security so that each product manager will only be able to view their own sales data when using Power BI. Well, for that, let's first head over to the data view and do a quick sanity check by looking at product category managers, where we can confirm that all the data we entered has shown up here. And when it comes to row-level security, as touched upon earlier, it is the UPN which will play a crucial role. Now, when any user logs into the Power BI service, they will be identified by a UPN such as this one. It is possible for us to extract the UPN of the logged in user and then implement security measures based on that information. As for what exactly those security measures could be, let's head back over to the model view and then check out how exactly the product category managers are related to the other data. More specifically, how exactly are the category managers related to the sales information? Well, if we follow the path from the product category managers to product category, then subcategory, products, and then sales, well, it is possible for us to aggregate the sales for each product category manager. Our goal, of course, however, is to limit the view which is available to each product manager so that they can only view their own sales data and not that of the other managers. And towards this end, we will need to create a new role. This can be accomplished by heading over to the Manage Roles section. And sure enough, at least in my view, there are no roles to manage. However, there is the option to create a new role, and that is what we will now opt for. And when we select that, well, this is what we can do when setting up a role. Just in case you're unfamiliar with setting user permissions, a role essentially encompasses a set of permissions which regulates what actions can be performed. Roles can be assigned to one or even more users. And a good practice is to define roles which can be assigned to multiple users. In any case, now that you have an idea of what roles are, let's go about setting one up for our own Power BI instance, starting with the name of the role. So let's just call this one manager sees own data, since this is exactly what we want to accomplish with this role. And now it's time for us to set exactly what information will be visible to a user. More precisely, we will restrict the view of a manager to only their own row in the product category managers table. For this to happen, from the tables menu, let's select product category managers. And this presents us with the option to add a filter on this table. And that is precisely what we wish to do. So let's expand this menu. And this presents us with further options pointing to the different columns in the table. So on the basis of which column in product category managers will we assign permissions to the signed in user in Power BI service? Well, once a user signs into the service, we will have access to the user principal name or UPN, and we will check this against the UPN column within this table. So let's make this selection first, and then we can specify a DAX expression which decides whether a particular row in product category managers can be accessed by the signed in user. So if I have signed in as user X, which row in this table should I have access to? Well, it is the row which contains my own information. So for a product category manager, once they have signed in to Power BI service, they'll have access to the row where the UPN column has the same value as their own user principal name, which can be obtained by invoking the DAX user principal name function. Now, when you take a close look at this particular function call, the spelling of principal is a little off. It should be PAL, but I have typed in PLE, which is why when we try to save down this DAX expression, well, there is a warning message below, which points to the fact that this is not a valid function. However, we still have the option to keep this particular expression in place, but I'm just going to choose to cancel out and then retry. So you can see that if you do type in a wrong DAX expression, there is validation which can be performed in this particular view. So there is a lower chance of being stuck with a wrongly configured role. Now I'll just fix this spelling mistake here and then use the correct function call for user principal name. And in order to explicitly perform a validation, we can make use of this button. And now the warning message has disappeared, which means that this is a valid DAX expression. Before we save down the role, however, let's quickly summarize what we have implemented. This role with the name of manager sees own data applies to the product category managers table. When a user signs into the Power BI service and then try to check out this particular table, they will only be able to view the data where the user principal name matches the row which has that same user principal name in its UPN column. And while this particular security measure only applies to the product category managers table, the security measure also applies to any aggregations performed using this table, which we will soon see. So let's save things down. And now we're back to the model view. But to test out the row level security settings, we'll head over to reports and we will continue using this same table since it does have the right formatting for us. So rather than create a new one, I'm just going to clean it up by deleting each of these different values from here. And once the table has been emptied, let's add in some new data. So the goal now is to view the sales corresponding to each manager. For that, we expand in the fields menu the product category managers table, and then in our table visualization, we will add in the name field. So the 5 different category managers now show up here, but we already know that the manager Gareth Vargas does not really map to an existing product category, so there won't be any sales corresponding to that manager. In fact, we will soon see that as far as the sales in 2017 are concerned, one of the other managers also has recorded no sales. Alright then, it's time to move on to the next step, when we expand sales 2017 and then add in our sale amount calculated column. So these are the sales for all of the managers whose departments recorded sales in 2017. We can see that by far it is JPAC's department which has recorded the highest revenues, and this corresponds to the category of bikes. 2 managers who exist in the managers table and don't show up over here are Gareth Vargas and Linda Mitchell. Their absence here, however, is not due to any security setting, but simply because their departments did not record any sales. The question then is, how exactly can we test whether the row level security which we implemented does indeed work? Well, for that, within Power BI Desktop, we will need to simulate signing in as a specific user and ensure that a newly created role is activated. First, however, I'm just going to make a slight change in the formatting of the sale amount. So you don't really need to go along with me here. I'll just add in 2 decimal places before moving along to the model view. So this is where, in order to sign in as a specific user, we can head over to the View As option. This will allow us to view the reports pane as a specific user. So when we pull this up, you'll observe that there is no role configuration set up as yet. So within Power BI Desktop, we do have access to all data. However, if you'd like to view things as a specific user, we'll need to check the Other User option and also enable our Manager Sees Own Data role. Then, within the Other User form, we can specify exactly which user we would like to sign in as in our simulation. So, we can put in the UPN of the user, which in the case of the manager of the bikes category is jpack@loonycon.com. Now when we hit OK, well, the view has changed and you can see that there is a little notification bar which allows us to turn off this view as setting so that we can go back to viewing all of the data. But let's just stick with this for now and then see what is visible when navigating over Power BI Desktop. First of all, we can head over to the data view. Conveniently enough for me, it is the product category managers table which is now up, and clearly there is just a single row which is visible here. So it is not just in the visuals but also within the data view where these security roles can be applied. Next, let's head over to the reports, and in our table visual, there is only the data for JPAC. Even the total row only summarizes the sales for this one manager. So we now have an idea of how row level security works. However, let's see if it is possible for us to view more detailed information about the sales recorded under JPAC. For that, let's head over to the territories table and then see if it is possible for us to view the sales recorded under JPAC's department across each of the different countries. So when we include country here, well, the breakup is available to us. Once again, however, it is only JPAC sales which are visible here. So now that we've ensured that JPAC is only able to view their own data, in the next video, we will sign in as some other users and see what difference this makes when it comes to the views. In the previous video, we successfully implemented row-level security in our data, and once we signed in as JPAC, we were able to confirm that this user is only able to view their own sales data. Now, we can hit this Stop Viewing button in order to go back to a view where all of the data is visible. So let's just hit that. And now we can see the sales recorded in different countries for the 3 different managers whose departments did record revenues. Scrolling along, we see that these only include JPAC, Lynn Soflias, and Rachel Valdez. Next, when we switch over from this report view over to the data view, we're now back to being able to view all 5 rows in this product category managers table. Alright then, it's now time for us to sign in as a different user, specifically Lynn Soflias, and we know that her department did record some sales. So to sign in as her, we head back over to the model view and once again to View As. This time, we will also select the Other User and Manager Sees Own Data options, and then for the other user, we specify the UPN for Lynn. And once we set this to take effect, once again the notification bar pops up, which allows us to stop viewing all of this as Lynn. Heading over to the data view, we can confirm that Lynn is only able to view her own row in the product category managers table. And then from the report view, sure enough, this table has been adjusted so that only Lynn's data is visible. So now we can see the breakdown of the sales under her department across each of the countries. This of course ensures that each manager can only view their own sales data and nobody else's. And this is how security can be arranged in Power BI. We now continue exploring row level security by first stopping this exploration as Lin and then back to the model view where we can view as a different user. I'll just fill in the details over here very quickly. So we check the same boxes as we did before, but the user we will now sign in as is Linda Mitchell. You will recall that her department recorded no sales at all in 2017. So the question is, what exactly will we see in the table visualization where the aggregate of sales is computed and displayed? When we hit OK, heading over to the data view, sure enough, Linda can only view her own row. But in the report view, well, she sees nothing. Since her department had no sales at all, there is really no sales information she has access to. So we have now simulated the signing in as 3 different users. However, all of these users are those who exist in our product category managers table. What if we try to sign in as a user who has no entry in that table at all? For that test, we will of course need to stop viewing as Linda first, and then over to the model view. We navigate once again to view as, and again I'll check the 2 boxes which we have been working with, and then for the UPN, we'll supply one for Alice at lunicon.com. So there is absolutely no record of her within the product category managers table. So once we have signed in, so there are no errors which are thrown, and we do have the option to stop viewing as Alice. However, let's continue on first to the data view, where no row in the product category managers table is accessible. And this does make sense. This table contains the details for the different managers, but let's just say Alice is not exactly a product category manager and belongs to an entirely different department, which means that within our Power BI instance, she should not be able to view any manager specific data at all. Heading over to reports, sure enough, the table visualization is currently empty. That is, you can see the column headers, but none of the data. Alright then, let's continue on with our test by heading back over to the model view, stop viewing as Alice, and then back to view as. This time, we will re-sign as the user JPAC. So just make the selections here and enter the UPN for this user, and then head back over to the reports view. Sure enough, in the table visualization, we can only see the sales recorded in the different countries for the user JPAC. A question to ask at this point is, how strict is this row level security? Does it only apply when JPAC's own name appears in a visualization? Or will this still apply if we were to eliminate the name field altogether, or any other field from the product category managers table to which we have applied the row level security? Well, of course, there is one easy way to find out by simply deleting the name field from the table. But before we do so, I'd like to point out that the total sales recorded under J's department stands at about 8.468 million. And this includes about 2.8 million in sales in the United States and about 1 million in the UK. So when we go ahead and remove the name, well, it is still just J's information which we have access to. So the total sales numbers for the UK and the United States are exactly the same, as is the total sale amount. This clearly shows us that the row level security implementation in Power BI is quite robust. Even though our role has only been applied to the product category managers table, this has been used in order to filter each of the other tables as well. To understand how, I'll just first hit stop viewing and then switch back over to the model view. So let's try to understand how product category managers can be used to filter the sales records. And the short answer is that this is possible due to cross filtering. So looking at the product category manager table in this model view, this can be used to filter product categories, which in turn can filter subcategories, that in turn can filter products, and then finally sales. So now that we have an idea that row level security can be applied even if the table to which it is applied does not feature in a visual, Let's do a quick sanity check by heading back over to View As and then signing in as a different manager. This time, we will sign in as Lynn, who is the head of a different department. And then when we hit OK, and then head back over to the data view, sure enough, her own row is visible. And in reports, well, it is just her own countrywide distribution of sales, which she can view. The aim of this course was to cover a breadth of data modeling topics which truly showcase the extent of data analysis features in Power BI. You started off by loading a sales dataset containing a large fact table and multiple dimension tables, which was then modeled as a snowflake schema. You clearly saw how Power BI is capable of automatically detecting relationships between the loaded tables and what its limitations are when it comes to auto-detecting them. Specifically, you observed how the type as well as the header of the common columns need to match for relationships to be auto-detected. You then moved on to detailed configurations of relationships, from setting the right cardinality such as one-to-one or one-to-many, and also explored when to apply bidirectional cross-filtering. You learned that while single direction filtering is enough in most cases and is best suited for optimal performance, there will be specific aggregations which may only be possible with bidirectional cross-filtering. Next, you moved on to explicitly defining a hierarchy in your data to model a set of geographical values. You then covered some more detailed configurations which can affect your visualizations, such as setting a default aggregation operation on fields, hiding specific fields from the reports view, and disabling the auto date time feature. Finally, you cover the steps involved in implementing row-level security in Power BI. This is essential to ensure that individuals only have access to data which falls under their own domain when performing analysis with Power BI. You also saw how you can impersonate specific users within Power BI Desktop in order to test out the degree of access permitted. Having concluded this course and also this learning path, you are now truly an expert when it comes to modeling data with Power BI. You have all the theoretical and hands-on skills required to define accurate models and also ones which are optimized for performance. You are now all set to apply these skills for your own data analysis and to answer a range of questions in the DA-100 certification test. However, there is still more to cover when it comes to preparing for the exam and for becoming an expert at data analysis with Power BI. You can take up the next path in this journey where all that you have covered is put to use in order to build visualizations and in compiling reports and dashboards.
We will begin our study of visualizations in Power BI with a quick look at the importance of data visualization and some top-level best practices. Data visualization can be thought of as conveying information in the form of visuals such as charts and graphs. These visuals will include chart types such as line charts, bar charts, and so on. And in addition, they will also consist of other visual elements such as maps, icons, and tooltips. Taken all together, these visualizations and visual elements help the user or the consumer of the visualization to gain insights from facts, numbers, and measurements. Specifically, those insights might be a lot harder to extract by just looking at the underlying numbers. And it's for this reason that visualizations are an important means of democratizing data. Visualization software allows anyone, even someone who does not possess high-level numeric or analytical skills, to gain insights from data. And indeed, this is why the famous quote goes, "A picture is worth 1,000 words." Visualization has some very specific use cases. You can use visualizations in order to quickly spot outliers and errors. You can use visualizations to identify trends or patterns over time, to find relationships between variables, and finally, to summarize complex statistics. As we shall see in the many demos that lie ahead of us, there are powerful and common types of visualizations that are tailored to each of these use cases. Within the specific context of Power BI, you should be aware that Power BI has the Power BI desktop and the Power BI service. The Power BI desktop app is a great environment within which you can construct reports by pulling in data from many different data sources, plotting interactive visualizations, and compiling those visualizations into reports. Then, once a report is ready, you can go ahead and publish it to the Power BI service. From the Power BI service, it becomes accessible to collaborators as well as to the end users, that is, to the audience of your report. In this context, it's also worth noting that Power BI has a mobile app. And while designing your reports and dashboards, you should take the time and effort required to ensure that the mobile viewing experience is optimal. While constructing or compiling your reports, it's always important to retain empathy with your audience. Know your audience and understand what it is that they wish to get from your report. If your audience consists of analysts and scientists, these might be folks who would like technical information and they would like access to the raw data so that they can explore that data and go deep on their own time. This might be one common type of end user. Another common type might be members of upper management who really want high level data, a high level perspective, and are more likely to view reports using their mobile devices. So, while compiling your reports, it's important to balance these different considerations, such as access to the underlying raw data, the level of interactivity, and the level of customization for mobile phones. Choosing the right visualization type is an important skill, and while doing so, you should keep in mind these high level guidelines. If you'd like a very granular representation of the data, for instance, to give access to the raw data to an analyst or a data scientist, then a table or a matrix control in Power BI might be a good choice. If you're interested in identifying trends or patterns over time, line charts are probably your go to visualization. Power BI also has support for map charts of different types to convey geographic information. Column charts or bar charts, as they are also commonly known in other packages, are great for comparing data across categories. Tree maps are great visuals for comparing proportions within categories as well as for displaying hierarchical information. If you have a large number of variables, or if those variables represent a hierarchy and you'd like to show composition, a tree map might be your best choice. On the other hand, if you have a relatively small number of variables which are hierarchically on the same level, then a pie chart might be a better choice. Do keep in mind that Power BI also has many other specialized types of visualizations in addition to these most common generic types. In keeping with that same idea of staying in empathy with your audience, you should always try to make it easy for your audience to interpret the data in your report. Power BI has a rich support for tooltips. These can be customized and can be used to convey a wealth of information, and you should be sure to use tooltips extensively. Also, wherever possible and appropriate, you should include data labels so that visual elements are accompanied either directly using labels or indirectly in the form of tooltips with the underlying values. This will allow members of your audience to actually view the raw numbers whenever possible. Another guideline worth remembering is that color can be used to convey an additional dimension of information. For instance, you can convert a two-dimensional visualization into a three-dimensional one simply by using the color of the points in order to encode information about a new or a third dimension. Where possible, stick to intuitive color, green for positives, red for negatives, and so on. Also important from a test perspective is the use of color scales. You can use a color scale from Power BI in order to encode numeric data. Finally, use color judiciously. If you find that your report has too many color categories, consider using a grouping or some other way to simplify your visualization. Power BI also makes it easy for you to ensure that your data can be consumed by anyone regardless of format. Also keep in mind accessibility considerations. So while developing your report, do make sure to spend time on the mobile layout and check that all of the charts do indeed render correctly in that mobile layout. For smaller screens as well as for users with accessibility needs, it's also important to make sure that all visual elements are clearly visible and that contrasts are clear and highlighted. Let's now turn our attention to some heuristics and best practices when it comes to picking the correct chart. Power BI supports a wide range of chart types and visualization types, and it's a good idea to have some high-level principles in mind so that we always pick the best or most appropriate chart type for our use case. This choice of visualization can be thought of as governed by three primary factors. The first is the data, the second is the use case, that is the message that we wish to get across, and the third is the target audience. Keeping these factors in mind, here are some broad categories of presentation or chart types. Comparison, which serves to contrast different data series. Composition, which shows how different parts make up a whole. Distribution, showing a range of values extending between a minimum and a maximum, encapsulating measures of central tendency and dispersion. Visualizing trends as a way of seeing patterns in data, usually over time, and relationships, which show how different data series or data variables vary with respect to each other. If you find this set of categories a little overwhelming, never fear. It's actually a lot simpler to pick the right category type by asking yourself a few simple questions. If the question that you are interested in answering is of the form, how do values across categories relate? Then you should be thinking of a comparison visualization. If you're interested in how individual parts or constituents make up a whole, composition is your category. If you're looking to explore probability distributions or get a sense of central tendency or dispersion and distribution, then distribution visualizations make the most sense. Distribution-based visuals are great for univariate data. That's where you have one data series and you're looking to study its distribution. If you have two data series, then it's a bivariate relationship that you are interested in. And if you have more than two, this is a multivariate relationship. So as the number of variables increases and as you become more interested in how one variable relates to the others, relationship visualizations start to make the most sense. And if we are interested in how values perform over time, and if we are interested in spotting patterns, then it's trend visualizations that we should be thinking of incorporating. In addition to the specific use case that you're looking to solve, there also ought to be other high-level considerations that you keep in mind. How many variables would you like to display in a single chart? 1, 2, 3, or more than that? Is your data numeric, categorical, or a mix where some variables are numeric and others are categorical? And finally, can your data be represented in the form of a hierarchy? With these considerations in mind, let's now start understanding some of the types of visualizations in each category. Please keep in mind that these categories need not be disjoint, so there will be some visualization types which make sense in more than one category. For instance, comparison charts could include bar or column charts, tree maps, and pie and donut charts. Now, if you stop to think about it, pie and donut charts are also a great way of showing composition, that is, how different parts make up a whole. And so, when we turn to composition charts, pie and donut charts fit in here as well. Tree maps are also a great way of representing composition, and that's why they also fit into this category. And finally, we could also make use of stacked bar and column charts. We'll turn to the difference between stacked bar and column charts and clustered bar and column charts in a little bit. Next, let's turn to some of the common types of distribution charts, and these include scatter charts and line charts. In addition to these two, other kinds of charts such as KDE plots, that is short for kernel density estimation plots, and box and whisker plots are also a great way of studying the distribution of your data series. However, KDE plots and box and whisker plots are better suited to statistical and scientific applications. Power BI, on the other hand, tends to be mostly used for business-based applications. Scatter charts contain information about the central tendency and dispersion of a variable, but they also contain information about the relationship between two variables. So, scatter charts are also a good way of exploring bivariate relationships. If we'd like one additional dimension, that is, if we'd like to represent three dimensions in our two-dimensional data, then a variant of the scatter chart, that's the bubble chart, also comes in handy. In addition to these purely visual representations of data, Power BI has a couple of important tabular chart abstractions, and these are the table and the matrix widgets. It's important to note that these are not exactly visualizations, but they serve as great jumping off points. Because of the interactivity that Power BI offers, you can have your reports or dashboards include tables or matrix controls, accept user input in the form of clicks or drill down actions, and wire up these tabular controls so that the contents of some other visualizations in your report update accordingly. A table control consists of data arranged in rows and columns. As its name would suggest, this is a two-dimensional representation of data. Matrix widgets are more powerful, and you can think of these as similar to pivot tables in Excel. They allow multiple levels of dimensionality, and like pivot tables in Excel, are a great way to slice and dice data. Power BI, of course, supports all of these standard types of visualizations, but in addition, it's also extensible. This means that Power BI has an SDK which you can use in order to build custom applications. Those can then be loaded into AppSource, which can be thought of as a repository of visualizations. And then these custom charts can be accessed from Power BI and included in your reports in reusable fashion. The process of actually building such a visualization in Power BI is very intuitive and follows a common set of steps. Select the kind of visualization based on the data, the message that we need to convey, and the audience that we are going to try and convey that message to. Next, use the Power BI interface to add categorical and numeric fields to the visuals. You can think of a field as a column from a dataset. A categorical field is one which only draws from a specific allowed set of values, maybe days of the week or months of the year or car brand names. Numeric fields, on the other hand, take on general numeric values. Then customize or tweak the appearance of the visual. Power BI gives a lot of inputs so that every little aspect of the appearance of the visual can be controlled. Make sure that you spend enough time on this process so that your visualizations have the polished look that Power BI makes so easy to achieve. And finally, once all of these steps have been achieved on the individual visualization, make sure that it's been placed appropriately in a page of a report. Interactivity is another really strong point in Power BI. All visuals in Power BI have at least some degree of interactivity. They display tooltips and usually accept user input, which is then used to sync one specific visual with other visuals in the page. Clicking on chart elements can be used in order to bring data into focus, or to drill into data, or to drill one level up in hierarchical data. Power BI is great at understanding hierarchical relationships in data fields. A couple of other important points to keep in mind: interacting with one visual will often cause other visuals on the same report page to change dynamically, and it's also possible to make use of a widget known as a slicer in order to filter or restrict the data that a visualization uses. This kind of filtering is possible using slicers as well as Power BI filters, and we will explain the difference between these two constructs in the demos coming up ahead. Now that we have a good overall sense of the different types of visualizations available in Power BI, let's turn our attention to specific chart types and their uses. Now, it so happens that chart selection is also an important topic from the perspective of the DA-100 certification exam. Questions about visuals will usually involve a case study centered around a real-world business case. You'll often be asked to select the type of chart for a specific use case. For instance, what kind of chart would you use in order to show variations in expenses over time? If you read all of the provided context carefully and make sense of the use case and try and put yourself in the shoes of the end user of the visualization, you will usually be able to find the right visual. So for this process, it's important to understand the use cases and the provided context, as well as the capabilities of all of the common types of visuals. So from this perspective, it's a good idea for us to understand each type of control and its capabilities. Let's plunge right in, starting with tables. As we've already discussed, tables are one important kind of tabular control present in Power BI. These can be used to represent the source data, which is also going to be presented in an accompanying visual. So even though a table is not really a visualization, it usually accompanies a visualization and can be used to accept user input to govern that visualization. Because a table presents the raw data as is, it can be used for pretty much any use case, for comparison, composition, or the analysis of relationships. Do keep in mind that a table is an inherently two-dimensional representation of data, that is, data with rows and columns. So a table really makes sense when we have a relatively small number of variables in our data. As the number of variables increases, tables become more and more restrictive, and you might want to think about matrix controls or other types of multivariate visualizations. Perhaps the most common and powerful use case for a table is for when you need to drill down into the actual precise values in your data. For instance, let's say you're investigating some kind of data discrepancy and you're interested in knowing the value of a particular variable for a particular month down to the last decimal digit. It's hard to get this kind of information easily in any control other than in a table. Tables also make sense when your data has multiple different units of measurement, as well as in cases where you're interested in quantitative information but not in distribution or trends. As we shall see, distribution and trend information is best represented using specific visualizations such as scatter plots or line charts. The mirror image of this is a few use cases where you ought not to use tables. Tables do not make sense in use cases where the raw numbers do not convey meaningful information by themselves. Because tables are all about the raw numbers placed for the benefit of the end user, if those raw numbers are not insightful in and of themselves, a table is not a good idea. Tables are also not a good idea if you're trying to explore relationships or trends over time. Next, let's turn to the Power BI matrix control. As we've already discussed, the matrix can be thought of as the Power BI equivalent of an Excel pivot table. The great advantage of a matrix over a table is that multiple dimensions of data can be displayed and queried in an interactive fashion. Like pivot tables, matrix controls are great for hierarchical fields. This is where aggregated values, including headings and subheadings, totals and subtotals, can all be displayed. Now, the table and matrix abstractions were really more tabular than visual abstractions. Let's turn our attention to the first chart type, and that's the column chart. On screen now, you can see a column chart. On the x-axis, we have country name, which is a categorical variable. On the y-axis, we have a continuous, that is a numeric variable. The term column chart is used because the basic element here is a column which is vertical. Those columns are also accompanied by captions or data labels which contain the exact numeric value associated with the corresponding column. So when should you be thinking of using a column chart? Well, whenever you'd like to compare values across categories or changes in a value over a period of time for a single category, a column chart ought to come to mind. Remember that the x-axis in a column chart usually has a categorical variable. So if, for instance, you'd like to show sales for individual years, here each year can be thought of as a category, then a column chart makes sense. If you'd like to represent sales over a period of time, such as by day, then a line chart might make more sense instead. Column charts are also useful when users are interested in the actual and precise value for each category, because we can easily accompany each column in the column chart with a data label containing that actual precise value. Remember that column charts consist of columns, and of course the whole point of a column is to compare the heights of the columns or bars used for different quantities. So column charts ought to be used whenever you'd like to compare quantities, and it's the heights of the corresponding columns that you will use for that comparison. Now at this point you might be wondering to yourself what the difference is between a column chart and what's commonly referred to as a bar chart. You should be aware that the term column chart is specifically used in Power BI to represent visualizations where the columns are vertical. If these columns were horizontal, this would be called a bar chart instead. Now, the column chart we just looked at was two-dimensional, but we can also use something known as a clustered bar or column chart in order to represent more than two variables. Specifically, if we have multiple categorical variables that we wish to represent on the x-axis, a clustered bar or column chart is what we'd like to use. As the name would suggest, we then will have clusters of bars or columns where each bar within a cluster is encoded in a different color based on the value of that categorical variable. This will become more clear with an example. Here on screen now is a clustered column chart. As you can see, this visualization has information about not two but three variables. Those three variables are the grade, the test score, and the subject. We have clusters of columns. These clusters include two columns, one each for each subject. And then we have one cluster each for grade 8 and grade 9. A clustered column chart extends vertically. A clustered bar chart extends horizontally. So here, as you can see, we have again three variables. These are role, location, and income. We have two clusters, one each for the role analyst and the role scientist. Within each cluster, we have two bars, one each for the locations New York and California. Now, if a clustered bar chart has clusters of bars placed adjacent to each other, a stacked bar chart is one where we would have these individual bars stacked one on top of the other. So a stacked bar chart also can be used to depict information about more than two variables. However, that information can now consist of parts of a whole in addition to trends over time. Let's now turn to some best practices for column and bar charts. Such visualizations make sense when the number of categories being compared is small. It's a good idea to have the numeric axis start at 0, make sure that the bars are not truncated, and that the magnitude and units of the values are clear. And it's also often a good idea to include the value labels or data labels for each bar to help with readability. When choosing between a stacked bar or column chart and a clustered bar or column chart, only go with a stacked chart when the values can be summed up meaningfully. For instance, if you're representing sales for one geographic area and you'd like to compute the total sales across all geographic areas, then stacked bars do indeed make sense. On the other hand, if you have values which represent different dimensions or different units, then you should not use a stacked bar or column chart. You should go with a clustered bar or column chart instead. And when it comes to the aesthetics, it's usually a good idea to use solid colors rather than stripes for the bars. This way, the visuals remain clean and crisp. Let's continue with our discussion of the important chart types in Power BI. We are now turning our attention to line charts. A sample of a line chart is visible on screen now. You can see that on the x-axis we have time. Here, time has been represented as a continuous rather than as a categorical variable. On the y-axis, we have a numeric column. Then within the body of the chart itself, we have multiple different lines, and each of these lines corresponds to a different data series. Here, the arrow marks, for instance, highlight the red line, and we can see from the legend of symbols over on the top right that that red line corresponds to the state of Ohio. So this line chart also represents three variables, and those three variables are time in the form of the year, the location or the state of the plants, and the production quantities of those plants. These three variables are represented using a continuous curve, that is, using a line rather than a set of discrete bars. And this brings us to an important difference between line charts and column or bar charts. On the x-axis or on the independent axis, we have categorical variables in a bar or a column chart, but we have a continuous variable in a line chart. Here, that continuous variable on the x-axis is time. Line charts are used extremely often for this particular use case, that is, for analyzing trends over time. Line charts are very useful when we have a continuous dataset and we'd like to see changes in the dataset over a long time period. So line charts typically make sense with larger datasets than bar or column charts. In a line chart, the emphasis in the visualization is on the flow or on the continuous nature of the data being visualized. Note please that Power BI, like Excel, allows line and column charts to be combined in a single visual. So this is something which we'll see in the demos coming ahead. Next, let's run through some best practices for line chart construction. Use solid rather than dotted lines whenever possible. Do not make your line chart too crowded, so restrict the number of lines to 4 to 5. Have the time axis always run from left to right. That's the natural flow of time. Try to make sure that your time intervals are all equal sized. And finally, make sure that the axis range is selected such that all line values can be displayed. Now, if column charts were ideal for comparing the heights, that is, the magnitudes of quantities in different categories or time periods, and if line charts are best for identifying time trends, pie charts are ideal for identifying composition at a specific moment in time. On screen now, we have an example of a pie chart depicting global sales by region. You can see that the pie chart takes the form of a circle. That's where the name pie comes from. There are different slices, and those slices correspond to colors, which are explained in the legend of symbols on the top right. So again, pie charts are used to represent composition, that is, how different parts make up a whole. Pie charts can be used to represent either the raw values, that is the absolute values, or the percentages that each category contribute towards the whole. Finally, if your main intention is to compare different values, then a pie chart is probably not your best choice. A bar chart is probably better for comparison. A tree map is probably better for composition, because it's the angles in a pie chart that represent the relative proportions, and those angles can be hard to interpret. A pie chart does make sense, however, when you'd like to get a very quick visual sense of the most important categories which make up a whole. In such situations, and especially when the number of categories that you have is relatively small, a pie chart is ideal. Now, a pie chart consists of a circle, and the sum of the angles within the slices must be equal to 360. So in other words, you only ought to use a pie chart when all of the sections do indeed add up to 100%. Secondly, as with any other visual, you should try and avoid making your visual too cluttered. In terms of a pie chart, you should try and avoid a pie chart which has more than 4 or 5 pie slices or pie sections. If you do have more than 4 or 5 such slices, you have two choices. You could either go with a tree map instead of a pie chart, or you could only include the most important 4 to 5 categories and sum up all of the remaining categories into a slice called Other. Finally, pie charts tend to be most impactful when the category values are not identical to each other, and in fact when they are not even close. So for instance, if you had 4 sections, each representing 25% of the pie, then a pie chart would probably be a poor choice. Why? Because such slices, which are all very close to each other in magnitude, are hard to interpret with respect to order. It's hard to tell whether one angle is ever so slightly greater than another angle, And in such situations, it's confusing to know which category matters the most. So again, try to use pie charts when your category values have a wide level of dispersion. Next, let's turn our attention to another chart type. This is a favorite of folks in statistical or scientific computing, and this is a scatter chart. You can see an example of a scatter chart on screen now. This scatter chart has two continuous variables. On the y-axis here we have clicks, and on the x-axis we have views. You can also see that the scatter chart in this form simply visualizes or highlights the individual points in a two-dimensional space. No attempt is made to fit a curve through these points. Now, some scatter charts also include a trend line, and as you can see in this visual, adding a trend line would make it clear that there is a clear positive relationship between the two variables which we display on the x and the y axes. So scatter charts are ideal when we'd like to represent the relationship between two variables. Scatter charts are inherently bivariate in their nature. In the example we just looked at, it was very clear that there was a linear relationship between the two variables, but just by eyeballing the points in a scatter plot, we can usually get a good sense of the functional form of the relationship. What do we mean by the functional form? Well, whether we ought to use a linear, exponential, logarithmic, quadratic, or higher polynomial form to express one variable in terms of the other. It's also possible to find that our scatter chart shows no pattern at all. And in such a situation, we conclude that these two variables are independent of each other and there's no pattern or functional form which correctly links them. This last use case becomes particularly important while analyzing the scatter plot of residuals from a regression. A scatter plot is also a great way of identifying the distribution of data or clusters which may be present in our data, and scatter charts also help us to identify or highlight outlier points or anomalies. Such outlier points or anomalies might be data errors, or indeed they might be indicative of some underlying phenomenon in our data which we have yet to properly understand. Now, scatter plots in their most basic form are indeed two-dimensional, but there are some tricks and techniques that can be used in order to represent more than two dimensions using a scatter chart. And these in turn lead to our next chart type, which is the bubble chart. Here is an example of a bubble chart on screen now. This is quite similar to a scatter chart in that we have two continuous variables on the x and the y axes, and then we have individual point markers for the corresponding points in our dataset. Where things get very different is in the variable size of the different points or bubbles contained in this chart. And the area of those points is used to encode a third variable. That variable is the horsepower. We can see this from the title of this particular bubble chart. Finally, you can also see that the different bubbles have subtly different colors, and those different colors are explained using the legend of symbols on the top right, and these colors are used to encode a fourth variable into this visualization, and that fourth variable refers to the car type. So in this way, the bubble chart has not two, not three, but four variables represented in one two-dimensional visual. And thus, a bubble chart is a variant of a scatter plot that can be used to represent more than two dimensions. The dimensions of the bubble can be used to encode a third variable, and the color of the bubble can be used to encode a fourth variable. A few best practices to keep in mind while constructing scatter or bubble charts. Typically use this data in order to look for relationships. Make sure that that relationship is clearly interpretable, and if not, switch to a different chart type. Use the size or color to incorporate the additional dimensions. Start the axis at 0 in order to represent data as accurately as possible. And finally, use the area of the bubbles rather than the diameter of the bubbles in order to encode the third variable. We now have a thorough grasp of some of the basic building blocks of visualizations in Power BI. Let's turn our attention to some more specialized Power BI chart types, including maps, funnels, and more. These specialized chart types are very niche in their use cases. Bar charts, scatter charts, line charts, and pie charts have broad use cases and will likely be part of most reports. However, for some specific use cases, these common chart types might not get the job done. And in such cases, the more specialized chart types, which are very narrow in applicability, might be exactly what you require. Consider, for instance, a waterfall chart. On screen now, we have a waterfall chart where we have an initial value, that's the operating revenue. That's the bar which starts from the x-axis over on the left. And then we have floating bars which represent changes or deltas which are applied to that initial state, leading to a final state, that's the total, which is way over on the right. And so the waterfall chart has a very specific use case. It's a great way of getting across the composition of a numeric value or the accumulation towards a final value. And what's more, unlike a pie chart, in a waterfall chart, you can represent quantities which are not of exactly the same type. So a waterfall chart can be used to represent how an initial value gets updated by intermediate values, and those intermediate values in turn give us a final result. Please note that the initial value, the intermediate values, and the final values might all be different in terms of units or nature of measurement. Waterfall charts are heavily favored in finance and accounting use cases, and a very common use case is to show how different line items relating to revenues or costs stack up and give us either a profit or a revenue number. In recent years, the support for waterfall charts has improved in many common software packages, including Microsoft Excel, but even so, Power BI offers a really quick and easy way to work with waterfall charts. Next, let's move to another specialized visualization type, that's the funnel chart. On screen now is an example of a funnel chart, and this one represents the sequential steps in a sales process. You can see that this particular funnel starts with lead generation. That then leads to a sales call from a member of the sales team, follow up, hopefully conversion, and finally the closing of the sale. This is called a funnel because you can see that the start is broad and the end is very narrow. Not all of the data points in the first step of the funnel are going to still exist at the last step. Not every lead that we get is going to convert to a closed sale. And it is for exactly such use cases that funnel charts become so useful. If we'd like to compare the efficacy of two different sales teams, if we were to plot two such funnels, one for each sales team, and place them side by side, we'd get a quick sense of where one sales team outperforms the other, or where there is a sudden drop off in performance. In this way, a funnel chart represents a series of successive steps and a completion rate for each step. By its very nature, a funnel chart only makes sense when these steps are sequential, that is, when one step follows after another. Funnel charts can be used to represent sales funnels or conversion rates for websites. While creating funnel charts, it's important to ensure that each step or the sequence of steps is set up correctly and is correctly scaled based on the data for your use case. Just as waterfall charts are usually associated with financial use cases, funnel charts are usually associated with sales and marketing use cases. That's because these often correctly represent the linear sequential steps in a sales or marketing process. A much more universal kind of visualization is a map chart. As its name would suggest, this is a form of visual which conveys data where the main dimension is geographical. For instance, revenues in a country. By using a combination of a map along with color coding and tooltips and highlighting, this can be used in order to find insights related to geographies. Now, of course, for map charts to be supported by any visualization package, it's important for that package to have inbuilt support for maps. And in the case of Power BI, that comes from the underlying support provided by Bing Maps. In practical terms, this means that if your dataset contains geographical entities such as country, state, or city, you can quickly and easily use Power BI in order to plot those on a map. All you need to do is make sure that your region names are recognized by Power BI. For instance, if your data has a column or a field known as country and all of the country names there match with those recognized by Power BI, then you can use country as the basis for a visualization. And in that visualization, you can plot other fields such as revenue or profit or population or any other field in your dataset. And the visual support for the mapping will come built in from Power BI. A quick word here on two types of mapping visualizations available in Power BI: maps and filled maps. Maps, which we refer to here as regular maps, filled maps are better for categorical data. In the first kind of map visualization, each geographic unit will include a bubble, and the size of the bubble can be used to represent the magnitude of the plotted value. In the case of a filled map, the interior of the geographic region will be shaded in, and that shade can be set to a color scale, where that color scale in turn encodes some numeric field. Power BI also has support for ArcGIS. GIS is an acronym for Geographic Information System, and ArcGIS is a suite of GIS software. ArcGIS includes support for layering of information as well as for easy printing. That does it for our quick look at mapping support in Power BI. Let's turn to another powerful type of visualization, that's the tree map. On screen now is an example of a tree map which represents phone sales in Africa. As you can see, we have individual rectangles corresponding to each of the important countries, and the areas of those rectangles are directly proportional to the sales in that country. The largest rectangle is in the top left, and as we move towards the bottom right, the rectangles become smaller and smaller. This is a fairly typical use case for a tree map. Tree maps have some similarities to pie charts in that a tree map, like a pie chart, consists of various sections which correspond to subcategories. Tree maps, like pie charts, can be used to convey proportions of the whole. Unlike pie charts, however, tree maps are great for representing hierarchies. Every individual rectangle can be used to hold multiple variables which together form a hierarchy. Tree maps are a natural fit with Power BI because Power BI has built-in support for hierarchy, hierarchical fields, and drill downs and drill ups. And for that reason, Power BI tree maps are an excellent type of visual, and you should be thinking about using them whenever possible. We will be covering each of these specialized types of visualizations in a lot of detail in the demos that lie ahead. To wrap up, here are some parting words on custom visuals in Power BI. The built-in types of visualizations that we've discussed so far are sufficient for most use cases. However, there are even more specialized visuals which might work for even more niche applications, such as candlestick charts for technical stock analysis, word clouds for natural language processing, radar charts where we have a large number of categorical variables. Variations of standard visuals may also be made more engaging using bar races or tachometers. Custom visuals can be built for Power BI using the Power BI Visuals SDK, and these are then made available for general use using AppSource. We've spent some time covering the individual types of visualization supported in Power BI. We will now turn our focus to how these visualizations can be put together into a coherent whole in the form of a Power BI report. The term report has a specific meaning in Power BI. This is used to refer to a specific type of Power BI document. In a report, you can combine multiple visuals from an underlying dataset and use those visuals to tell a story. A report can have multiple pages, and each page can have multiple interconnected visuals. And in this way, a Power BI report has some similarities to an Excel workbook. Just as an Excel workbook can contain many different worksheets, in similar fashion, a Power BI report can contain many different pages. A report can be shared with collaborators and end users. So Power BI reports are the logical units of working with data in Power BI. Let's take a moment to understand the purposes of using the report abstraction. A report helps you to present data from multiple angles or perspectives. The pages within a report enable interactions, and these interactions also have context, such as filters and drill downs. Those pages are also interconnected. Actions on one page can be synchronized with actions on another page. The report ought to be set up such that end users can extract insights and such that those insights can then be used to drive business decisions. The process of compiling a report has some similarities to the process of creating a PowerPoint presentation. It also has some similarities to creating an Excel workbook. The steps in compiling a report broadly are as follows. First, start out with a high-level understanding of the audience of the reports and what it is that they wish to achieve from your analysis. Then perform a preliminary analysis and build a rough outline of the story that you wish to convey to your audience. Then pick the visualizations that best convey or get across that story, and finally combine those visualizations into a report, place them on the different pages, wire up the interactivity between those different visualizations, and create that report and get it into a finished form before sharing it with your audience. While designing the report, pick and configure the visuals and place them on one or more pages. Group these visualizations logically so that visuals on the same page are related to each other. Also, make sure that the visualizations are dynamically connected so that interactions with one visual alter the others in the same page in a natural manner. While doing so, a couple of considerations to keep in mind are accessibility and readability, as well as mobile optimization. So do make sure that the size of your visuals optimizes readability for all users, and also do try out the mobile layout in order to ensure that those viewing or consuming your reports from a different device get an optimal experience. A lot of these considerations would also exist if you were to design a well thought out and effective PowerPoint presentation. However, in addition, Power BI has a lot of additional functionality, and you should be sure to use that optimally. For instance, buttons and bookmarks can be used to navigate between pages of your report. You can use tooltips, titles, and labels to provide valuable context, and you can use hierarchies of fields or columns and enable drill throughs so that your users can zoom in and zoom out of the data as they wish to. As a really simple example of one page of a report, consider these two visuals placed side by side. On the left, we have a tree map denoting phone sales by country, and then on the right, we have a pie chart showing phone sales by brand. One possible way of wiring up the interactivity would be such that if we clicked on a country over on the left, then the corresponding pie chart displayed on the right should be specific to that country. In this context, it's worth our understanding the very special role played by slicers in reports. A slicer is a visual element. You can select this from the visualization toolbox and add it to any page in your report. As its name would suggest, a slicer helps you to slice or dice your data by applying filters to the visuals on a page. A categorical field in the data could be mapped to a slicer, and you also could have slicers for continuous or numeric fields. Those slicers would take the form of sliders. You can think of a slicer as a dynamic selection tool. Using a slicer, one or more categories can be selected, and the visuals on the page will change dynamically to reflect that selection. By default, a slicer selection only applies to visuals in the same report page, but Power BI allows you to sync slicers across pages as well. And in this way, it's possible for the selections on one slicer on a specific page to influence other pages in your Power BI report as well. Now, Power BI has a desktop app that's known as Power BI Desktop, and there is also a web-based SaaS product known as the Power BI Service. Once you've created your report using Power BI Desktop, you can publish that report to the Power BI Service. Also, once you've created your report, you could publish it and share it with collaborators who might modify it or review your work, or with the end users. This is the intended audience who will actually consume the data and the stories in your Power BI report. Power BI reports are the basic building blocks in Power BI. They are akin to workbooks in Excel. But it's also worth knowing about another Power BI building block known as the dashboard. A dashboard can be thought of as a much simpler, high-level summary version of a report. It's a single page of visualizations that's meant to summarize the data from one or more reports. So this is important. One dashboard can include visuals from more than one report. Dashboards can only be created from the Power BI service, not from Power BI desktop, and they aren't really intended for detailed analysis. For instance, it's not presently possible to incorporate a slicer into a dashboard. Some best practices when it comes to creating and using Power BI reports. As with everything else, try and keep your reports simple. Use just enough visuals to get your story across. Do not overwhelm the audience with too much information. Where possible and necessary, implement row-level security to ensure that different members of your audience get views of the data compatible with their levels of access. Use reports in order to construct your stories, and then use dashboards in order to summarize those reports. And finally, stick to unified themes such as colors throughout all of the pages in your report. In addition to these aesthetic considerations, it's also worth keeping in mind performance aspects while building your reports. Do remember that there are different kinds of storage access modes which govern how a particular report interacts with the underlying data. If you're making use of direct query, then try and avoid the use of slicers, because every little interaction with the visual is going to trigger a round trip to the underlying data source. So where possible, use an apply button along with your slicers in order to make sure that you make all of the customizations that you require to your slicer before you actually communicate with the underlying data. This seems like a little point, but when you're making use of direct query, this can make a substantial difference to the performance of your Power BI reports. We have now come to the end of this course, Understanding Data Visualization. We began this course by understanding that data visualization can be used to convey information about data using visual elements such as graphs and icons. There are different graphs suited to visualize different types of data, such as line charts, bar charts, pie charts, etc. Different visualizations should be chosen based on what you would like to convey. Next, we began an exploration of different types of visualizations and their use cases. We first covered standard charts such as line charts, bar charts, pie charts, and scatter charts, as well as charts such as waterfall charts and funnel charts, which have very specific use cases and are not generally used outside their scope. Finally, we talked about the structure of Power BI and how it helps with data visualization. We first understood the concept of a report in Power BI before turning to some aspects of your report that you should manage and customize, such as the color and other aesthetics and the mobile phone layout of your report. Now that you have a solid understanding of the theory behind data visualization in Power BI, you are ready to move on to creating and formatting charts in Power BI. That's in the course with that same title coming up next.